Chapter 49 Total Solar Eclipses. The reason why our knowledge concerning the nature of the sun is still so imperfect that it is scarcely possible to decide between the diametrically opposed theories of Kirchhoff and Faye is that the remarkable phenomena occurring on the sun's limb are so completely overpowered by the blinding light of the solar nucleus or photosphere that they remain invisible even in the most powerful telescopes. It is not sufficient to get rid of the sun's rays by the interposition of an opaque screen, because the diffused light of the sky cannot be eliminated by this means. And this light even is so intense as to conceal the faint light of the sun's appendages. It is quite otherwise, however, during a total eclipse of the sun. Then the moon covers the whole of the sun's disk, and includes a large tract of the earth's surface in the cone of its shadow, revealing to the observer, who is no longer hindered by the light of day, a display of phenomena round the sun which can be seen in no other way, and the study of which is peculiarly fitted to throw light on the nature and physical constitution of the sun. When, at the commencement of a total solar eclipse, the moon in her course from west to east passes over the disk of the sun, the observer perceives by the use of a simple dark glass the first contact of the moon's disk on the west, that is to say, right side of the sun. If he employ an astronomical telescope, the image is reversed, and the eclipse appears to begin at the left side. If, however, he continue to observe it by direct vision only, the moon is seen to advance over the sun's disk from west to east, and the obscuration increases until the whole of the sun is covered, and the last rays disappear from the sun's eastern limb. Between this moment, the commencement of total darkness, and that when the following edge of the moon touches the sun's western limb, where at the same instant the solar rays reappear and the total darkness is at an end, are comprised the few precious moments for the sake of which costly expeditions are prepared, and the interest of learned and scientific men of every nation greatly aroused, since in these moments a unique opportunity is afforded for the investigation of the central body of our system. And the successful use of this opportunity is entirely dependent upon the weather, for a momentary veil of cloud or a fleeting wisp of vapor may render unavailing all the trouble and expense incurred. We will not suffer ourselves to be detained by a description of those changes that pass over the landscape as the darkness advances, nor dwell upon the deep impression which the sudden disappearance of the last rays of the sun, and the equally sudden reappearance of the light, make both upon men and animals. The diameter of the cone of the shadow thrown by the moon towards the earth amounts at the spot where it touches the earth's surface on the equator during the time of totality to about miles. As, however, the moon which throws the shadow only completes its course in the heavens round the earth from west to east in 1 month, and the earth which receives the shadow accomplishes its revolution from west to east in 1 day. It follows that the motion of the moon's shadow is very much slower than that of the earth's surface. It therefore happens that the earth appears to run away from under the moon's shadow, or that the moon's shadow seems to run over the earth from east to west. From an elevated position, the shadow of the moon is seen to approach with enormous rapidity, and the sensation as though a material substance, such as a terrific cloud of smoke, were rushing over the earth's surface, fills the uninitiated spectator with fear and dread. A few minutes before the commencement of the totality, the brightest stars become visible, and the sharply defined black edge of the moon appears surrounded on all sides by a very narrow but very brilliant ring of light of silver whiteness, which is called the corona. From the corona faint rays of light, irregular in length and breadth, stream out in all directions, surrounding the moon's disk like a glory, whence this crown of rays is usually designated the glory Gloires Aigrettes, or halo, drawn by Dr. B. A. Gould, and represents the total eclipse of the 7th of August, 1869, as it appeared to the unassisted eye at Des Moines in North America. When the total darkness has commenced, the prominences make their appearance, which are cloud-like masses of a rose or pale coral color, disposed either singly or in groups at various places on the moon's limb. They pierce the corona in the most wonderful forms, sometimes as single outgrowths of enormous height, sometimes as low projections spreading far total solar eclipse of 7th August 1869 along the moon's limb. The prominences are generally first seen on the eastern left side of the sun, where at the commencement of the totality the moon only grazes the sun's edge, and the space immediately surrounding the sun is yet uncovered. In proportion as the moon advances to the east, the space immediately surrounding the western parts, W of the sun, becomes free. And the prominences are then seen also on that side in greater number, and developed with much greater distinctness. There remains now no longer any doubt that these remarkable phenomena belong to the sun, and are great accumulations of the luminous gaseous material by which the solar body is wholly surrounded. It cannot therefore greatly astonish us that their forms have been seen to change, even during the short duration of the totality. That which calls much more for wonder is the enormous height to which these pillars of gas extend beyond the limb of the sun, a height which, in some instances, exceeds 90 miles. Chapter 50. Photographic pictures of total solar eclipses besides the important observations of the first, second, third, and fourth contacts, especially needed by astronomers for a more precise determination of the diameters of the sun and moon. And the direction of the moon's course, careful attention is also given during a total eclipse to the corona and halo, corona neb Strahlenkreis, and especially to the prominences. The telescope was formerly the elusive means of observation. Photography was first made use of at the great solar eclipse of I-160 in Spain, where it was employed with very good results by Secchi and de la Rue at different stations. It will in future be extensively applied to the record of important eclipses, since photographic pictures taken of the sun through the telescope at different periods of observation give a faithful transcript of the phenomena taking place. And when the pictures are taken at rapidly succeeding intervals and at stations far removed from each other, they afford, when collected together, a vivid picture of the whole course of the eclipse, as well as of the phenomena which has occurred during the totality. The apparatus needed for astronomical photography is as follows. 1. An astronomical telescope. 2. A driving clock to carry the telescope in a direction contrary to the revolution of the earth, at such a speed that a star placed on a wire or in the axis of the instrument should not alter its position, notwithstanding the motion of the earth on its axis, and that the telescope, without any interference on the part of the observer, should follow precisely the apparent motion of a star or any other object in the heavens. 3. The photographic apparatus, which in its connection with the telescope consists only of a contrivance for holding the slide containing the prepared plate in the place where the image is formed by the object glass, and upon which the eyepiece is usually directed. This slide is so arranged that the light may be admitted onto the glass plate for either the fraction of a second or for a much longer period, according to the will of the observer. This contrivance must be fixed at the upper or lower end of the tube, according as the telescope is a reflector or a refractor, that is to say, whether the image be formed by a mirror or lens. 11. Figure No is shown the photographic reflecting telescope made by Browning for the Indian government, with which Colonel Tennant took photographs of the eclipse of the 18th of August, 1868, at Guntur. The tube, AIA, is constructed of iron in 3 pieces connected together by the 2 rings CC, and contains at the lower end the concave mirror B of silvered glass, figure high. By means of 2 projecting screws, this mirror can be easily so adjusted that the rays reflected from it to the plane mirror MN, and thence to the opening R, shall there form a small sharp image of the object to be observed, the sun for instance. The telescope AA is attached to the declination axis and is counterbalanced by the weight D. Close to this counterpoise is fixed the declination circle, by which the angle the tube makes with the direction of the pole is measured. The hour circle E is fastened to the polar axis GG and registers the right ascension on the fixed vernier fort. On the underside of the circle are 3 friction wheels, 2 of which are shown in the drawing, by which the friction of the polar axis placed parallel to the axis of the Earth is so reduced that a weight of 9 pounds, hung at D on the declination, axis is sufficient to set in motion the movable part of the instrument, weighing about 5 cwt. The weight of the instrument is counterbalanced by the massive weight and attached to the end of the polar axis, and the telescope counterpoise D and the circle E, with its driving screw, are thus held in equilibrium. The polar axis GG carries the driving wheel I, made of gunmetal, which is set in motion by means of an endless screw placed underneath. The axle beds of this screw can be moved aside to allow it to be placed either in or out of contact with the teeth of the driving wheel I, a contrivance requisite for enabling the observer to turn the telescope by hand in any direction, and fix it on the object to be observed. When this has been accomplished, and the screw-ass is pushed back into the toothed wheel I, the telescope can only be moved as the clock drives it. The works are enclosed in the square bronze case T, and are propelled by means of the driving weight U. The governing balls, keys serve to regulate the clock, which sets in motion the endless screw, and turns the driving wheel I, and the polar axis GG. The solar rays falling parallel on the mirror B, the diameter of which is GGA inches, will, as shown in of the mirror, distant 549 in it. Intercepting the rays close in front of the focal point is placed the diagonal mirror MN, by which the converging rays are reflected sideways and thrown into the eye tube R. The rays unite somewhat beyond the tube R to form an image, which is a point when the luminous object has no sensible diameter, but as the sun subtends an angle of about 3/2. Its image formed at the focus is somewhat more than 3/4 of an inch in diameter. 3°6 the eyepiece tube R serves for the reception of the photographic slide, and for this purpose contains a tube C, figure 112, which is entirely closed from both light and dust by means of two springs phi, and which can be moved in and out by the use of the powerful screw D. At the end of this inner tube C is the slide E, figure 113, which holds the sensitive plate prepared for the reception of the photographic image. The construction of this dark slide will be easily understood from the drawing. When the opaque shutter B has been pushed in so as to cover the 4 fine silver wires, the prepared plate is laid upon the silver ledges fixed at the corners, and the door is shut. The slide is then inserted at the end of the tube C, figure 112, the shutter B drawn out and the plate exposed to the action of the light. After a suitable exposure, 0 is again pushed in, and the slide taken away, and replaced in the telescope by another containing a newly prepared plate. In order to avoid delay during the short duration of totality, 6 dark slides with as many sensitive plates were prepared beforehand for photographing the phenomena. To secure the perfect definition of the cross marked by the 4 silver wires on each plate, the purpose of which was to show the exact position of the sun's axis upon each photographic picture. The wires were placed at a distance of only an inch from the surface of the prepared plate, without, however, interfering with the action of the exceedingly thin shutter B, which moved up and down with safety between the wires and the plate, touching neither the one nor the other. The focus required for the plate, that is to say, the distance to tube C, figure 1 of R, was ascertained by previous trials. For this purpose, a round sliding shutter was constructed at the back of the door, figure Rio, which, when open, allowed of a view into the interior of the dark slide onto the ground glass. The 2 pictures represented in figure 114 are faithful copies of the photographs taken by De la Tolle eclipse of 18th July, photographed by De la Rue at Rivaballoza in Spain on the 18th of July, 860. The first shows the appearance of the eclipse at 3h40s GMT. The corona appears as a soft, gentle light round the intensely black moon. The prominences stand out conspicuously in different parts of the corona, and among them, one at the upper left side assumed the form compared by De la Rue to a Turkish scimitar, and reached the enormous height of 70 miles, 3 degrees. The rays of the halo emanating from the corona appeared with great beauty in the telescope and to the unassisted eye, but the light was too faint to make any impression on the photographic plates. Since these pictures were taken, spectrum analysis has entered the service of astronomy and has been rendered mainly by the labors of Kirchhoff. So indispensable in all investigations of the sun that the spectroscope forms now an important part of the requisite apparatus for observing the phenomena of a total solar eclipse. When it is remembered that astronomers have now, in addition, the self-registering electric chronograph for recording time, as well as the newly invented photometer by Zollner for measuring the amount of light, it may be supposed that for the efficient use of so many delicate instruments and the observation of so many phenomena, several experienced astronomers, photographers, and physicists are required at each station, and therefore the outfitting of an expedition for observing a total solar eclipse is both a difficult and expensive undertaking. Chapter 51. The total solar eclipse of 18th August 1868. August 1868. This eclipse afforded a remarkable combination of advantageous circumstances and excited considerable interest from the fact that it could be well observed from many stations widely separated, and also that the duration of totality being 6 50s was very nearly the greatest that can ever occur in an eclipse of the sun. A total solar eclipse is a phenomenon of rare occurrence at any fixed spot. The last visible in London took place in 1715. And the first in this century to be seen at Berlin will not occur till the 19th of August, 1887, while in Paris there will not be one during the whole of the 19th century. The eclipse of the 18th of August, 1868, offered sufficient inducement, therefore, to assemble the scientific men of all nations for its observation, and it might perhaps be asserted that it excited the interest of all nations in a higher degree than any other astronomical phenomenon of this century. The zone of total darkness passed over the southern part of Asia from Aden across Hindustan, Malacca, Borneo, Celebes, etc., in a breadth of 138 miles, and expeditions furnished with efficient and costly instruments were sent out by the North German Confederation, Austria, France, and England, under the superintendence of well-known astronomers. The zone of totality from Aden to Torres Straits is represented in Figure 115, in which the various stations are marked. The central dark line denotes the middle of the shadow, where the duration of totality was greatest. According to a calculation previously made by Dr. Weiss of Vienna, the sun rose eclipsed in that region of Abyssinia where the Blue Nile begins its northward course. The nucleus of the shadow-grazed Gondar, with its northern edge, passed over the lake of Zaka and by the straits of Bab el-Mandeb to Aden, the first station marked in the map. Then it crossed the Arabian Gulf to southern India, where the districts Jamkhandi, Bijapur, Mulwar, Guntur, Masilapatam lay near the central line, and the duration of totality varied from 5 10s to 5 45s to In the Bay of Bengal and in the Malay Peninsula, Watan, the duration of total darkness increased till in the Gulf of Siam it attained its maximum of 6 a.m. 50s. The zone of totality passed then through the southern point of the Anamba Islands, over the northern portions of Borneo and Celebes, and through the middle of the Molucca group. The cone of shadow passed further over the southern bay of New Guinea, the northern point of Australia, and finally over the Pacific Ocean to the New Hebrides, where the sun must have set while still eclipsed. The North German Confederation sent out 2 expeditions, one of which, consisting of Dr. Thiel from the observatory at Bonn, and the Berlin photographers, Drs. Vogel, Zenkler, and Fritsch, selected Aden as a station, while the other, with Professor Spurrer of Anklam, Dr. Tietjen of Berlin, Dr. Engelmann of Leipzig, and Kopp of Berlin, repaired to Mulwar in the Bombay Presidency 4 miles south of Bijapur, Tupi. The Austrian expedition, under Dr. Weiss, Dr. Pulzer, and a naval officer, Lieutenant Ziha, remained at Aden with the 1st Division of the North German Confederation. 3. France also sent out 2 expeditions. The first was under the superintendence of Janssen, an observer greatly experienced in spectrum investigations, who selected the station of Guntur. The second, comprising Stephen, director of the observatory at Marseille, and among others the physicists Rayet and Tisserand in the engineer hall, was sent farther east and stationed themselves at Watan, a small place near the sea, in the peninsula of Malacca. The English expeditions were also admirably prepared. The one under the conduct of Captain Herschel took up its position on the western coast of southern India at Jamkhandi, in the neighborhood of Belgium. Another detachment under Capt. Haig and Tanner was stationed at Bijapur, while a third, superintended by Colonel Tennant, and equipped especially for photographic purposes, occupied a locality further east at Guntur, where Janssen also was stationed. 5. The Jesuits at Manila in the Philippines fitted out a small expedition consisting of Fathers Foro, Nanel, and Ricart, stationed at Mantawala Kiki, a coral island at the entrance of the Gulf of Tamini or Garantola, where in company with Captain Charles Bullock of HMS Serpent, the eclipse was observed with good results. This station was in 0 degrees 32 501 south latitude in 1230-27, 275 east longitude from Greenwich. Besides these very complete expeditions, furnished with every requisite instrument for scientific investigation, there were many private individuals, some possessed of very good telescopes, who happening to be in the line of totally observed the eclipse with praiseworthy zeal, and obtained some good results. Among these was Captain Reynoldson, who crossed the line of shadow in mid-ocean in the steamer Rangoon, and the 4 sketches he took during the totality were among the first pictures published of the eclipse. The eclipse was observed also by the governor of Labuan, Mr. J. Pope Hennessy, on the west coast of Borneo, in company with Captain Ree and others, and the account he gave of the phenomena of the eclipse, with the readings of the barometer and thermometer during its course, is of the greatest interest. At Adani, a town near Bellary, in 15 degrees 37 north latitude and 77 degrees 20 east longitude loop, Warren, possessing a good telescope, watched the phenomena of the eclipse with care, and has published his observations, including the variations of the thermometer. The Dutch doubtless sent an expedition to the zone of totality from their settlements in the islands of the archipelago, but no published account of their proceedings has yet appeared. With the purpose we have in view, we must pass over the results of the various expeditions as far as they are purely astronomical, such as the measures in position and height of the prominences, and the observations of the polarization of light in the corona, as well as those that relate to the variations of light and heat, the changes in the density of the atmosphere, etc., in order to dwell in detail on those phenomena registered by photography and spectrum analysis, since they are of such high importance that their full significance cannot as yet be fully realized. Photographic pictures of the eclipse of the 18th of August, 1868, were taken by the following expeditions. 1. The North German expedition at Aden under Drs. Vogel, Zenker, Fritsch, and Thiel. 2. The English expedition at Guntur under Colonel Tennant. 3. The expedition of the Jesuits from Manila at Mantawala Kiki. The results obtained by Dr. Vogel, the first on the list, shall be narrated in his own words. He wrote as follows from the steamer in which he and his party returned to Suez. We rose early, by 4 o'clock on the morning of the 18th of August. About 9/10 of the sky was overcast. In a spirit of resignation, we commenced our preparations. The task before us consisted of taking as many pictures of the phenomena as possible during the 3 minutes the duration of totality at Aden. For this purpose, we had regularly drilled ourselves in the use of the photographic telescope. Like so many artillerymen at a gun, Dr. Fritsch prepared the plates in the first step. Dr. Zenker undertook the insertion of the dark slide into the tube. Dr. Thiel attended to the exposure of the plate and the telescope, which, by means of the clock, followed the course of the sun with such precision that its image remained immovable upon the prepared plate, and I developed the pictures in the second tent. We had proved by experiment that it was possible in this way to take 6 pictures in 3 minutes. The decisive moment came nearer and nearer. To our great joy, the clouds we had been watching with so much anxiety began to break, and the sun, already partially eclipsed, appeared occasionally as a crescent. A strange light overspread the landscape, something between sunlight and moonlight. The chemical action of the light was exceedingly small. The crescent kept diminishing. The breaks in the clouds seemed to increase. We began to hope. The minute before totality, which commenced at 6h20 m, flew rapidly by. Dr. Fritsch and I hastily crept to our tents and remained there, seeing unfortunately nothing of the totality under these circumstances. Our work began. The first plate was exposed 5 and 10 seconds to test the right amount of exposure. Mohammed, our black servant, brought me the first dark slide with the plate that had just been exposed. I poured the developing solution of iron over it, looking eagerly for the expected image. My lamp at this moment went out. Light, light, I called, light, but no one heard. Everyone had enough to do. I caught at the outside of the tent with one hand, holding the plate in my left, and happily found the oil lamp, which I had placed there, lighted in case of accident. Then I saw the small image of the sun appearing on the plate, figure 116 titled. The dark edge of the moon was surrounded by a range of remarkable elevations at one side, while on the other there was an extraordinary horn or protuberance. Both phenomena were perfectly analogous in the two pictures on the same plate. My delight was great, but it was no time for rejoicing. The second plate was soon brought me, and a minute later the third was also in my tent. "The sun is coming!" 9 called out Zenker, and the totality was over. All seemed but the work of a moment, so rapidly had the time flown. The second plate gave in developing only faint traces of an image, and showed peculiar markings. This was explained by thin passing clouds which had almost entirely interrupted the photographic action. The third pseudo total solar eclipse of 18th August, 1868, observed at Aden, picture 1. Plate, figure 7, taken during the third minute of totality, showed 2 successful pictures with prominences on the lower limb, as seen in an inverting telescope. The fourth picture, figure 118, was taken at the last moment of totality and exhibited yet more plainly the prominences that had already appeared on the western limb of the sun, by uniting in one drawing, figure 119, the various photographic pictures taken during the totality. A very correct conception may be formed of the way in which the prominences were arranged round the sun's limb at the time of the eclipse. Aden, picture 2. Chemical action of the light of the corona was not sufficiently powerful to leave any impression on the prepared plate during the short time of exposure. But through the telescope, and even with the unassisted eye, this phenomenon was seen at every station in all its glory. The great prominence on the eastern limb of the sun had an elevation of about 1/14 of the sun's diameter, or about 60 miles. In the various drawings of the totality, more or less carefully executed, which have been contributed by different observers, the prominences are very differently represented, both as to size and position. After rejecting those unworthy productions, prepare total solar eclipse of 18th August, 1868, Aden, picture 3. For sale, which are finished merely for effect according to the fancy of the artist. The chief cause of these discrepancies will be found to arise from the fact that the sun's disk assumes a different position with respect to the horizon, according as it is observed at sunrise, noon, or sunset. The same prominence therefore appears to occupy a different position with respect to the horizon in a picture taken early in the morning at Aden to that in which it appears in one taken at midday at Celebes. Another cause of discrepancy is to be found in the difference of time, about 7 hours, between the extreme ends of the central line of totality or zone of observation, one of which was at Aden and the other at Celebes. And during this time, great changes may have occurred in the position and size of the prominences, when it is remembered also that the image of the eclipsed sun appears inverted in an astronomical telescope, the upper part being seen below, and the right side reversed to the left. It will easily be understood that the various drawings of the eclipse present different appearances according to the place whence the phenomena were seen, and whether observed by the unassisted eye or by an inverting telescope. Guntur, 18th August, 1868. When the sun at noon has reached its greatest altitude, the highest point is the true north, the lowest point the true south. Standing face to the sun, the east lies 90 degrees from the north point to the left, and the west as many degrees to the right. A glance at figure 120 will show this more clearly. Sup 1868. Guntur, Cologne tenant, commencement of totality. Fiume of exposure sec. Guntur Cole tenant, towards the end of totality. Time of exposure sec posing the sun's circumference to be divided into 360 degrees. And the north point reckoned as 0 degrees, the point of due east, lies 90 degrees to the left of north, the south point 1800. and the west 270 degrees. If the sun be observed at any other time of day, a vertical line represented by the cross wires forms the apparent north and south line, the upper end of which is called the apparent north point, and the lower end the apparent south point. It is therefore easy for astronomers to calculate the true north for any time and place, from the apparent north by means of the latitude and the time of observation, as well as to determine by the use of a telescope provided with a suitable micrometer the angle which the apparent north and south line makes with any other line drawn from the center of the sun to its circumference. If therefore this angle, that is to say the apparent position of any particular object on the limb or disk of the sun, a prominence or a solar spot for instance, be measured and reduced to the true north and south line, and the angle thus determined, or the true position be drawn out upon a diagram of the sun's disk, divided into degrees, the correct place which the object occupied on the sun will then be found, whatever the position of the sun in the heavens may have been at the time of observation. The 7th of August, 1869, taken at Des Moines at 5 o'clock in the afternoon, at which hour the apparent north point was considerably removed from the true north. As the disk of the sun was never during any part of the totality concentric with that of the moon, a further correction is necessary for transferring the angles measured with the circumference of the moon to that of the sun. The angle of position for the great prominence, figures 1/1/6 and 120, was about 80 degrees. To assist in estimating the positions, the 4 true points of the sun are given in figure 116 and following pictures of the eclipse. The photographs obtained by Colonel Tennant at Guntur appear at first sight to have been less successful than those taken at Aden. He exposed 6 plates, in all of which the prominences were sufficiently well marked to allow of the photographs being compared one with another. Plate 7 exhibits exact copies of these photographs, published with the cooperation of Warren de la Rue. The upper picture shows the eclipse at the commencement of the totality, and the lower one immediately before its cessation. In all the pictures the same large prominence appears, which is to be seen in the photographs taken by the German expedition, while the configuration of the smaller prominences, also seen in each plate, presents a different appearance in every picture. Warren de la Rue has superposed magnified copies, something more than 2 inches in diameter, of Tennant's 6 original photographs, and by a careful estimation of the sun's center and the exact coincidence of the large prominence in all the pictures, has composed a drawing, figure 120, which not only gives a representation of the prominence's total solar eclipse of 18th August 1868 at Mantawalakiki, that made their appearance during the course of the eclipse, but also shows clearly by the first and second inner contacts the beginning and the end of the total darkness. In the figure, the shaded disk I represents the sun. 2 denotes the moon's disk at the moment of second contact, 2, first inner contact, when the totality began, and the large prominence appeared on the sun's eastern limb, the fair. 3 is the moon's disk at the third contact, 3, second inner contact. The drawing also gives the position of the sun's axis, the direction in which the moon's center was traveling from west to east, and indicates by the dotted lines over the prominences a peculiar faint glimmering light which appeared on the eastern side and was invisible in the telescope on account of the brilliancy of the corona and prominences, a phenomenon the nature of which, unknown as yet, may perhaps be discovered at some future eclipse. The spots drawn on the sun's disk are those which were photographed at the Kew Observatory on the day of the eclipse. The corona and the halo are both wanting in these photographs. The expedition of the Jesuits from Manila did not arrive at the place of observation, owing to an accident to the machinery of the vessel, till the evening of the 17th of August, the day before the eclipse, so that no photographic experiments could be previously made on the spot selected as a station. The 8 instantaneous pictures of the principal phases of the eclipse were successful, but of the 4 plates exposed during the totality, the second only, which was exposed 12 seconds, showed any trace of the corona. This loss was fortunately, however, repaired to some extent by immediately tracing upon the focusing glass of the camera the image of the totality as it appeared upon the smoothly ground glass, and permanently fixing the drawing thus made. Seen at Mantalakiki during the last two 125s, therefore just before the reappearance of the sun's rays. Scarcely had the last ray of sunlight disappeared, writes Father F. Borrow, in reporting the results of this expedition to Secchi in Rome, when the magnificent corona or aureola burst into view, as by enchantment round the black edge of the moon. The form that it assumed is shown in any artist to paint. All observers agree that it resembled mother of pearl or pure unpolished silver, but far more beautiful and more intensely brilliant. The corona consisted of three principal divisions. The first was a narrow circle of intense white light, forming an even band round the edge of the moon. The second extended further out, gradually diminishing in intensity, but preserving a tolerable regularity of form. The third was composed of a very large number of rays, which possessed various degrees of intensity, and radiated with great irregularity, some reaching to a distance equal to more than double the diameter of the moon. The aspect of the rays changed slightly from one moment to another, and it deserves special notice that a somewhat brighter line was seen to cut obliquely through the lower stratum of rays. This line represented a ray of light which made its appearance 5 minutes after the commencement of the totality, and remained visible as long as the darkness lasted, from the communications received from the various expeditions. It seems conclusive that the halo of the corona presented a different appearance at each station, but as the drawings of this phenomenon were made from estimations taken merely by the eye, their accuracy is not sufficient to warrant any conclusions being deduced from them. We shall enter more fully upon this subject when we come to speak of the spectroscopic observations of the corona, and the various theories that have been propounded as to its nature, with regard to the inner portion of the corona. The observations made at all the above-mentioned stations concur in this, that all light was not extinguished during the totality, but that immediately after the disappearance of the sun, contact 2, the intensely black disk of the moon was surrounded by a very white and brilliant narrow ring of light, from which the pale red prominence is projected at various places. The Austrian observers, as well as the French observers, Stefan, Tisserand, and Janssen, speak very decidedly of the formation of an intensely bright and very narrow ring of light. Solar eclipse of 18th August, 1868, observed from the steamer Rangoon. Therefore, scarcely any doubt that the lower part of the corona belongs to the sun, and that this close appendage of the sun is highly luminous, but that the intensity rapidly diminishes at a little distance from the edge. He observations of the total solar eclipse of the 1/8 of July, IA-60, in Spain when the prominences were photographed figure 114, as well as examined telescopically by many eminent astronomers. Left scarcely any doubt that these remarkable forms are of a gaseous nature, and belong not to the moon. Solar eclipse of 1868, observed at Watton by Stefan, but to the sun. The eclipse of the 18th of August, 1868, afforded an opportunity for acquiring complete certainty on this subject. At the same instant that the corona started into view, the prominences also became visible on the eastern limb of the sun, precisely at the spot where the last rays of light disappeared at the commencement of the totality. The first of these prominences, to the left of the vertical line, figure 116, was of an extraordinary height and shone with an intense rose-colored light. The other prominence at the right solar eclipse of 18th August. 1868, observed at Mantalakiki, side of the vertical line was of a similar color and of equal brilliancy, but was neither so high nor so beautiful in form. From the steamer Rangoon at the beginning of total darkness, when another prominence, much less in height, but spreading much further along the sun's limb, made its appearance almost simultaneously upon the opposite side, were drawn by Stefan during the course of the totality at Watton. Complete picture of the totality shown in figure 12.1 and merely represents the prominences as they were observed at Mantalakiki by the Jesuits from Manila to Watton. Before the reappearance of the sun, in explanation of this picture, we give an abstract of Father Foro's communication to Secchi. The breadth of the great promenade was I degrees 40, that of the second one SS amounted to 90 at the base. Scarcely had these prominences made their appearance when a third prominence, 7, broke out from the western limb of the sun, and gradually increased in size and beauty as the moon passed over the sun from west to east. The phenomenon of the gradual disappearance of the prominences from the eastern side and the simultaneous increase and extension of those on the western side was distinctly seen by all observers. The height of the two prominences, the moment they appeared in view, was respectively 310 and f15, and on repeating the measurements after an interval of 310, when the totality was about half over, their height was found to be J2 and O18s, more accurately, is equal to 445 miles. The prominence 7, which was seen at first with difficulty, was gradually disclosed as the moon passed on, and when fully visible presented the appearance of a long chain of mountains. It terminated very abruptly to the left, as if suddenly cut off, while towards the right it gradually diminished in height, until it was lost behind the dark disk of the moon, at the spot where the corona exhibited the greatest amount of irregularity. In the same picture, figure 124, a fourth prominent section is seen to the left of 7. It was completely separated from the other prominences, and presented the appearance of a cloud. The color was neither so brilliant nor so uniform as that of the others, and it exhibited some dark streaks similar to those observed in other prominences. Its breadth amounted to 50 thirds. Finally, a small prominence made its appearance half a minute before the end of the totality, to the right of the chain of rose-colored peaks. It was perfectly detached, and bore a great resemblance to 3. The color of the prominences was described in very different terms by the various observers. It was designated by most of them as pale red, by some as scarlet, by others again as rose red or pale coral red, and by Tennant as white. Angle of an object seen upon the sun from the earth may be reckoned roundly at German geographical miles, and 1 minute of the arc of the sun's circumference as 122 miles. Chapter 52. The total solar eclipse of 7th August, 1869. August 1869. This eclipse was likewise invisible in Europe. The zone of totality stretched from Alaska, where the eclipse began at noon, over British America and the southwest corner of Minnesota, then crossed the Mississippi near Burlington, Iowa, and passed through Illinois, western Virginia, and North Carolina, reaching the Atlantic Ocean in the neighborhood of Beaufort. The event excited the most lively interest among astronomers and photographers throughout the whole of North America, and occasioned the equipment of a number of scientific expeditions, which were also supplemented by the valuable labors of many private individuals. The observers were in almost every instance favored with the finest weather, and their efforts were rewarded by a large collection of photographic pictures and many valuable spectroscopic and other observations. That portion of the zone of totality which traversed the inhabited parts of the United States was studied everywhere with telescopes, spectroscopes, and other instruments of observation, so that the whole of this tract of country became one vast observatory. Although the duration of totality was less than in the eclipse observed in India, yet the phenomenon was attended on the whole with many more favorable circumstances. The heat was less intense, the places suitable for observation were much more conveniently situated, and the sun's altitude was not so great as in the eclipse of 1868. The most important points of investigation had reference to the scrutiny of the prominences by means of photography and the spectroscope, the examination of the nature of the corona, and the search for planets between Mercury and the sun. The most complete expeditions were those sent out from Washington, one from the Nautical Almanac Office, the astronomical department being under the charge of Professor Coffin, while the photographic arrangements were conducted by Professor Henry Morton of Philadelphia. Another expedition was dispatched from the United States Naval Observatory, under the superintendence of Commodore B.F. Sands. The first expedition, under the guidance of Professor Morton, selected stations in the state of Iowa as follows: 1 Burlington, where the observers were Professor Mayer and Messrs. Kendall, Willard, Phillips, and Mahoney, together with Dr. C. A. Young, professor of Dartmouth College, Hanover, well known as an experienced spectroscopist, and Dr. B. A. Gould, to whose charge the photographic department was committed. 2 Ottawa, where Professor Himes and Messrs. P. Zentmeyer, Moling, Brown, and Baker were stationed. 3 Mount Pleasant, occupied by Professor Morton and Messrs. Wilson, Clifford, Creamer, Ranger, and Carbut, as well as by some other professors in eluding Pickering, who were desirous of making astronomical observations on the physical phenomena of the eclipse. Station selected by the second expedition. 1. Des Moines, Iowa, where Professor Newcomb undertook the observation of the corona and the search for intermercurial planets, Professor Harkness the spectroscopic investigations, and Professor Eastman the meteorological department. Several other gentlemen skilled in solar photography associated themselves with these observers. 2. Bristol, Tennessee, where Bard, who undertook the observation of the corona, and other observers were stationed. Besides these important expeditions furnished with the most admirable and complete means of observation, several scientific men were engaged at various points in the zone of totality, either in observing the astronomical details of the eclipse, or in investigating the prominences, the corona, and their spectra. Among these may be mentioned Dr. Edward Curtis, who at Des Moines obtained no fewer than 119 pictures of the different phases of the eclipse. Gilman, by whom some most valuable observations were instituted at St. Paul Junction, Iowa, upon the connection between the solar spots, the facles, and the prominences. J.A. Whipple, who with Professor Winlock and several assistants procured at Shelbyville, Kentucky, 80 photographic pictures, 6 of which were taken during the totality, one of them exhibiting a complete and magnificent corona, as well as Professor G. W. Huff, director of the Dudley Observatory, who in company with 9 fellow observers recorded all the details of the eclipse at Mattoon, Illinois. Out of the mass of materials afforded by the observations of this eclipse, it will only come within our province to communicate those results which have reference to the physical constitution of the sun, and were obtained partly by photographic delineation and partly by the help of the spectroscope. Here, as in section 51, the phenomena of the eclipse, as exhibited in the telescope and on the photographic plates, will first be described, while the details of the prominences and the corona revealed by the spectroscope will be deferred to a future page. The course of the eclipse and the photographic work carried on at Mount Pleasant, where the totality lasted 2 minutes. 48 seconds is described by Wilson nearly as follows. For some days prior to the eclipse, the sky was overcast and threatened rain, but the 7th of August was bright, without a cloud, such a day as had not occurred for months, and the sun shone with remarkable clearness and warmth. The moment of first contact arrived. The first plate was already placed in the tube. Professor Watson signaled to us the moment for exposure by a motion of the hand. The instantaneous shutter was opened and closed, and the first picture was taken. We thus commenced a series of pictures taken at intervals of 5 or 10 minutes till the commencement of totality, after which the series was continued on the reappearance of the sun till the termination of the eclipse. Darkness came on with the totality, but not the darkness of night. Still it rendered reading impossible. The amount of light upon the landscape was scarcely equal to that of bright moonlight, yet it was sufficient for us to pursue our work. An instant before the commencement of totality, the thin crescent of the sun was still quite dazzling. Then the light went out as from an expiring candle. There, between heaven and earth, hung face to face the 2 great luminaries, sun and moon. A large, black, round spot encircled by a brilliant ring of deep gold-colored light, interrupted here and there by the brighter spots of the flesh-colored prominences of irregular size and form, and surrounded by the magnificent corona, which shot out rays in every direction, faintest where the prominences were most conspicuous, but enveloping the whole with a glory which was marvelously beautiful, as if the Creator were about to show his omnipotence in this wonder. The phenomenon resembled a gigantic image from a magic lantern received upon the heavens as a screen. 4 plates were exposed when suddenly the full significance of those words was realized. Let there be light, and there was light, for a mighty flood of brilliant light gushed forth like the rushing, foaming waters of Niagara. The sun came forth like a conqueror from a battle with the Titans, and was greeted with acclamations by the assembled spectators. Total solar eclipse, JF, North America, 1869, August 7th. Burlmantori, Iowako, commencement of totality. Tune of exposure, sex, Burlington, Iowa, towards the end of totality. Tune of exposure, sex, the 3 pictures of the totality taken at Mount Pleasant were not remarkably sharp. As the telescope was not furnished with a clock movement, much better results were obtained by the observers stationed at Ottawa and Burlington. At Ottawa, 40 negatives were taken, 4 of which were during the totality. And of the 40 pictures obtained at Burlington, 6 were taken while the totality lasted, so that the expedition under Morton contributed 13 pictures of the totality, several of which were of great excellence. A picture of this magnificent spectacle has been already given in Figure 109, showing the prominences in corona after drawings made by Dr. Gould. The photographic plates, which were exposed for the brief space of from 5 to 16 seconds, give only faint traces of the corona, on account of its light being too weak to produce, in so short a time, any chemical action on the prepared plates. Photographic pictures taken at Burlington at the commencement of the totality and immediately before its termination. In the upper picture, the first prominences are just becoming visible on the eastern limb of the sun, while those on the western limb are still covered by the moon. By the further advance of the moon from west to east, the eastern prominences are shown in the lower picture to be gradually disappearing, while those to the west are being revealed with increasing distinctness, as they appeared on the sun's limb during the course of the totality, whether as single and isolated flames, or in less definite forms as widespread luminous masses, arranged according to the measures obtained and the estimations made of their angles of position, P321. The prominences are numbered from 1 to 12, beginning at north 7th August 1869, and passing by east and south to west. Among them, nose 4, 5, and 8 are especially remarkable from their form and height. Called the Eagle, rose to a height of 82 K, number 5, a nebulous cloud of flame extending from B to C, attained a height of 136, while number 8, compared to U, the head of an albatross, measured 75 in height, whence it may be calculated that the actual height of these prominences must have been respectively 37 0 miles, 6 0 miles, and 34 0 miles. In the photographic pictures, there was to be seen a glow of light of indefinite form, represented Figure 125 by an irregular dotted line, which extended from the point N towards the east, nearly as far as S, and attained a maximum elevation of 215, about halfway between the prominences 2 and 4, and again at a few degrees south of 5. In the vicinity of the prominences 3 and 5, near the points where the luminous appendage had attained its greatest elevation, several tongues of vivid flame, separated one from another, rose high above the lower portions of the mass of light. The white nebulous cloud of light between B and C attained a height of at least 64 miles. A similar luminous cloud was seen in the pictures along the western side, extending from south to north. It reached a maximum height between the prominences 11 and 12, and at the point was cut off almost perpendicularly. The dotted circle within the moon's edge shows the proportional size of the sun, as well as its position in the middle of totality. The arrow marks the direction of the moon's course, but the fact that the disks of the sun and moon were never perfectly concentric during the eclipse has not been disregarded in the drawing. In the photographic pictures, the bases of the prominences, with the exception of number 4, project within the circle formed by the moon's edge, as shown in Figure 125. The explanation of this remarkable phenomenon was thought to be found in the circumstance that the photographic telescope, by following the motion of the prominences by clockwork, kept their image immovable on the photographic plate, while the image of the moon, owing to its angular motion being different to that of the sun, continued to advance over the plate. Dr. Curtis, however, has strikingly shown by photographing from an artificial eclipse in which the moon was represented by black paper, notched for the prominences and corona, that this projection of the prominence images on the disk of the moon is caused by a kind of photographic irradiation on the prepared plate, and is therefore an entirely mechanical action which always occurs where an intensely bright object is in immediate contact with a dark one. And the duration of the action of the light, time of exposure, has exceeded the proper limit. The eclipse of 1868 observed in India, though furnishing so many valuable details concerning the prominences, was almost without results with respect to the corona. The various observers of the eclipse in America were all the more eager, therefore, to examine the details of this remarkable phenomenon, its form, its spectrum, and especially its connection with the prominences. The photographs of short exposure from 1 to 7 seconds show the corona only in its brightest parts close to the edge of the sun. Still, they give, especially those taken at Ottawa, a tolerably distinct image of it. With nearly the same form as it presented to the unassisted eye, the curved path of the rays, and the varying intensity with which they stream out from the different points, can be distinctly traced in these pictures. The most brilliant rays agree strikingly in a position with the light of those prominences which have the form of a pointed flame, while where the prominences resemble rounded masses, a shadow seems cast upon the corona. It is clearly evident from these pictures that the corona does not move along with the moon during the totality, but that it remains concentric with the sun. It becomes more and more covered at the eastern edge in proportion as the moon advances, and in the same proportion is gradually revealed on the opposite side, in order to obtain a complete photographic picture of the entire corona in all its parts. Not only must the time of exposure considerably exceed that requisite for the intensely bright prominences, but the image of the corona must not be magnified before falling on the photographic plate. J. A. Whipple of Boston accordingly arranged his telescope for photographing the corona at Shelbyville, Kentucky, in such a manner that the prepared plate was placed in the main focus of the object glass, and he employed 40 seconds as the time of exposure. In this way, a picture was obtained in which the prominences appeared only as bright spots, while the inner ring of light, as well as the outline of the whole corona, and the peculiar curve of its rays, are clearly shown. Figure 126 is an exact copy of this picture, with the exception that in the original, the light fades away more gradually, and the rays are not so sharply defined. When the corona is observed through a large telescope, only a small portion of it can be seen at once, and the instrument must be gradually turned photographic picture of the corona, 7th August, 1869, round the entire limb of the moon in order to obtain a general view of the whole. Professor Eastman, who instituted observations of this kind at Des Moines, has published 2 pictures of the corona, one of which, represented in figure 127, was taken at the commencement of the totality, and the other just before its termination. The instant the totality began, the corona made its appearance as a light of silvery whiteness, with an exceedingly tender flush of a greenish-violet hue at the extreme edges, and not the slightest change was perceptible during the totality in the color, the outline, or the position of the rays, an observation confirmed by Professor Huff at Mattoon, Illinois, by Gill, and by several others. The corona of the eclipse of 7th August, 1869, at Des Moines. The corona appeared to consist of 2 principal portions. The inner one, next to the sun, was nearly annular, reaching an elevation of about eye, and in color of a pure silvery whiteness. The outer portion consisted of rays, some of which grouped themselves into 5 star-like points, while the others assumed the appearance of radiations and were the most sharply defined. The corona was scarcely visible between the prominences A and B. The star-like rays attained a height equal to half the diameter of the sun. Gould's drawing of the corona of 7th August, 1869, 4:08 p.m. Dr. B.A. Gould observed the corona with the unassisted eye at Burlington and made 3 complete drawings of it during the totality at intervals of 1 minute. In figures 128 and 129, 2 of the pictures are given, one representing the corona at the commencement of the totality at 4:58, and the other at 5 each. These pictures by Gould appear to be opposed to the observations cited above, that the corona preserved the same appearance throughout the totality, inasmuch as they seem to show some Gould's drawing of the corona of 7th August. 1869, 5 Evidence of change. This observer therefore maintains that owing to the long exposure of 40 seconds, the sharp photographic picture, figure 126, does not represent the corona, but another luminous atmosphere of the sun, the chromosphere. Against this opinion of Gould's, it must first of all be remarked that it is not possible to draw a correct picture of the corona in all its details merely by the unassisted eye, without the aid of instruments of measurement, for which reason all the drawings of the various observers, made merely by the eye, differ one from the other, and from the photographs. Then again, the photographic picture taken by Whipple that has been alluded to cannot possibly represent the chromosphere, since this appendage of the sun, as will be seen further on, is not higher than Io for 450 miles. J, while the rays of light in the photograph attain a height of 10,277.0 miles, Dr. Curtis has, after a very complete and searching investigation, arrived at the conclusion that Gould's 3 drawings of the corona are not perfectly accurate, and that his views as to the variability of the corona and his explanation of Whipple's photograph cannot be justified, but that, on the contrary, the corona did not change its form during the whole period of total darkness, and that the photograph referred to could represent nothing else but the corona. Chapter 53. The prominences and their spectra in the total eclipse of the 18th of August, 1868. The spectrum of the prominences was observed by T. Victet. Whole question rests upon the meaning assigned to the word chromosphere. See note at the beginning of section 56, Tarshal et Jamkhandi, by Haig at Bijapur, by Tennant and Janssen at Guntur, by Rayet and Hall at Watan, and was found by these observers to consist of a few bright lines, from which they concluded that these forms are composed of luminous gases, of which hydrogen gas is the chief constituent. The spectrum of this gas is characterized, as is well known, by 3 bright lines, frontispiece number 7, of which the first, red, is coincident with the Fraunhofer line C. The second, greenish-blue, coincides with the line F, while the third, dark blue, lies in the vicinity of the line G. Comparison spectra number 1, the principal lines of the solar spectrum, and number 2, the principal lines of hydrogen gas, the spectra of the prominences, NOS 3, 4, 5, and 6, as observed by Rayet, Herschel, Tennant, and Lockyer. Rayet, who preferred to keep his direct vision spectroscope pointed exclusively to the great prominence, and employed the instrument in all positions, perceived 9 bright lines, consisting of those corresponding to the dark lines B, D, E, B, F, G, of a green line between B and F and a blue one near G, number 3. These lines appeared very bright upon the dark background, so that their position could be determined with ease. The bright lines D, E, F were seen in the inverting telescope of the spectroscope to be prolonged downwards below the rest, as finer and fainter lines, and were thus turned away from the sun's limb, a phenomenon which seems to indicate that a portion of the mass of glowing gas composing the prominent stretches solar spectrum. Prom. Spectrum Rayet. Prom. Spectrum Herschel. Prom spectrum Tennant. Prom spectrum Lockyer. New D inclines, Secchi and Lockyer, widening of the F lines. Prom spectrum Janssen, far upwards into the sun's atmosphere in a state of extreme rarefaction. Herschel, number 4, made use of a spectroscope specially constructed for these observations and for the measurement of the spectrum lines. At the first glance, the spectrum of the prominence appeared as a spectrum of 3 very brilliant lines, of which the orange line coincided with D, while the red line was not coincident with either B or C, nor did the blue line coincide with F. Tennant, number 5, employ a spectroscope similar to that used by Huggins in his investigations on the spectra of the nebulae and the fixed stars. The spectrum of the prominence appeared to him as a spectrum of 5 bright lines, 3 of which were in exact coincidence with C, D, and B, while the greenish-blue line lay very near to F, and the dark blue line near to G. Time did not allow of a more accurate measurement of these 2 doubtful lines, but from the observations of Rayet, it is almost certain that the first of them was actually coincident with F, and the other with the hydrogen line, H7, near to G. Janssen sent the first telegraphic announcement to Europe that the spectrum of the prominences consisted of bright lines, and that therefore these remarkable forms are enormous columns of luminous gas, of which hydrogen constitutes the chief element. In readiness for the observation, the slit was held close to the advancing limb of the moon, at a tangent to the point where the last rays of the sun would disappear. With the extinction of the last rays, 2 new spectra started suddenly into view, each consisting of 5 or 6 bright lines, figure 130, number 8, the lines were red, yellow, green, blue, and violet, and the two spectra, which were separated by a dark space, were exactly coincident line for line. When Janssen left the spectroscope to look for a moment through the finder or small telescope, he saw that both spectra belonged to two magnificent prominences, which shone out at the black edge of the moon to the right and left of the point where the last ray of sunlight had disappeared. One of these attained a height of 3, and resembled the flame of a furnace as it breaks forth vehemently under the influence of a powerful blast. The other presented the appearance of an extended chain of snow mountains, which seemed to rest on the moon's limb, and glowed as if illuminated by the red light of the setting sun. As the principal lines of the spectrum coincided with the Fraunhofer lines, C and S, Janssen declared at once that hydrogen gas forms an important element in the constitution of the prominences. From the circumstance that the space between the spectra of the two prominences was dark, Janssen was brought to the conclusion that the results of his investigations were not in accordance with Kirchhoff's theory. He imagined that the space between these prominences must have been filled with what Kirchhoff had assumed to be the solar atmosphere, and therefore that this space, instead of being dark in the spectroscope, ought to have yielded a spectrum of bright lines. As this was not the case, then Kirchhoff's theory that the white light of the solid or incandescent solar nucleus was partially absorbed by the glowing vapors of an atmosphere had become untenable. This absorption could not, therefore, have taken place outside the photosphere or light-giving portion of the sun, but necessarily within it, and had been produced by the glowing vapors from which the condensed solid or liquid particles of the cloud-like mass of the actual photosphere were formed. In reply to this objection of Janssen's, it may be remarked that, though he obtained no spectrum from the immediate neighborhood of the sun, it was to be attributed to the very narrow setting of the slit he employed, for the sake of seeing the bright lines of the prominences distinctly, which was too narrow to allow of a spectrum from the other, much fainter portions of the sun being received at the same time. Erzea, as well as Tennant, obtained indubitable, though faint spectra from the immediate neighborhood of the sun. Janssen's observations seem, therefore, only to strengthen the conclusion arrived at by the other observers, that the light of the prominences is much more intense than that of the solar atmosphere, even when in closest proximity to the sun's limb, or than the corona. If all the spectrum observations of the prominences made on the 18th of August, 1868, be collected together, and those of least importance be set aside, the following results are obtained. 1. The spectrum of the prominences consists of some bright lines of intense brilliancy, among which the hydrogen lines HA equals C, H, SS equals F and HY, near to G, are especially noticeable. 2. The prominences are masses of luminous gas, principally luminous hydrogen gas. They envelop the entire surface of the solar body, sometimes in a low stratum, extending over exceedingly large tracts of the sun's surface, sometimes in accumulated masses rising at certain localities to a height of more than 80 miles. In the eclipse of the 7th of August, 1869, observed in America, the spectra of the prominences were investigated by Professor Harkness at Des Moines, as well as by Professor Young at Burlington, who devoted himself with especial attention to this work. Professor Harkness employed an ordinary simple spectroscope consisting of a single prism of 60 degrees, to which had been added a micrometer in preparation for the eclipse. Owing to the small dispersive power of such an instrument, the measures taken of the distances between the lines of the spectrum, as compared with Kirchhoff's scale, can make no claim to great accuracy. Harkness compared the divisions of his micrometer by means of the principal Fraunhofer lines with the millimeter numbers of the same lines in Kirchhoff's map, and marked the bright lines seen in the prominences given in figure 127 by the following numbers of Kirchhoff's scale. Prominence gave approximately the lines 693, 10.7. 1497, Kirchhoff 353 prominence C gave approximately the lines. Prominence gave approximately the lines. Prominence gave approximately correct, if these readings, though only approximately correct, be compared with Kirchhoff's numbers for the most important of the Fraunhofer lines given in P236, it will be found that the bright lines observed in the prominences may very probably have been as follows. 694 equals 0. Ha! 1017 equals D. Beyond D2, 2080 equals F. Ish S 2796 equals H7, as well as the line 1474, and instead of 1497, less refrangible than E, whether an error had occurred in the measurement of the position of the green line, 1611, between E and B, or whether this line be identical with that observed by Winlock in the spectrum of the aurora borealis, marked 1680 in Huggins' scale, 1608 Kirchhoff, must still be left in doubt. According to these observations, therefore, it appears that the bright lines in the various prominences vary in number, but not in position, and that hydrogen gas is the principal constituent of the prominences. The observations and measurements made by Young were much more accurate and complete. He was provided with an instrument consisting of 5 prisms of 450 each, the lateral surfaces of 2 and 3 inches, and the method by which this compound spectroscope P was connected with the telescope A, a comet seeker of 4 inches aperture and 30 inches focus, is shown in figure 13.1. The collimator C was furnished with an adjustable slit 1/8 of an inch in length, through 1/2 of which the prism of comparison introduced into the instrument the light of any terrestrial substance rendered luminous in the electric spark, or of a Geissler's tube. By means of the conducting wires L, the platinum electrodes could be placed in connection with an induction coil. Immediately in front of the slit there was placed at S a divided disc, in the center of which was a circular opening 1/8 of an inch wide, a contrivance by means of which the image of the sun could be kept exactly on the slit, and any portion of the solar image directed upon it at will. The dispersive power of the 5 prisms amounted to 80 degrees between the lines A and H, and the total deviation for the D line nearly to 165 degrees. The prisms were so adjusted one with another, and the plate P carrying them secured to the telescope A in such a manner by the bolts BBB, that all lines occupying the middle of the field of view should be in the most advantageous position. The field of view included at the same time the lines D and E by means of the micrometer screw T. The telescope E turning upon a pivot could be directed upon any of the lines of the spectrum. The eyepiece was furnished with a micrometer. The solar spectrum appeared about 1 3/4 inches in width and 45 inches in length, and showed all the lines contained in Kirchhoff's map. The readings of the instrument, Fig. T32, had been compared with Kirchhoff's maps by repeated measurements at 42 intervals between the principal lines along the whole length of the spectrum from A to G. Before the commencement of totality, the slit 5 figure 132 was placed on the limb end of the sun, in a perpendicular direction to the tangent AC at that point, where, by the advance of the moon onto the sun's disk, in an inverting telescope at the left side, Spromhanseschi, the first contact would take place. With such an arrangement, the spectrum consists, as will be described more in detail hereafter, of 2 halves in juxtaposition, one of which is the very intense solar spectrum abed, and the other, the very faint spectrum, FEC, of the diffused atmospheric light, rendered extremely pale by the powerful dispersion of the light. Both spectra are crossed equally by the Fraunhofer lines as shown in Figure 133, where the portion of the spectrum between B and C is more fully represented. When the 1/2 of the slit happens to fall upon a prominence, the bright lines of the luminous gases in the prominence immediately appear upon the faint spectrum of the atmosphere, especially the hydrogen lines PTSEs, green upon S, and H7 blue near G, as well as the bright lines of the other incandescent substances that may be present in the prominence. Before the moon's entrance on the sun's disk, Young observed, as he directed the telescope upon the line C in the spectrum, a very bright red line M upon the dark spectrum of the sky, forming an exact prolongation of the dark line C of the solar spectrum, and evidence that at this spot the sun was surrounded by a stratum of luminous hydrogen, the height of which reckoned by the length of the line M, must have been from 50 to 12. Now it is evident that the moon in its approach to the sun must first pass over this stratum of hydrogen. The observer notices the entrance of the moon upon this stratum and her progress over it by the shortening of the bright red line M, and he is able to determine with great accuracy the moment of first contact of the moon and sun by noticing the time when this line disappeared completely. The same phenomenon may be observed if, instead of the line C, the F line be brought into the field of view, but the red line H is better suited for this observation than the greenish-blue line HSS. This plan of observation employed by Young had already been devised in theory by Faye, who had suggested this method as an accurate means of observing the first contact of the moon, Venus, or any other planet with the sun's lit. Shortly before the commencement of totality, the slit was directed onto the prominence marked D in figure 127, and the line C brought into the field of view. When the totality began, the red line HGY became exceedingly intense, but owing to the slight elevation of the prominence, it did not extend across the whole width of the spectrum. No bright lines were perceptible either between C and A or between C and D. Immediately beyond the second sodium line, D2, appeared the orange-colored line D3 on 10,175 of Kirchhoff's scale, which was followed immediately by two faint yellowish-green lines, estimated at 1250 plus 21 million, 350,000 Kirchhoff. The green line following at 1474 K was very bright, though fainter than C and D3. It crossed the whole breadth of the spectrum and remained visible without undergoing any change when the slit was turned from the prominence to the corona, while the line D3 disappeared. Proof was thus afforded that this line did not belong exclusively to the spectrum of the prominence, but also to that of the corona. Young is of opinion that the two preceding faint lines remained also unaffected, and therefore belonged equally to the spectrum of the corona, which was observed simultaneously with that of the prominence, while the slit was directed upon the prominence, E, figure 127. The magnesium lines B were not visible, so that no bright lines were perceived by Young at this part of the prominence spectrum. The greenish-blue line FHSS was truly splendid, wide at the base, and terminating above in a point. It was followed by a blue line at 2,602 plus 2. K, almost as bright as the green line 1474 by the third hydrogen line HY near G at 2,096 K. And finally, by the very distinct but much less bright hydrogen line HHS at 33,701 K. The 9 bright lines observed by Young in the spectrum of the prominences are given in their natural colors in plate 9, number 1s. Annexed to the solar spectrum according to Kirchhoff's scale, spectrum, arid spectrum of the commences during a total eclipse. Nina V3 TRF. Uz. Chromolioi pound, Corona Fat 06 F at AI Sirens. Hi, Mr. Brothers, DEC 22N1870, given above, and they afford an accurate representation of the spectrum of a prominence, as it appears during the totality of a solar eclipse. The upper half of the picture, that is to say the solar spectrum, is of course invisible at such a time, and in its stead a faint continuous spectrum, without a trace of any dark lines, belonging, without doubt, to the corona, appears to adjoin the spectrum of the prominence. If the bright prominence lines, as observed by Young, be tabulated in their order of succession from red to blue, they will be found to correspond with the following numbers of Kirchhoff's scale: 1017 to 5 UNGBR3, belonging neither to hydrogen nor sodium, 1350, plus apparently belonging to the corona, 274 7. 2602 plus 2, observed also by Captain Herschel between F and G during the eclipse of the 1868. The spectroscopic observations of the prominences during the eclipse of 1868, given in P 352, have been fully confirmed by the observations of 1869, when further results were obtained, the import of which will be more attentively considered in the following section. Chapter 54. The corona and its spectrum in the eclipse of 1868. The observers were too much occupied with the spectroscopic investigations of the prominences to pay any adequate attention to the examination of the corona. The few observations that were obtained, some of which were made by Zia at Aden and some by Tennant at Guntur, are in complete agreement as to the sudden disappearance of all the dark lines from the spectrum on the commencement of the totality, and as to the fact that the light of the corona gave only a faint continuous spectrum. Tennant admits that this spectrum might also have contained faint lines which he was unable to perceive, because in order to ensure seeing something, he had employed a rather wide opening of the slit, and consequently some of the lines may have run one into the other. The eclipse of 1869 has furnished many valuable details on the spectrum of the corona, throwing much light upon its nature and fully confirming the previous observations that its spectrum is free from dark lights. Pickering, Harkness, Young, and others are agreed that with the extinction of the last rays of the sun, all the Fraunhofer lines disappear at once from the spectrum. The small instruments employed by Pickering and Harkness, in which the field of view was large, exhibited a spectrum obtained at once from the corona, the prominences, and the sky in the neighborhood of the sun. These instruments showed during the totality a faint continuous spectrum free from dark lines, but crossed by 2 or 3 bright lines. Young, whose spectroscope consisted of 5 prisms, figure 13.1, observed the 3 bright lines in the spectrum of the corona, which are represented in Plate 9, number 2, where they are drawn in the colors in which they appeared according to Kirchhoff's millimeter scale, introduced above. These lines were 1250 plus 20, 1350 plus 20, and 1474. It has been already explained in P. 358 why the last and brightest of these lines is thought to belong to the spectrum of the corona, and not to that of the prominences, and it seems probable that the other 2 lines belong also to the light of the corona, from the fact that they are both wanting in the spectrum of the prominences when observed without an eclipse. But what invests these 3 lines with a peculiar interest is the circumstance that they appear to coincide exactly with the first 3 of the 5 bright lines observed by Professor Winlock in the spectrum of the aurora borealis, Plate 9. Number 3. These lines of the aurora were determined by Winlock according to Huygens' scale. If these numbers be reduced to Kirchhoff's scale, the position of the lines will be found to be 1247, 1351. And 1473, while the lines observed by Young were registered as 1250, 1350, and 1474. Now, if it be borne in mind that Young found the positions of the 2 fainter lines more by estimation than by measurement, the coincidence between the bright lines of the corona and those of the aurora borealis will be found to be very remarkable. The brightest of these lines, 1474, is the reversal of a strongly marked Fraunhofer line which has been ascribed both by Kirchhoff and Angstrom to the vapor of iron. What, then, is the nature of the corona, this magic circle of rays of silvery whiteness which surrounds like a halo the black disk of the moon at the time of a total eclipse and invests the whole phenomenon with an indescribable charm? It has been thought that while the inner bright circle of light closely surrounding the moon's limb belonged to the solar body itself, the rays streaming from the luminous ring were merely the rays of the sun reflected from the dark and uneven surface of the moon, and brought by a sort of refraction into the earth's atmosphere, whence they were reflected to the eye of the observer. In opposition to this theory is the fact that, whereas the halo ought then to pass through great changes by the advance of the moon during the totality, no such changes were noticed by any of the observers, Gould excepted, nor were they to be traced in any of the photographs taken during the totality. In addition, it would not be difficult to prove geometrically that none of such rays as might be reflected from the moon's limb could possibly reach the small totality. The light of the corona cannot be that of reflected sunlight, since none of the dark Fraunhofer lines are contained in its spectrum. A comparison of several of the photographic pictures leads further to the conclusion that in proportion as the moon advanced, the corona around the eastern limb of the sun became gradually covered, while on the west, it was more and more revealed. The ring of light did not therefore move with the moon, but remain invariable during the whole of the totality. If it be also taken into consideration that, as shown by the careful investigations of Professor Pickering, the light of the whole surrounding sky almost up to the edge of the corona was polarized, while that from the corona itself was not polarized, the conclusion will be arrived at that the corona is self-luminous and belongs to the sun, and therefore is not to be regarded as an optical phenomenon caused by the combined action of the sun's rays, the moon, and the Earth's atmosphere. From the bright lines in its spectrum, it is probably of a gaseous nature, and forms a widely diffused atmosphere around the sun. If this were the case, even its most remote particles would be 100 times nearer the sun than the Earth is, and would therefore receive 10,000 times the amount of heat. Such a temperature would suffice to resolve every known substance of our planet, either into a state of incandescence or into a gaseous form. It has been supposed, from the coincidence of the three bright lines of the corona with those of the aurora borealis, that the corona is a permanent polar light existing in the sun analogous to that of our Earth. Lockyer, however, justly urges against this theory the fact that although the brightest of these three lines, which is due to the vapor of iron, is very often present among the great number of bright lines occasionally seen in the spectrum of the prominences, it is by no means constantly visible, which ought to be the case were the corona a permanent polar light in the sun. A yet bolder theory is the ascription of such a polar light in the sun to the influence of electricity, which has been proved, as is well known, by the agitation of the magnetic needle and the disturbance of the electric current in the telegraph wires, to play an important part in the phenomena of the aurora borealis. In the present state of our knowledge on this branch of science, the question as to the nature of the corona still remains unanswered. The solution of this problem must be reserved till, by the careful observation of future total eclipses, fresh data shall be collected which may either confirm the theories already received, or else suggest new ones in their stead, appear to the Council an occasion on which they should take steps to assist observers, and, if necessary, organize an expedition provided with suitable instruments for attacking the important problem which still remained unsolved, the extent and nature of the coronal light. At the meeting of the Council held in March, the Council resolved itself into a committee to consider the preparations to be made for the observation of the solar eclipse of DQ. In the following month, this committee united itself with a committee appointed for AE and held by this joint committee on June 16. It was resolved that the government be solicited to grant 2 ships for conveyance of observers to Spain and Sicily, and also a sum of money for the preparation and transport of instruments. To this application, which was made in accordance with former usage, to the Admiralty an unfavorable answer was received on August 10. Absence from town of some members of the Joint Committee and other circumstances prevented any further steps being taken until November 4, when the Joint Committee met and resolved that an application for means of transit for the expedition and for a pecuniary grant in aid of the funds voted by the Royal and Royal Astronomical Societies should be made to the Lords Commissioners of Her Majesty's Treasury. To this renewed application, a favorable reply was returned by the government, who placed H.M. Troop Ship Urgent at the service of the expedition for the conveyance of observers and instruments to Spain and Africa, and the sum of EA20 in aid of the traveling expenses of the overland party to Sicily, and for the preparation and transport of instruments. At this late moment, a few weeks only before the expedition should leave England, the greatest energy was needed to organize a party of observers and procure the special instruments needed for the proposed observations. A small organizing committee was appointed, which met almost daily up to the departure of the expedition. The successful and very complete arrangements ultimately made were due in great measure to the unflagging zeal of the Secretary, Mr. Lockyer, and of the Assistant Secretary, Mr. Ranier, and the Council wish here to state how much, in their opinion, is owing to the valuable suggestions and assistance afforded by Professor Stokes. The opticians, Mr. Browning, Mr. Grubb, Mr. Ladd, and Mr. Slater, afforded very valuable assistance to the expedition by the preparation and loan of instruments, for which they deserve the grateful thanks of the Society. distinct observing parties in charge of Mr. Lockyer, Reverend S.J. Perry, Captain Parsons, and Mr. Huggins, were appointed for the 4 stations, Sicily, Cadiz, Gibraltar, and Oran. Professor Tyndall accompanied the Oran party as an independent observer, Lord Lindsay taking with him several skilled observers and a very complete photographic apparatus, went to Cadiz independently at his own expense. Besides these English expeditions, there was an American expedition with Professor Pierce at its head, consisting of 2 parties, one in Sicily, under Professor Pierce himself, and one in Spain, under Professor Winlock. Independent observations were taken by Professor Newcomb at Gibraltar, and by a party consisting of Profs. Hall, Eastman, and Harkness in Sicily. At no former eclipse have preparations been made on so complete a scale, or the work to be done so skillfully divided among observers trained to carry out efficiently the parts assigned to them. All the parties were prepared to attack the corona by the several methods of the spectroscope, the polariscope, photography, and eye drawings. With favorable weather, it was not too much to expect from these expeditions a searching and almost exhaustive examination of the coronal light by these different methods of attack. The weather was not propitious. At all the stations, the sky was more or less obscured by clouds. On the African continent, where there had been grounds for confidently anticipating a cloudless sky, the English party and M. Janssen, who had escaped with his instruments from Paris in a balloon, at Oran, and Doctors Weiss and Opposer at Tunis, saw nothing of the eclipse at the time of totality, though the earlier phases were visible at Oran. At Cadiz and in Sicily, successful photographs of the totality were obtained by Lord Lindsay, Mr. Willard, of the American expedition, and Mr. Brothers. At these stations, and also at Estepona, some observations were obtained of the spectrum and polarization of the corona. Although the gain to our knowledge of solar physics is much less full and decided than doubtless it would have been if the observers had been favored with a cloudless sky. The new information which comes to us from the eclipse is very valuable, and well repays the large amount of thought, time, and money which were so freely bestowed upon the preparations. The present time is too early for a complete analysis of the different observations, with a view to eliciting from them the new teaching which they may contain of the extent and nature of the coronal light. Still, it may not be undesirable to give a short account of some of the more important observations. In the last annual report, in the account of the eclipse of August 1869, attention was called to the 2 apparently distinct portions besides the prominences in the light seen round the moon during totality. The American pictures showed similar indications of brighter portions near the sun's limb, within which the eruptions of hydrogen forming the prominences take place, to those which were visible in the photographs taken by Mr. de la Rue in I and by Colonel Tennant and Dr. Vogel in 1868. A distinction between different portions of the coronal light was observed as early as 1706 by M. E. Planté and Capes at Montpellier. As soon as the sun was eclipsed, there appeared around the moon a very white light forming a corona, the breadth of which was equal to about 3. Within these limits, the light was everywhere equally vivid. But beyond the exterior contour, it was less intense, and was seen to fade off gradually into the surrounding darkness, forming an annulus around the moon of about 8 in diameter, in 1842 mm. Arago considered this distinction to be sufficiently marked to sanction the subdivision of the corona into 2 concentric zones, the inner zone equally bright and well-defined at the outer border, while the exterior zone gradually diminished in brightness until it was lost in the surrounding darkness. The observations of the eclipse of last December confirmed these earlier descriptions as to the apparent subdivision of the coronal light, though the breadth of the inner zone varies considerably as described by different observers. In our future remarks, we shall restrict the word corona to the inner brighter ring, and for the faint exterior portion use the term halo. It may conduce to clearness in our interpretation of those observations which appear to differ from each other. If we consider that the imperfect transparency of our atmosphere must cause a scattering of a portion of the light of the corona seen through it, and form a more or less brightly illuminated screen between the eye and the eclipsed sun. This atmospheric light will interfere especially with the observer's appreciation of the form and extent of the faint halo. There may exist at least 3 distinct sources of the light seen about the sun, in addition to the prominences of the corona: a solar halo overlapping the corona or beginning at its exterior limit, and an atmospheric halo produced by the scattering of the light by our atmosphere. The corona and solar halo would probably not alter greatly in the short time between observations of the same eclipse at different stations, but the scattering of light would be peculiar to each station, and be mixed up with the effect of haze or light cloud present at the time. It is possible that without the Earth's atmosphere, some scattering of light may arise from the imperfect transparency of interplanetary space, not to speak of the possible existence of finely divided matter more densely aggregated in the neighborhood of the sun. It may be that in these and some other considerations will be found the key to the interpretation of the widely different descriptions of the solar surroundings which come to us from different observers. Professor Watson, observing at Carlentini, describes a bright corona about 5 high. Observations at Cadiz give a breadth of about 3. Brown, observing with Lord Lindsay, found the inner zone, which he saw defined in its outer margin, to vary from 2 to 5 in breadth. Mr. Abbott at Gibraltar at about 5 high. Some of the observers described the exterior contour of the corona to be affected by the prominences bulging out over the loftiest of these. In the photographs, a defined zone is also seen in Lord Lindsay's photographs and the one taken by Mr. Willard. It extends rather more than I. In the photograph by Mr. Brothers, the height of the brighter zone varies from 3 to 5. 44. We will now speak of the photographs of the totality, which are very instructive. 44. The photographs taken at Cadiz by Lord Lindsay were obtained by placing the sensitive surface at the focus of a silvered glass mirror 12 inches in diameter and 6 feet focal length, giving an image of the sun about 3/4 of an inch in diameter. The other photograph, taken near Cadiz by Mr. Willard of the American expedition, was obtained at the focus of an achromatic object glass of 6 inches diameter, specially corrected for actinic rays. 44. Mr. Brothers at Syracuse employed a photographic object glass of 30 inches focal length and 4 inches diameter, lent to him by the maker, Mr. Dallmeyer. This lens gave a brilliant image of the sun about 3/10 of an inch in diameter, which was received upon a plate 5 inches square. The camera was mounted on the Sheepshanks Equatorial, belonging to the Society. 44. The photograph taken at the commencement of totality by Lord Lindsay had an exposure of 20 seconds. It shows around the moon's advancing limb a bright corona extending about T from the moon's limb, in which the prominences are distinctly marked, and outside this a halo of faint light diminishing rapidly in brilliancy, with indications of a radial structure which can be traced as far as 15 from the moon's limb. On the other side of the moon, where it overlaps the sun sufficiently to conceal the prominences and the bright corona, the halo is almost absent. It may be suggested that such portion of the halo as appears around the advancing limb of the moon has its origin on this side of the moon. As a pure speculation, the explanation may perhaps be hazarded that the true solar halo, as some spectroscopic observations would suggest, was less powerfully actinic than the scattered light of the prominences and corona, in which the halo on the one side of the moon, only as seen on the plate, may have its origin. The photograph taken by Mr. Willard was exposed during a minute and a half, and therefore must contain mixed up several successive appearances. The prominences are distinctly shown, and a defined corona of rather more than T in height. In the halo, there are indications of portions of unequal brightness and a radial structure, but the most remarkable feature is a V-shaped rift or dark space in the halo on the southeast, beginning from the outer boundary of the bright corona. A second, similar dark space is faintly traceable on the south. The same dark gaps are also recorded in an eye sketch by Lute. Brown, similar dark rifts are also shown in Mr. Brothers' photograph taken at Syracuse, a representation of which is given in is very valuable since it shows the halo extending towards the northwest, about 2 diameters at the moon, and on the east and south, about 1 diameter. The halo, therefore, is not concentric with either the sun or moon, but extends to the greatest distance in the direction from which the moon is moving. It shows in many parts traces of a radial structure. The stronger light about the moon is much broader on the west and northwest, and assumes a somewhat stellate appearance, with rays gradually softening down as if combed out into the fainter halo. This photograph was taken in 8 seconds, from the 93rd to the 101st second after the commencement of totality, and therefore presents a true representation of the different phenomena at the time, that is, as regards their relative actinic power, which may possibly differ in a sensible degree from the relative brightness they present to the eye. The eye sketches made at different stations show remarkable differences, especially in the form of the outer part of the halo. Some represent it as consisting all that taken by Mr. Brothers leave little doubt of the absolute agreement in position of these dark rifts or gaps. Professor Young remarks that this be so, it certainly bears very strongly in favor of those theories which assign a purely solar origin to the whole phenomena. Separate rays, others give to it an almost true geometrical contour. In some of the Spanish sketches, a tendency to assume a roughly quadrangular form can be detected, while in most of the Sicilian drawings there is a tendency to an angular form. Professor Winlock, using a spectroscope of 2 prisms on a 5.5-inch achromatic, found a faint continuous spectrum of the bright lines. The most persistent was 1474 Kirchhoff. This bright line and the continuous spectrum without dark lines were followed from the sun to at least 20 from his disk. Professor Young estimates the least extension of this line to a solar radius. Captain McClure, observing with a direct vision spectroscope attached to a 4-inch telescope, saw a faint continuous spectrum and bright lines in positions about C, D, and F to a distance of 8 from the moon's limb, and also the same lines, but much fainter, on the moon's disk. This observation would seem to show, as has been already suggested, that some of the light from the true surroundings of the sun is scattered by sieving some medium between the eye and the moon, and therefore the distance from the moon to which these lines can be traced does not imply necessarily an equally great extension of the true halo. Lute Brown of Lord Lindsay's party saw only a continuous spectrum without bright lines from 4 to 25 from the moon's limb. Mr. Cartmale Paunawashi, solar prominence observed by Zollner, 1869. Orffs 29, Piohas, 3 degrees, and degrees 1. Tim and Ika 1 to 22 on an Alpshimayas, Ayopu, and degrees 2. Time on Ek 20 VP 1 and 540. Up to the NC degrees 0, 3 point consia. Saksh 8 Cebu 6. 991 Orioaki. PIQ Echuino Ajajuo. Observing at Estepona, saw 3 bright lines in the spectrum of the corona. He considers the one in green to correspond with 1359 Kirchhoff. The observations with the polariscope show that a portion of the coronal light is polarized. And though the result as to the plane of polarization are interpreted differently by different observers, there seems reason to suppose with Mr. Ranyard and Mr. Pierce that the light is polarized radially, showing that the corona and halo may possibly reflect solar light as well as emit light of their own. There is one observation made by Professor Young which is of so much importance that it will be well to give an account of it in Professor Langley's words, with the slit of his spectroscope placed longitudinally at the moment of obscuration, and for 1 or 2 seconds later, the field of the instrument was filled with bright lines. As far as could be judged, during this brief interval, every non-atmospheric line of the solar spectrum showed bright. An interesting observation confirmed by Mr. Pye, a young gentleman whose voluntary aid proved of much service. From the concurrence of these independent observations, we seem to be justified in assuming the probable existence of an envelope surrounding the photosphere and beneath the chromosphere, usually so called, whose thickness must be limited to 2 or 3 seconds of arc, and which gives a discontinuous spectrum consisting of all or nearly all the Fraunhofer lines showing them, that is, bright on a dark ground, rapid and imperfect, as this early sketch must necessarily be of the observations of the last eclipse. It shows a distinct and important gain to our knowledge of solar physics. Professor Young considers it to be shown by the observations of this eclipse that one important element of the corona consists in a solar envelope of glowing gas reaching to a considerable elevation, at least to 8 or IO on the average, with occasional prolongations of double that extent, and it may turn out to have no upper limit whatever. He states, there was an important difference between the behavior of the hydrogen line and that of 1474. At the edge of the chromosphere, there was a sudden and very great falling off in the brightness of the form. While no such boundary was observed for the latter, the line grew regularly and continuously more faint as the distance from the sun increased, until it simply faded out. Professor Young says, I have no hesitation in affirming that the corona, as it appeared to me in December, was a very different phenomenon from what I saw the year before, and far more complex. He considers the spectrum of the corona to consist of at least 4 superposed elements. 1. A continuous spectrum without lines, either bright or dark, due to incandescent dust, that is, particles of solid or liquid meteoric matter near the sun. 2. A true gaseous spectrum consisting of 1 or more bright lines which may arise from the vapor of the meteoric dust, but more probably from a solar atmosphere through which the meteoric particles move. 3. A true sunlight spectrum with its dark lines, formed by photospheric light reflected from the solar atmosphere and meteoric dust. To this reflected sunlight undoubtedly is due most of the polarization. 4. Another component spectrum is due to the light reflected from the particles of our own atmosphere. This is a mixture of the 3 already named, with the addition of the chromosphere spectrum. For while at the middle of the eclipse, the air is wholly shielded from photospheric sunlight, it is of course exposed to illumination from the prominences and upper portions of the chromosphere. If there should be between us and the moon at the moment of eclipse any cloud of cosmical dust, the light reflected by this cloud would come in as a 5th element. Mr. Proctor, Monthly Notices, Vol 21, p. 184, considers that we have evidence of vertical disturbance with reference to the sun's globe in the objects which surround the sun, and that these are not of the nature of concentric atmospheric shells. The observations, he remarks, of Zollner and Respighi show that the prominences as respects their first formation are phenomena of eruption. The velocity with which the gaseous matter of the prominences must pass the photosphere must be in many cases at least 200 miles per second, and its initial velocity probably not less than 300 miles per second. Dense gaseous matter flung out with the hydrogen would probably retain a velocity of, say, 240 miles per second and reach a height exceed that indicated by the greatest extension of the radiations observed last December. From an examination of the original negative taken by Mr. Brothers, Mr. Proctor considers that this photograph favors the view that the coronal radiations are phenomena of eruption. Chapter 55. The telespectroscope and method of observing the spectra of the prominences in sunshine, serving the spectra of the prominences in sunshine. As early as October 1866, Mr. J. Norman Lockyer observing the spectrum of the solar prominences at any time when the sun was visible. But his labors were unproductive. Owing to the insufficient dispersive power of his instrument, it does not seem that Janssen was aware of Lockyer's suggestion in 1866. Or that he had seen the following description of the SO1 RP Roin on CSBSE. The AN as a position are reckonal all high Respaplian 1870. 50 to 360, north round by east. In observing the solar eclipse of August 1868, Janssen was surprised by the remarkable brilliancy of the prominence lines, and exclaimed as the sun reappeared and the prominences faded away, Je reverrai ces lignes-là en dehors des eclipses. Clouds prevented him carrying out his intention on that day. But on the 19th of August, he was up by daybreak to await the rising of the sun. And scarcely had the orb of day risen in full splendor above the horizon, than he succeeded in seeing the spectrum of the prominences with perfect distinctness. The phenomena of the previous day had completely changed their character. The distribution of the masses of gas round the sun's edge was entirely different, and of the great prominence scarcely a trace remained. For 17 consecutive days, Janssen continued to observe and make drawings of the prominences, by which it was proved that these gaseous masses changed their form and position. Experiments of Huygens, published some 6 months before the eclipse, February 1868, in the monthly notices of the Royal Astronomical Society of Hawaii. 88. During the last 2 years, Mr. Huygens has made numerous observations for the purpose of obtaining a view of the red prominences seen during a solar eclipse. The invisibility of these objects at ordinary times is supposed to arise from the illumination of our atmosphere. If these bodies are gaseous, their spectra would consist of bright lines. With a powerful spectroscope, the light scattered by our atmosphere near the sun's edge would be greatly reduced in intensity by the dispersion of the prisms, while the bright lines of the prominences, if such be present, would remain but little diminished in brilliancy. This principle has been carried out by various forms of prismatic apparatus, and also by other contrivances, but hitherto without success. 38 degrees with extraordinary rapidity. Janssen's paper communicating his discovery to the French Minister of Education is dated from Cacanada, the 19th of September. Lockyer, in the meantime, had caused some improvements to be made in his instrument, and only received it again into his possession on the 16th of October, 1868, long after the news of Janssen's discovery had reached Europe. On the 20th of October, the telespectroscope sent was sufficiently in order to allow of its being employed for observation. And on the same day, Lockyer wrote, "In a communication I have this morning perfectly succeeded in obtaining and observing part of the spectrum of a solar prominence. As a result, I have established the existence of 3 bright lines in the following positions, figure 130, number 6. 1 absolute coincident with C2, nearly coincident with F3. Near D, this third line, near D, always a very fine line, is more refrangible by 9 or 10 degrees of Kirchhoff's scale than the most refrangible the 2 lines. That is to say, it lies nearer to the green, and is designated D. In a subsequent communication to Mr. Warren de la Rue, Lockyer states that the prominences are merely local aggregations of a luminous gaseous medium, which entirely envelopes the sun, and that the characteristic spectrum of the prominences could be obtained on all sides of the sun. He estimates the thickness of this gaseous envelope to be about 0 miles, and remarks that the pure spectrum of a prominence consists of short bright lines, but that if the slit of the instrument be directed on to the limb N of the sun, as already explained in figure 132, and kept perpendicular to the tangent C of this spot, a narrow stripe abed of the solar spectrum will be seen fringed by the faint spectrum at EFC of the air and the prominence. As in this way, the bright lines of the prominence are so closely joined to the sketch of a prominence by means of its spectrum lines. Solar spectrum as to form prolongations of the Fraunhofer lines. It is easy to ascertain with great accuracy which of the lines coincide with the Fraunhofer lines, and which do not. If the spectroscope be directed according to this method to the extreme edge of the sun, and the slit carried round the sun, the spectrum of the prominences will be immediately recognized. And as the lines appear only where an accumulation of hydrogen is present, from the greater or less length of these bright lines, a drawing of the form and position of the prominence is round. The sun may be made with almost the same accuracy as during an eclipse. A prominence thus observed and sketched by Lockyer is shown in figure 134. As the length of the bright lines depends upon the height of the prominence upon which the slit of the spectroscope is directed, and these lines appear only in the field of the instrument when the light of the luminous gas falls into the slit. It is easy to see that attention need only be directed to one of these bright lines, the bluish-green F line for instance, in order to determine the form of a prominence. If such a line be observed to be of some length, a prominence is then in view. And if the slit be turned slowly to the right and to the left, the line will lengthen or shorten, according as the prominence is higher or lower. It will also appear interrupted, divided, or is at the point isolated from the solar spectrum, according as the prominence itself is interrupted or separated from the sun's limb. Lockyer was undoubtedly the first to suggest the possibility of observing the spectrum of the prominences in ordinary sunlight. and to furnish a method for the purpose, Janssen was the first to accomplish the fact. Under such circumstances, it is needless to discuss to whom the priority of this important discovery is due. The fame connected with it is sufficiently great to be shared by these two observers. The possibility of observing the lines of the prominences in bright sunshine lies in the difference between the spectrum of the solar light and that of the prominences. While the former is continuous, crossed with the dark lines, the latter consists merely of a few bright lines. If both spectra be formed in the spectroscope at the same time, the intense brightness of the continuous spectrum will in an ordinary instrument completely overpower the one consisting of lines and prevent its being visible. It has, however, been shown, p. 234, that by increasing the number of prisms, the spectrum may be greatly extended, whereby the continuous spectrum becomes considerably diminished in intensity, and may indeed, by the use of a sufficient number of prisms, be rendered almost invisible. The light of the prominences, on the contrary, consists of very few colors, which, though becoming further separated one from another by the increased dispersion of the light, are yet merely displaced, and do not suffer any very perceptible loss of light, but remain still visible in the spectroscope as very bright lights. It therefore follows that by the use of a spectroscope of highly dispersive power, the dazzling light of the sun is modified, while the lines of the prominences retaining their intensity may be observed even on the disk of the sun. The greater, therefore, the dispersive power of the instrument, the brighter will the colored lines of the prominences appear to be. It was on these considerations that Lockyer based his plan of observing the spectra of the prominences in full sunlight by means of a telespectroscope, figure 135. For this purpose, the slit of a highly dispersive spectroscope, DCA, firmly attached by the rods up to an equatorially mounted telescope, LTPT, driven by clockwork, is directed perpendicularly on to the edge of the sun's image formed in the telescope by moving the 2B of the spectroscope from end to end of the spectrum and setting the focus each time. The bright lines of the prominences may be seen as prolongations of the dark lines of the spectrum of the sun's disk on a background of the exceedingly faint spectrum of the Earth's atmosphere. In the picture, S is the finder GA handle for moving the telescope in declination, D the tube containing the slit, HA small telescope for reading the divisions on the micrometer screw head, partly concealed by the rod, AA. The telescope, an excellent refractor of 6 inches aperture and 98 inches focal length, is driven by clockwork. The spectroscope, constructed by Browning with his well-known ability, is represented on an enlarged scale in figure 136. The eyepiece is separated from the telescope, and the small image of the sun is therefore formed beyond the tube of the telescope, and can, if necessary, be easily received upon a screen. The slit of the collimator D is fixed precisely on the edge of this image, and the small telescope E so far turned round the pivot M by the driving screw N as to bring the dark line C, or F, of the solar spectrum into the middle of the field of view. The adjustment of the spectroscope to the telescope allows of the slit being brought either radially or tangentially onto any part of the sun's limb as required. The system of prisms C consists of 7 prisms of dense flint glass, of 450 each, and possesses a refracting angle of more than 300 degrees, when a still greater dispersion is needed. Lockyer employs an 8th prism of 60 degrees, and in some special cases even makes use in addition of a system of direct vision prisms, which is introduced into the telescope tube E more clearly. This method of observing the prominences S represents the solar image as formed by the object glass of the telescope, PP the image of the immediate neighborhood of the sun, which is rendered invisible owing to the overpowering light of day. The slit SS is placed perpendicularly to the sun's limb, and is therefore in the direction of the sun's radius, so that one half falls on the sun's disk, while the other half extends beyond it onto the surrounding envelope of glowing hydrogen, the prominences. In spectrum 1, which is still bright, though very much weakened by the great dispersion of the light, the Fraunhofer lines are very strongly marked. The other half of the field of view contains the spectrum of the air 233, which is extremely faint, and which, by a sufficient increase in the number of prisms, may be very nearly extinguished. The spectrum 2 of the prominence stratum PP appears upon this spectrum in immediate contact with the spectrum 1 of the sun's disk, and it has been found by observation that spectrum 2 consists of several bright lines, among which the hydrogen lines are at all times particularly brilliant, of which HELA red forms the exact prolongation of C, HSS greenish-blue accurate prolongation of F, and HY, blue less refrangible than G, not represented in the drawing. There's also to be seen the line as yet unknown D3, immediately following the sodium line, D. In plate 9, number 4, is represented the spectrum of the sun, and that of its immediate neighborhood, as it usually appears in a large telespectroscope with a radial slit. In the latter spectrum, besides the 4 bright lines of luminous hydrogen, other bright lines are generally visible, being the reversal of the Fraunhofer lines. Among these, the yellow line D3 beyond D is usually present, and frequently a green line due to iron. 1475, Kirchhoff, besides the 3 magnesium line 6. And according to an observation by Rayet, the 2 sodium lines done and D2 towards it. From the circumstance of the spectrum of the prominences as well as that of the gaseous stratum PP immediately surrounding the sun, being composed of colored lines, Lockyer has given to this gaseous envelope the name of chromosphere. The slit may also be placed in a position tangential to the sun's limb, as at St. Figure 137. And the light admitted either exclusively from the immediate neighborhood of the sun, namely from the chromosphere, or else in conjunction with that from the extreme edge of the sun. Instead of examining the direct image of the sun as formed by the object glass, a magnified image may be obtained by drawing out the eyepiece of the telescope and directing the slit onto this enlarged image. The telespectroscope employed by Professor Young, Figure 13.1, is essentially of the same construction as that just described used by Lockyer. Merz, the celebrated optician of Munich, constructs direct vision spectroscopes of great dispersive power for the spectroscopic observation of the prominences. They afford the advantage of viewing directly the object to be observed, as for instance the sun's limb, a prominence, or a spot, and are introduced into the telescope in place of the eyepiece. Figure 138 shows the interior construction of such a spectroscope. The system of prisms P has a dispersive power from D to H equals 8 degrees. The collimating lens is placed at C. One half of the slit 5, adjustable by the screw S, is covered by the reflecting prism, R, which receives the light used for comparison, whether that of a flame or a Geissler's tube. From the side, opposite to that where the screw S is placed, L is a cylindrical lens employed for stellar observations, but withdrawn for observations on the sun. The telescope F, of which the object glasses have a focal length of 4 inches, and an aperture of 7 lines, is provided with the positive eyepiece O of 1 inch, and furnished with a micrometer of points mm, with the necessary delicate adjustments. By means of the screw G, the tube F, under pressure of the opposing spring, can be so far turned towards either side as to be fixed on any part of the spectrum from the extreme red to the violet. In this form, the instrument acts as an ordinary highly dispersive spectroscope, particularly when it is screwed into the place of the eyepiece of a telescope in order to observe the spectrum of a faint object, such as the moon, the planet, or the brightest of the fixed stars, when the instrument is required for the observation of the solar prominences. Its dispersive power must be doubled by the introduction of a second direct vision system of prisms similar to that marked P between the collimating lens C and the first system of prisms. In this compound form, the instrument shows very distinctly in a clear atmosphere the fine nickel line between the 2 sodium lines DJ and D. To assist in directing the instrument onto any part of the sun's limb, a divided position circle is attached within the tube at the part where it is screwed on to the telescope, according to Cartmel. One of Browning's direct vision system of 7 prisms similar to that contained in the spectroscope described in page 119, suffices when combined with the 2-inch object glass of a good telescope to show in sunlight the two bright prominence lines, HA and HSS, when the instrument is so mounted as to be turned with convenience onto the sun. A blue glass is placed before the slit so as to exclude all but blue light from the spectroscope. When the image of the sun formed within the telescope passes over the slit, and the slit is placed in the right position, the bright greenish-blue line, HSS, will be seen as a prolongation of the F line of the solar spectrum. By substituting red glass for blue, the red line HA will be seen in a similar manner as the prolongation of the line C. Immediately upon the arrival of the news by telegraph of Jansen's discovery, Secchi, at Rome, began a series of spectrum investigations of the prominences. He employed a spectroscope of two excellent flint glass prisms of highly dispersive power, capable of showing the fine Fraunhofer lines situated between B and A, and placed it in combination with an excellent equatorial. Even on the first attempt, as the narrow slit was fixed on the sun's limb, the lines C and F were observed to be reversed in the spectrum of the air, and appeared therefore as bright lines. Secchi then carried the slit completely round the disk of the sun, placing it alternately in a direction parallel and perpendicular to the sun's limb. He observed that the bright line C, red, was everywhere visible. With the slit in a position perpendicular to the sun's limb, this line was always from 10 to 15 in length, excepting in a zone of 450 on each side of the equator. In this region, where the solar spots and faculae are known to abound, this line was 4 times its ordinary length. In many places, the C line was separated from the sun's limb, when the slit was placed at a tangent to the limb. This line always appeared as a bright line crossing the entire spectrum, and sometimes was cut up in single pieces when the slit was removed from the sun's limb, but always appeared complete and unbroken when the slit was again brought in contact with the limb of the sun. This proves what the observations of solar eclipses and the researches of Lockyer had already shown, that the stratum of glowing gas, the chromosphere, surrounding the sun is really continuous, though distributed very unevenly. Where a bright line attains the height of 60 or more in the spectrum, it proclaims the existence of a prominence in that place, and where a bright line is broken into fragments, it is an indication of the presence of isolated masses of glowing gas, of solar clouds at a considerable height above the sun's surface. Chapter 56. The chromosphere and its spectrum, by the term chromosphere, is designated that luminous gaseous envelope by which the sun is entirely surrounded. As already mentioned, its spectrum consists of a number of bright lines. Professor Young writes, one important element of the corona consists in a solar envelope of glowing gas reaching to a considerable elevation. For this envelope, the name of leucosphere has been proposed. It seems a suitable term and well worthy of adoption. It has been objected to on the ground that chromosphere covers the whole bright line region around the sun. But when the latter name was first proposed, there was evidently no idea that above the envelope of hydrogen there lay another from 20 to 100 times as extensive, and it would be very convenient to restrict it to the lower hydrogen stratum, and retain the new term for the more elevated mass of gaseous matter. Mr. Proctor suggests that the relation between the prominences and the layer of colored matter at a lower level is such as to render the term Sierra, employed by those who discovered the layer, altogether more appropriate than chromosphere, which seems to imply that the colored layer forms a spherical envelope. I see no reason why the fine word Sierra should not be restored to its place in our books of astronomy, and the brighter and fainter packs of the corona should not be called corona and glory. Or else the Astronomer Royal's mode of describing them might be adopted, and one called the ring-formed corona, the other the radiated corona, among which those of hydrogen are always present, and are especially noticeable from their length and brilliancy. If, during the observation, the slit of the spectroscope be placed radially, as in figure 137, so that while one half extends over the sun's limb, the other half falls on the chromosphere, the double spectrum of the sun and chromosphere will then be received as shown in plate 9, number 4. So great at the end of the spectrum motif of the sun's disk below. And that of the chromosphere above, near the sea line, power dispersion is requisite, suited to this purpose. In order to subdue the spectrum of diffuse daylight formed at the same time, that only a small portion of the spectrum of the chromosphere can be in the field of view at once. And therefore, the telescope must be brought in various directions onto the system of prisms in order to examine the different sections of the entire spectrum, drawing those portions of the spectrum which are usually observed, since they are those best suited for the examination of the prominences and the chromosphere, and for noticing the changes occurring in them. Figure 139 shows that part of the solar spectrum, which includes the sea line, together with the similar portion of the chromosphere exhibiting the hydrogen line HA, equally broad and somewhat domed to the spectrum of the sun's disk below, and the chromosphere above near the D line, pointed at its termination. Figure 14.1 exhibits the F line and solar spectrum in its immediate neighborhood, and above it, the hydrogen line HSS of the chromosphere. This line is spread out at the base and terminates above in an arrow-shaped point, while the line HI, on the contrary, remains as a rule of the same width throughout as the C line. Figure 140 represents that portion of the spectrum beyond the double sodium line D, where about midway between two very fine dark lines of the solar spectrum, the yet unknown line D3 is situated in the spectrum of the chromosphere. While the red line HGLA is always brilliant and easily seen, the greenish-blue line HSS, though also very bright, is yet much fainter and frequently also much shorter than HOP. The F line, as well as its corresponding line, HSS, is subject to a variety of the spectrum of the sun's disk below, and that of the chromosphere above, near the F line. Changes, such as becoming inflated, bent, widened, twisted, and broken up, a full description of which will be found in section 57. Besides these bright lines constantly occurring in the spectra of the prominences and the chromosphere, there appear from time to time in various places of the spectrum many other bright lines, very marked and brilliant, among which is a line in the red between B and C, but nearer to C, figure 130, number 7. Another in the green between E and F, figure 130, NOSA 358, the iron line 1474K, the magnesium lines, etc. The same way the third hydrogen line, H, blue near G, figure 130, number 2. Frontispiece number 796K appears very brilliant under favorable circumstances. And when the air is transparent and free from vapor, and a high prominence is present, there is also seen the fourth hydrogen line, H3 blue 33701K, which coincides precisely with the dark line marked H by angstrom of a wavelength of 4,101 of a millimeter. This line was seen by Rayet with great distinctness on the 30th of April and on the IST and 20th of May, 1869. The red line near C does not correspond with any of the dark Fraunhofer lines. The remarkable yellow line D3, figure 140, is seen as constantly in every part of the circumference of the sun's disk as the hydrogen lines. The luminous gas to which it is due must therefore, like hydrogen, form a constituent of the chromosphere. Lockyer has been unable to find any corresponding dark line in the solar spectrum for this line, notwithstanding the most careful micrometric measurements and the most painstaking comparisons with the maps of Kirchhoff and Gassiot. 39. The position of this line has been determined by Rayet, as well as by Lockyer and Secchi. If with Rayet the distance between the sodium lines D and D2 be taken as the unit, then the distance of the line D3 from D2 equals 249. If the wavelengths of the lines D and D2 be taken at 59,053 and 58,988 millionth of a millimeter, then the wavelength of the line D3 will be 58,827 millionth of a millimeter. The position of this line in Kirchhoff's scale is, according to Young, 10,175. According to Rayet, 10,168. A series of observations upon this line has lately been instituted by Lockyer, who in conjunction with Franklin had previously ascertained, by comparisons with the spectrum given by a tube filled with hydrogen, that it could not be attributed to hydrogen gas. The results obtained were as follows. 1. With the slit tangential to the sun's limb, the line D3 appeared bright at the lower part of the chromosphere, while at the same time the C line was dark in the same field of view. 2. In a prominence over a spot on the sun's disk, the lines C and F were bright, while the yellow line D3 was invisible. 3. In a prominence which burst forth under high pressure from the sun, the motion indicated by change of the wavelength, section 57, was less for the line D3 than for either C or F. In one case, the C line appeared long and continuous, while the line D3, though of equal length, was broken and interrupted. It follows from this that the line D3 is certainly not occasioned by hydrogen gas, and its source is therefore at present still undiscovered. The reversal of the sodium lines D and D2, vied and subsequently also by Rayet in the spectrum of the chromosphere. That is to say, they have been seen as bright lines. With a tangential slit, Rayet saw both these lines dark upon the sun's lid. At the base of a magnificent prominence 3 high, which appeared to rest upon the sun's limb, both these lines were still dark and fading away, though already somewhat fainter. When nearly 2/3 from the base, they had entirely disappeared. But by a slight displacement of the slit, they were discovered in the form of bright yellow lines. At the summit of the prominence, they were again dark lines. The 4 magnesium lines BLF, B2, B4 are seen not unfrequently as bright lines in the spectrum of the chromosphere, but almost always as very short lines, which seems to show that the vapor of magnesium does not rise to any great height in the chromosphere. When these bright lines are visible, the first 3, BZ, B2, B3, appear of about equal length, while the 4th line, G4, is much shorter. Plate 9, number 4. It has been found by Lockyer and Franklin that a similar phenomenon to that observed in the chromosphere is to be noticed in the spectrum of terrestrial magnesium when formed by the passage of the electric spark through the air between electrodes of this metal and the poles too far separated to allow of the spectrum extending from one pole to the other, but each pole surrounded by a luminous vapor of magnesium. In observing at a short distance the spectrum of this luminous gaseous envelope, the most refrangible of the 3 magnesium lines that made their appearance was always the shortest, and shorter still were several other lines which have not been observed as yet in the spectrum of the chromosphere. Of the many iron lines occurring as dark lines in the solar spectrum, only a few appear as bright lines in the spectrum of the chromosphere. Among these, the line 1474, so often referred to, which shows itself as a short green line, is that most frequently observed. At certain times, when powerful eruptions from the interior of the sun extend into, and even beyond the chromosphere, the spectrum of the latter becomes very complicated. Phenomena of this kind have been frequently observed by Lockyer with a tangential slit. This position offers the advantage of viewing, at one time, a much larger extent of the sun's limb, or chromosphere, than can be obtained by a slit placed radially, although the latter position is advantageous when the object of the observer is to watch the changes occurring in the chromosphere, or to observe especially the form and height of the prominences. When the slit is placed tangentially upon the sun's limb, so that portions of the sun and chromosphere are visible at the same time, to an equal height in the slit, the spectra of the sun and chromosphere are no longer seen side by side, but are partially superposed, the one obscuring the other. An instance of this is given in figure 142, as observed by Lockyer in that portion of the spectrum containing the C line when the slit encountered a prominence. The dark C line was completely annihilated and replaced by a bright band. The line, as shown in figure 143, was differently affected. In the spectrum of the light emitted from the extreme edge of the sun, the bright F line, HSS, appears to be of greater refrangibility than the dark F line itself. But at a short distance from the sun's limb, the dark F line in the spectrum of a prominence was also completely replaced by the corresponding bright line of hydrogen gas. Not only the hydrogen lines, but also many other lines, but also appear bright under similar circumstances in the spectrum of the chromosphere. And on the 17th of April, 1870, hundreds of such bright or reversed Fraunhofer lines were observed by Lockyer at a spot in the chromosphere where prominence was situated. The complications in the spectrum of the chromosphere were most remarkable in the regions more refrangible than C, and in those extending from the line E beyond B, and as far as the neighborhood of S. The vapor of iron under extreme pressure seems to be an important agent in this phenomenon. Among the most remarkable phenomena observable in the bright lines of hydrogen gas seen in the spectrum of the chromosphere is that of the widening at the base and pointed arrow-like termination of the greenish-blue line, HSS, as well as the narrowing to a point of the other bright lines, HA and D3, as represented in figures 139, 140, and 14.1. The causes affecting the width of the spectrum lines have been pointed out in section 32. These have been found to consist partly in the density dependent upon pressure and partly in the temperature of the gas. Yet, according to some experiments made by Secchi, the temperature is found to exercise the most important influence upon the width of the lines. At a given temperature and at a certain degree of rarefaction, the spectrum of hydrogen consists of the three characteristic lines HUI, HSS, H7. With an increase of temperature, the line phi is the first to begin to widen on both sides. Then HSS becomes similarly affected, while HA remains unchanged, even when H7 has passed into a broad, ill-defined violet band. When the gas is rarefied, then HA is the first to disappear, while HSS remains unaffected. On the other hand, it seems to be proved from Secchi's experiments that with the same density of gas, a decrease of temperature is followed by a narrowing of the three lines, and that with a given density, there is a limit to the decrease of temperature at which they will entirely disappear. The pointed termination of the Brighi lines in the spectrum of the chromosphere indicates, therefore, that the temperature of the chromosphere decreases as it recedes from the sun, and at the same time, that the density of the hydrogen envelope is greater at the base of the chromosphere than in the higher regions. The phenomena observed in the C and F lines of the hydrogen gas in the chromosphere and prominences do not, however, consist merely in the widening of the lines and their pointed termination, but also frequently in several other changes, such as their becoming swollen out in several places and assuming a twisted appearance or being broken up into separate pieces. Phenomena which must be regarded as an indication of violent eruptive or 11 changes in the line HSS after Lockyer, stormy action taking place in the interior of the gaseous mass. Among other observers, Lockyer has made many observations of this kind, and he has recorded the appearance presented by these lines. An instance is given in figure 144. Where the F line of the solar spectrum is accompanied by the corresponding bright prominence line, HSS, which, in addition to the usual arrow-pointed termination, has assumed the form of a twisted, wavy line, the lower part of which spreads out over the sun's disk. The C line of the same prominence remained in the meanwhile unaffected, being neither spread out at the base nor twisted in form. A similar phenomenon in a very brilliant prominence was noticed by Professor Young on the 19th of April, 1870. The red C line, HGA, was remarkably bright, so as to admit of its form being observed with a tolerably wide opening of the slit, but in no part was the line either twisted or broken. The F line, HS, on the contrary, figure 145, though equally brilliant, was everywhere broken up into pieces, and at the base was 3 or 4 times wider than usual. It will presently be shown in what manner the displacement of a spectrum line and the phenomena depicted in figures 144 and 145 are connected with the motion of the luminous gaseous mass to which these lines in the spectroscope owe their origin, when, however, as in these instances, only one of the spectrum lines, HS, is so affected, and the other line, HA, remains unchanged. It is scarcely credible that the cause of this phenomenon is to be found in the eddying motion of the gas whence the light is emitted. Young is of opinion that phenomena of this kind are to be attributed to some local absorption by which a line color which is much spread out by the influence of pressure and temperature, is particularly affected. By means of his powerful spectroscope, composed of 5 prisms, Young was able to watch the above phenomenon for half an hour at a time. A series of similar but still more complicated phenomena occurring in the bright spectrum lines of a problem, the causes of which will be dealt with more in detail in section 57, were observed by Lockyer in April 1870, when some sketches were taken of them by an experienced draftsman. In this instance, the phenomena were confined chiefly to the Red Sea line, to which Lockyer directed his attention almost exclusively. When the air is exceedingly tranquil in the neighborhood of a large solar spot, or over a large region in the sun's disk, absorption bands are seen to traverse the whole length of the spectrum, figure 107, crossing at right angles of Fraunhofer lines. They vary in width and in depth of shade according as a pore, a depression, or a completely formed spot is found opposite the corresponding place in the slit. Here and there in the brightest portions of the spectrum there suddenly appears a lozenge-shaped light, figure 146, number 2, in the middle of the absorption line. It is thought by Lockyer to be caused by luminous hydrogen, which is subjected to a more than usual pressure, and this may therefore possibly be the cause of those extremely bright points which are to be observed in the facles in the neighborhood of the sun's limb, base of a prominence as observed with a tangential slit. In it are to be seen 2 or 3 of those lozenge-shaped stripes of light which are due APFC reversal of the C and F line. Apparently, to the greater pressure of the gas, they were more elongated in the direction of the dark line than was the case in the line C. A precisely similar phenomenon was observed by Young in both the D lines. On the 22nd of September, 1870, he saw in the spectrum of the umbra of a large spot near the sun's eastern limb the 2 sodium lines D and D2 reversed, or as bright lines in the manner represented in figure 147. The C and F lines were also reversed at the same time, a phenomenon which has been frequently observed in the spectra of the solar spots. P. 290 with Young's new spectroscope, an instrument possessing a dispersive power equal to 13 prisms of dense flint glass. The line D3 was not visible in the umbra of the spot, but showed itself distinctly in the penumbra as a dark shadow. On the afternoon of the 28th of September, the following lines were seen, bright reversed, in the spectrum of the umbra of the same spot, in the following order of brightness: CFD3 2796 K, or HYB3 DX D2 9B4, and 1474 K. The cause of this phenomenon was soon revealed by the appearance of 2 gigantic prominences, which were observed as brilliant objects in the spectroscope on the sun's disk. One extended into the umbra of the spot, the other only as far as the penumbra. A simple method of illustrating the occurrence of the simultaneous observation of the spectra of the immediate appendage of the sun, the chromosphere, and the sun itself has been devised by Lockyer. He noticed that the flame of an ordinary tallow or stearine candle is surrounded by an envelope of sodium vapor not ordinarily visible, but which can be perceived immediately on the application of the spectroscope by the existence of the yellow sodium lines, if the slit of the instrument be moved slowly from the side into the flame. At the spot, a little above the place where the wick bends outward, the bright line D will at once appear against a dark background. By a further movement of the slit into the flame itself, a second spectrum, the continuous spectrum of the flame, is formed, and there will be seen side by side in the same field of view the 2 spectra, that of the flame and that of the sodium vapor by which it is enveloped. If the flame be agitated so as to produce a flickering, the bright D line may be made to pass through similar changes to those observed in the hydrogen lines of the chromosphere. It may at first sight appear strange that the lines of oxygen, nitrogen, and carbon have never been perceived either in the spectrum of the sun or in that of the chromosphere, seeing that these substances are found in such abundance upon the earth. In his large maps of the solar spectrum, plates for 4, VD6, Ångström has also included the spectrum of the atmospheric air as obtained from the electric spark, whence it may at once be seen that the lines given by air the components of which are nitrogen and oxygen, are nowhere coincident with any of the Fraunhofer lines. The non-appearance of the lines of any substance in the spectrum of a self-luminous composite body in no way justifies the conclusion that such a substance is entirely absent. From Angstrom's investigations, it appears that the spectrum of the atmosphere is not visible when the electric spark is formed in the free air between the carbon points of a Bunsen battery of 50 elements, and can in general only be produced by the employment of a Gassler's tube filled with rarefied air when the electricity is at a high tension, that is to say, under circumstances that accompany an extremely high temperature. In the same way, the spectrum of carbon cannot be obtained by the mere incandescence of carbon in the electric current. The spectrum thus produced consists partly of the continuous spectrum of the incandescent solid particles of carbon, and partly of the spectra of carburetted hydrogen and of cyanogen. The heat of the voltaic arc of flame, section 10, is therefore insufficient to convert carbon into a gaseous form. We are led with Angstrom to the conclusion that the temperature of that luminary is on the one hand too high to permit of such combinations as carburetted hydrogen, cyanogen, etc. being formed, and on the other hand, too low to allow of carbon being converted into a gaseous state so as to form its spectrum, or to produce the spectra of oxygen and nitrogen. Similar results have been arrived at by Woolner, Secchi, and Zollner. Woolner by means of experiment, p. 173. Zollner by ingenious reasonings upon the behavior of hydrogen, nitrogen, and oxygen in the sun as affected by variations in their density, specific gravity, and emissive power, founded upon the supposition that the eruptive forms of the prominences are to be regarded as the result of hydrogen gas rushing to the outer surface from the interior of the sun, and that the cause of these eruptions is to be sought for in the difference of pressure to which the gas is subject in the interior and on the surface of the sun. Calculations made on this hypothesis, taking into account the amount of Hb plus Zollner, über die Temperatur und physische Beschaffenheit der Sonne, Berichte Künigl, 6 Gesellschaft der Wissenschaften vom Juni 1870. Drogen present in the sun would lead us by analogy to regard the amount of oxygen and nitrogen in that stratum, where the hydrogen spectrum begins to be continuous as extremely small in comparison with the amount of hydrogen. Those rays, therefore, which are given out by a stratum of hydrogen yielding a continuous spectrum, pass through so small an amount of incandescent particles of oxygen and nitrogen in coming to our eye, that the absorption they suffer is extremely small, and therefore not perceptible. For this reason, even supposing the sun to possess an atmosphere of nitrogen and oxygen, similar in density and temperature to its atmosphere of hydrogen, the lines of nitrogen and oxygen would still fail to be visible either as dark Fraunhofer lines in the spectrum of the sun, or as bright lines in the spectrum of the chromosphere. It must not be concluded, therefore, from the absence of the lines of nitrogen and oxygen in both these spectra, that these substances are not present in either the sun or the chromosphere. From all these observations, the following results may be deduced concerning the nature of the chromosphere. 1. The body of the sun or its light-giving envelope, the photosphere, is completely surrounded by a gaseous envelope in which hydrogen constitutes the chief element and which is called the chromosphere. Its mean thickness is between 50 and 70 miles. 2. The prominences are local accumulations of the chromosphere, and therefore preeminently of hydrogen gas, which appear to break forth from time to time from the interior of the sun in the form of monster eruptions, forcing their way through the photosphere and chromosphere. As this gas on effecting a passage rises with great rapidity, it becomes quickly rarefied in a direction away from the sun's limb. 3. As in the spectrum of the chromosphere, the greenish-blue line, HSS, coincident with the Fraunhofer line Fe, takes in general the form of an arrowhead, the base of which rests on the sun's limb, and the widening of this line is caused by an increase of pressure as well as by a rise of temperature. Therefore, the pressure and the temperature of the gas in the lowest stratum of the chromosphere must be greater than in the upper part, from the experiments undertaken by Lockyer, Franklin, Woolner, and Secchi. It appears that even in the lowest stratum of this gaseous envelope, the pressure is smaller than that of our atmosphere. Therefore, that the gas of the chromosphere is in a state of greater attenuation. 4. The greenish-blue line, HSS, which under normal conditions is of the same width as the lines HA and C, sometimes in a prominence swells out in a globular form, and is twisted over the chromosphere line, figure 144. The cause of which is probably the sudden and violent meeting or damming up of streams of gas and their consequent condensation. 5. The three characteristic lines of hydrogen, HHSS high, as well as a fourth blue line, are all observed with complete certainty in the spectrum of the chromosphere, and that of the prominences, in good instruments, and under favorable atmospheric circumstances. The first two lines sometimes extend into the spectrum of the regions underlying the chromosphere, and thus cause the corresponding Fraunhofer lines C and F to appear as bright lines upon the sun's disk. The yellow line D3 of the chromosphere is neither due to sodium nor to hydrogen, nor is the red line less refrangible than Ci hydrogen line. It has not yet been ascertained to what substances they belong. 6. Under the chromosphere lies the luminous cloud-like vaporous or nebulous photosphere, which contains all the substances, the spectrum lines of which appear as absorption lines in the solar spectrum. These substances, among which iron, magnesium, and sodium are especially prominent, often burst forth in a state of incandescence and are carried up to a certain distance into the chromosphere and into the basis of the prominences, though not in general to any considerable elevation. Secchi has been led to believe from his observations during the total eclipse of II 860, as well as from those recently undertaken with his large instrument, that the chromosphere does not immediately rest on the sun's limb, but is separated from it by a very thin space of white light from 2 to 3 in thickness, 40 miles, which gives a continuous spectrum. Secchi is of opinion that Kirchhoff's assumed atmosphere of luminous vapors, in which the white light of the sun suffers the selective absorption producing the dark lines, is to be found in this stratum of white light. This view is opposed by Lockyer, who denies the existence of this stratum of light separating the chromosphere from the sun's limb. According to him, the photosphere, a very narrow stratum of mixed luminous vapors which yield reversed spectra of the Fraunhofer lines, forms the border or upper surface of the solar nucleus, upon which the chromosphere or stratum of glowing hydrogen gas immediately rests. Kirchhoff's theory that the solar nucleus is surrounded by a very expanded non-luminous and comparatively cool absorptive atmosphere must therefore give place to that of the glowing and light-emitting photosphere, being surrounded by a luminous and intensely hot stratum of gas, the chromosphere, the spectrum of which consists mainly of that of hydrogen gas. Lockyer is of opinion that from the extremely rarefied condition of this gas, the existence of any other atmosphere extending beyond it, as might be inferred from the corona, is very improbable, and that the thickness of the chromosphere would be indicated by the height of its spectrum lines, the bright hydrogen lines HAH 3H7, these lines being broad at the limb of the sun and running to a point at the top, lead to the conclusion that the temperature of the chromosphere at the height indicated by the termination of the lines is insufficient to keep hydrogen gas in a state of luminosity. It has been ascertained, p. 173, that an increase of temperature imparts to hydrogen the power of widening its spectrum lines, while, on the contrary, a decrease of temperature produces a narrowing of the lines. Now, the spectrum lines of a prominence are broad at the base in the neighborhood of the sun's limb, and terminate in a point, figures 140, 14.1. The temperature at the point must therefore be lower than at the base. The envelope of hydrogen may manifestly extend far beyond the limit of the bright lines, without its existence being revealed to us by the lines of its spectrum. And for this reason, these bright lines afford no sufficient measure for the thickness of the chromosphere. It is much more probable that, owing to a continuous decrease in its temperature and density, the chromosphere stretches out into space to a distance far beyond our power of recognition. Chapter 57. Modes of observing the prominences in sunshine. Form of the prominences sunshine. Form of the prominences. As early as 1866, Lockyer attempted to observe the prominences in full sunshine by means of a Herschel-Browning spectroscope, placed in combination with a telescope. The method he employed, special communication, depends, as we have previously mentioned, P382, on the specific difference between the light of the prominences and that of the sun itself. The light of an incandescent solid or liquid body which passes through the slit of a spectroscope will be spread out by the prism into a band of greater or less length and form a cocontinuous spectrum. The light of a gaseous or vaporous body will by the same means, on the contrary, be decomposed into a few only, sometimes even into a very few bright lines. In the first case, the greater the length of the spectrum, the less will be its intensity and calm, by Mr. Johnston Stoney, published in 1867, in which he anticipated from theoretical considerations some of the results since obtained from observation. See abstract proceedings, Roy? So key, vol the 60th, P25, and vol the 70th, P1. May not the spectroscope afford us evidence of the existence of the red flames which total eclipses have revealed to us in the sun's atmosphere? Although they escape all other methods of observation, comparison with that of the source of light, in the second case, especially when the spectrum consists only of a couple of lines, the intensity of each line is little less than half that of the light itself, if, therefore, an equal amount of light from two self-luminous bodies, one of which is solid or liquid, and the other gaseous or vaporous, enter the slit of the spectroscope at the same time, the bright lines of the latter will be more brilliant than the color of the corresponding portion of the continuous spectrum. Now, by increasing the number of prisms, the continuous spectrum may become so elongated and consequently diminished in light that, as we have already mentioned, P234, the once brilliant solar spectrum may be reduced to the verge of visibility, while the same amount of dispersion produces on a spectrum of lines from glowing gas only an increase in the distance between the lines, and no considerable diminution of their brilliancy. The reason why the prominences round the sun's limb cannot be seen through a telescope at any time by screening off the intense light of the sun is owing to extreme brilliancy with which the sun illuminates the Earth's atmosphere, the particles of which scatter so large an amount of light as quite to overpower the fainter light of the prominences, and prevent them making any sensible impression on the eye. In a total eclipse of the sun, the light of this atmosphere is so considerably reduced as to allow the larger prominences beyond the limb of the sun to be observed by the unassisted eye. The possibility of reducing the glare of sunlight at any other time without extinguishing the light of the prominences rests on the circumstance already mentioned, that the light of the sun consists of rays of every color, and therefore produces in a spectroscope of highly dispersive power a long and faint spectrum, while the light of the prominences, consisting in general of only 3 or 4 kinds of rays, remains even after the greatest dispersive power still concentrated into the same number of lines. Says H70. It was on these principles, first announced by Lockyer, that Janssen succeeded the day after the eclipse of the 18th of August, 1868, in observing the spectrum of the prominences in sunshine. That the method he employed was no other than that suggested by Lockyer is evident from his own communication to the French Academy, dated Calcutta, the 3rd of October, 1868, in which he expresses himself as follows. The principle of the new method rests upon the difference between the spectrum peculiarities of the light of the prominences and that of the photosphere. The light of the photosphere, which is derived from incandescent solid or liquid particles, is incomparably stronger than that of the prominences which is derived from gases. On this account, it has been impossible hitherto to see the prominences except during a total solar eclipse. By the employment, however, of spectrum analysis, the circumstances of the case may be reversed. In fact, by the process of analyzation, the light of the sun is dispersed over the whole range of the spectrum, and its intensity becomes considerably lessened. The prominences, on the contrary, furnish only a few detached groups of rays, which are bright enough to bear comparison with the corresponding rays of the solar spectrum. It is for this reason that the lines of the prominences may be seen easily in the same field of the spectroscope with the solar spectrum, while the direct images of the prominences are invisible on account of the overpowering light of the sun. Another circumstance very favorable to this new method of observation lies in the fact that the bright lines of the prominences correspond with the dark lines of the solar spectrum. They can, therefore, not only be more easily recognized in the field of the spectroscope along the edges of the solar spectrum, but also detected on the solar spectrum itself, and their traces even follow on the very surface of the sun. As soon as Janssen and Lockyer had succeeded by this method in observing the spectra 7 of the prominences independently of a total eclipse, it became a question whether it would not be possible not merely to see the lines of the prominences, but also to make their actual forms visible during sunshine. The length of the bright lines of a prominence, the line HSS for instance, corresponds with the height of that part of the prominence which lies in the direction of the slit. And it has been already shown, p. 381, how by passing the slit over the surface of the prominence and mapping down the varying height of the line HSS, Lockyer succeeded in constructing the outline of a prominence. Proposed to bring the slit successively over every part of the surface of a prominence by means of the quick rotation of a direct vision spectroscope, so that when the motion was sufficiently rapid, he might be able, owing to the duration of the impression of light upon the eye, to see the complete outline at one view. The same idea occurred both to Lockyer and Zollner. The former, without interfering with the spectroscope, merely gave the slit a rapid revolution in a direction at right angles to that of the instrument. The latter accomplished the same end by giving the slit an oscillatory motion by means of a spring. But these experiments, though giving promise of success, were soon abandoned for other methods, partly on account of the mechanical difficulties they entailed, partly because it soon appeared that the object could be far better attained by a much simpler process. Huggins had already been working for 2 years in another direction. As the prominences were pale red or pink in color, it occurred to him that it might be possible to see them fully during sunshine if he could succeed by the intervention of colored glasses in eliminating the intense yellow, green, and blue rays from the white light of the sun. Were this accomplished, it was to be expected that the red light of the prominences would alone pass unobstructed through the glasses, and be no longer overpowered by the remaining atmospheric rays, so that the forms of the prominences themselves would be seen direct by the aid of a telescope or an opera glass. After selecting with great care, by means of prismatic analysis, a number of colored glasses and fluids suitable for this purpose, Huggins examined the sun by their aid, both by viewing it through them directly, and also by projecting the image of the sun upon a screen in a dark room, after the white light had previously been sifted, so to speak. By means of the system of colored media, this plan, however, failed in accomplishing its object, and in the winter of 1868 Huggins resumed his labors by employing as a medium a ruby-colored glass, which permitted only the extreme red rays of the spectrum to pass through. On the 13th of February, 1869, he first succeeded in bright sunshine in seeing a prominence with sufficient distinctness to determine its form and draw its outline. For this investigation, he made use of a spectroscope in which a narrow slit had been introduced between the prisms and the object glass of the small telescope. Close in front of the latter, this slit admitted into the telescope only those rays of a refrangibility exactly corresponding to that of the line C, as the bright C line, always occurs in the spectrum of a prominence. Huggins knew that when he saw this line visible in the instrument, a prominence was in the field of the slit, when he widened the slit of the spectroscope so as to view the whole form of the prominence. The spectrum became so impure that the image could only be traced with difficulty, and the light from the neighborhood of the C line became at the same time so intense as to interfere injuriously with the susceptibility of the eye. He then applied a deep ruby-colored glass to absorb the rays of a different refrangibility to that of the C line. When the prominence was seen in a complete form with perfect distinctness, a sketch of the prominence first observed by Huggins in this manner is given in Figure 148. Simultaneously with Huggins, both Zollner and Lockyer were each working independently towards the same end. Zollner, already known to fame by his photometrician under Suchenjan and well acquainted with the construction of every kind of optical instrument, had in a treatise entitled Über ein neues Spektroskop, etc., given expression to his ideas on the different modes of observing the forms of the prominences in sunlight, with a description of the experiments he had himself undertaken in this direction. He came to the conclusion that the method of diminishing the light of the Earth's atmosphere by a sufficient increase in the number of prisms deserved the most decided preference over the methods of a revolving slit or an absorptive medium. But he was unable himself to put this plan immediately into practice owing to the incomplete state of the necessary instruments. The mode of procedure which Zollner considered as most suitable consisted of a combination of Lockyer's principle with the last method employed by Huygens, namely of first seeking out the spectrum line of a prominence, and then opening the slit so wide as to be able to see the entire prominence, or at least a portion of it, through the aperture, when Lockyer learnt on the 27th of February 1869 that Huygens had succeeded in seeing the prominences in sunshine by merely widening the slit. The same idea occurred to him which Zollner had already published on the 6th of the same month, but which he had not been able to carry out practically, that the diminution of the atmospheric light would be much more completely accomplished by an increase in the number of prisms than by the use of absorptive glasses, and that the prominences would certainly be seen in their whole extent if one of their spectrum lines, the greenish-blue line HSS or the red line HA, for instance, was brought into the field of view of a spectroscope of great dispersive power, and the slit then opened sufficiently to allow the complete form of the prominence to be seen. The admirable telespectroscope, figure 136, furnished with 7 prisms, which was then complete and in his possession, confirmed after a few trials the correctness of this view, and he was the first to succeed without additional mechanical help or the use of colored glasses in observing the prominences at any time when the sun was visible and tracing their complete outline. By the same means, Zollner saw the prominences for the first time on the S of July, 1869. He has published the results of his observations and accompanied them by a series of highly interesting drawings of some of the larger prominences in 2 July, 3H 25 of July, 3H 45, July 6 45. Angle equals 76 degrees. Height equals 38. Height equals C120. Height equals 35 to 42 July, NH 35 July, Nina. Limb, NW limb. Height equals C65. Height equals C40. Height equals 35 solar prominences observed by Zollner, which their origin, development, and subsequent disappearance are very clearly exhibited. Slit to render the prominences less distinct than when seen by the method of using a wide slit, and more than to counterbalance the advantage of viewing at once a much larger portion of the sun's limb. On figure 149 are given some of the most conspicuous forms of these masses of flame, together with the date of observation, the place of their appearance on the sun's limb, and their height in seconds, vide note in P330. With regard to these forms, Zollner makes the following remarks. The first prominence which I observed is represented in figure 149. Over a conical mass of extreme brilliancy projecting from the sun's limb, there extends a cloud-like form of less intensity. To the same type belong also the prominences number 4 and number 6. Number 4 was a very striking object from the surprisingly beautiful cloud of cumulus form, which floated at some distance above the cone. The cloud was remarkably soft in texture and traceable in its smallest details. The individual cumulus-like elements of which it was composed appeared almost like faintly luminous points. One of the most remarkable forms was that represented in number 2. I could hardly trust the evidence of my eyes as I perceived in it the lambent motion of a flame. This motion was, however, slower in proportion to the size of the flame than the corresponding motion in the high flaring flames of great conflagrations. The time required for the propagation of this wave of flame from the base to the termination of the image was between 2 and 3 seconds. It is in most cases a matter of indifference whether the red line, HS, be selected for this method of observation. The requisite width of slit depends mainly upon the condition of the atmosphere. If the observing telescope of the spectroscope be fixed upon the sea line, and the narrow slit be so directed onto the limb of the sun that the red line HA appears in the field of view on widening the slit, the prominence will be seen of a red color. If, on the contrary, the F line and the line HS be observed, the same form will be visible in the color of greenish blue. It will not perhaps be superfluous to mention that, even with the smallest opening of the slit, a very considerable portion of the sun's surface is included in the field of view. If this opening be not greater than n of an inch, and the image of the sun, as in Lockyer's instrument, be nearly an inch in diameter, yet the rays passing through the slit would include those emitted from a space on the sun's surface of about 300 miles in extent. Each of the two methods described in section 55 of observing the spectrum of the chromosphere and that of the prominences possesses peculiar advantages. If the object be merely to analyze the various lines in the spectrum of the chromosphere, then the magnified image of the sun is examined by means of the narrow slit. But if, on the contrary, the forms of the prominences are to be observed, the small direct image of the sun formed in the principal focus of the object glass is made use of, and a wider slit is employed. When, as in Secchi's equatorial, the direct image of the sun is about I inch in diameter, and the slit of the spectroscope can be opened about L of an inch. The whole of prominence may be seen at once, if not exceeding 40 or 50, 18.0 or 22.0 miles. Prominences exceeding that height must be observed piecemeal, under such circumstances with a wide slit radially placed. It is not easy to observe in the small image of the sun the thickness of the chromosphere, even supposing it to extend to some distance, while in the magnified image it may readily both be seen and measured. If the widened slit be placed tangentially, that is to say, in a direction parallel to the sun's limb, the stratum of the chromosphere appears as a very bright red band. Upon this line are seen small elevations of a form resembling such flames as are to be seen in the fields of an evening at harvest time when the stubble is being burnt. The prominences are to be distinguished from the rest of the chromosphere by their more vivid light, and in general by their rising to a much greater elevation. When the spectrum of the Earth's atmosphere has disappeared in consequence of the powerful dispersion of the light, and the portion of the prominence then in the held of view alone is visible through the widely opened slit, the telescope or slit is moved slowly forward, and luminous images of the most wonderful forms flit before the eye, being just as easily observed as during a total solar eclipse. In describing some of these shadow forms, Lockyer writes, "Here one is reminded by the fleecy, infinitely delicate cloud films of an English hedgerow with luxuriant elms. Here of a densely intertwined tropical forest, the in all directions threading in all directions. The prominences generally expanding as they mount upwards and changing slowly, indeed almost imperceptibly. As a rule, the attachment to the chromosphere is narrow and is not often single. Higher up, the stems, so to speak, intertwine, higher up, and the prominence expands and soars upward until it is lost in delicate filaments, which are carried away in floating masses. The various forms of the prominences may be classified generally into two characteristic groups, very aptly designated by Zollner as vaporous or cloud-like forms and eruptive forms. Through a small telescope, the details of the outline and internal configuration of these forms are less clearly visible. Some of these are represented in figure 150, known as 1-13, as they were seen by Lockyer through his telescope, when they appeared as prolongations of the sea line of the solar spectrum in the form of red flames. The upper part is the spectrum of the sky immediately surrounding the sun, reduced to the verge of visibility by the great dispersive power of the spectroscope. Upon this first appeared the red line HA, which on widening the slit assumed the form of the prominence visible at that spot, represented in the drawings as white upon a black background. In some cases, number 2, the prominence was seen to extend downwards along the sea line. In others, the sea line appeared waved or interrupted, and sometimes terminated in a lozenge-shaped light of a red color. In number 3, the dark F line also appeared waved. and the small flame above it was of the greenish-blue color peculiar to that part of the spectrum. Professor C.A. Young of Dartmouth College, Hanover, in the United States, has devoted himself especially to the observation of the forms and variability of the prominence. In Figure 151, no stop 1 to 8 are represented some of these characteristic forms according to the drawings prepared by Young. The observations were made early in the afternoon on various days between the ist of October and the 4th of November, 1869. The annex table contains particulars of their size and position. No, position, angle, breadth, height. Remarks: 230 degrees, 68 degrees, 45, very brilliant. 267 degrees, 31 degrees, 60 bright and in two parts. 270 degrees, 28 degrees 30, faintly luminous, in form resembling a mushroom. 335 degrees, plus 37 degrees, 55 bright, cloud-like. 150 degrees, 32 degrees, an isolated cloud, 25 above the sun's limb, 20 in diameter, 35 degrees, plus 63 degrees, 35 bright, a low flat. 260 degrees, 35 degrees 20, a small horn rising from a depression in the chromosphere in the neighborhood of a spot. 345 degrees, plus 5 degrees, 65. A gigantic pyramid of cloud with active internal motion. On the 17th of September, 1869, an extended chain of prominences was seen by the same observer between plus 8 degrees and plus no degrees position angle, a representation of which is given in Figure 152. These enormous masses of flaming gas extended along the sun's limb for a distance of nearly 224 miles, and attained a height of 50 or 23 miles. The points of greatest brilliancy were at a Down B. Slight changes in the form of the prominences may be watched almost without intermission with an open slit. Great changes as a rule take place only very slowly or quite imperceptibly. In some cases, however, the change in the form of a prominence is so extraordinary and occurs with such rapidity that it can only be ascribed to extremely violent agitation in the upper portions of the solar atmosphere, compared with which the cyclonic storms occasionally agitating the Earth's atmosphere sink into insignificance. The observation of such a solar storm has been thus described by Lockyer. On the 14th of March, 1869, about 9h45 m with a slit tangential to the sun's limb, instead of solar storm observed by Lockyer on the 14th March, 1869. Picture 1. Radial, which was its usual position, I observed a fine dense prominence near the sun's equator on the eastern limb in which intense action was evidently taking place. At EOAO, fifth time, when the action was slackening, I opened the slit. I saw at once that the dense appearance had all disappeared and cloud-like filaments had taken its place. The first sketch, Figure 153, embracing an irregular prominence with a long, perfectly straight one, was finished at storm observed by Lockyer on the 14th March, 1869. Picture 2. 5. The height of the prominence being T5, or about 27 miles. I left the observatory for a few minutes, and on returning at 15 Imminum, I was astonished to find that part of the straight prominence had entirely disappeared. Not even the slightest rack appeared in its place. Whether it was entirely dissipated or whether parts of it had been wafted towards the other part, I do not know. Although I think the latter explanation the more probable one, as the other part had increased, which is to be seen clearly in the second sketch that was taken, Figure 154. The 4 drawings given in Figure 155 were made from one and the same brilliant prominence observed by Professor Young on the 7th of October, 1869. Its place was estimated at 1250 position angle. Its breadth was 70 and its height measured 75. The changes in its form took place with extraordinary rapidity. The 4 drawings were made at the following epochs: 1 2035 m, 255 m, and 330 A nearly horizontal movement of the various masses of cloud was perceptible in the interior of the prominence. The form of number 2 resembles the large prominence called the Eagle, which was observed at the total eclipse of the 7th of August, 1869, in the interior of which the original photographs clearly show an eddying motion in the lower part, while the upper part exhibited a centrifugal movement by which the gas was whirled off horizontally. In plates C1 and D12, two prominences are represented in their natural colors as seen in a large telescope when the slit of the spectroscope was opened wide and directed on to the red sea line, HA. They are characteristic of the two classes, the eruptive and the turbulous class, and serve to illustrate the remarkable changes of these forms. The prominence given in Plate 11, Nos. 1 and 2, is observed and drawn by Professor Zollner and is of an eruptive form with a decided rotatory movement. The prominence represented in Plate 12, Nos. 3 and 4, is one observed by Professor Young and is of a cloud-like character. By means of the accompanying scale, their height can be easily ascertained. As the meteorologist registers many times in a day the conditions of our atmosphere in the hope that a comparison of the observations may lead to a discovery of the law governing these changes, so has Respighi, director of the University Observatory at the Campidoglio at Rome, made it his daily task since October 1869 to observe the entire limb of the sun, when the weather was favorable, including the chromosphere and prominences, and to mark upon a straight line representing the circumference of the sun the position, height, and form of the prominences for each day by collating these lines or circumferences of the sun one below the other, and crossing them with lines indicating the principal positions. A comprehensive picture is afforded of the distribution of the prominences round the sun's limb, which shows at a glance those regions in which the prominences abound and those in which they are least frequently to be met with. The instrument employed by Respighi is an equatorial telescope by Merz, a 44 inches aperture, with a direct vision spectroscope of great dispersive power constructed on Hoffman's principle. At each observation, the slit is placed in a direction tangential to the sun's limb, and beginning at the north point is carried round the sun, its place at the various points of observation being read off on the position circle of the telescope. At each adjustment of the slit, about 200 of the circumference could be examined, so that 16 adjustments suffice to survey the entire limb of the sun. The presence of a prominence was revealed in the manner previously described by the red sea line, HA, being seen to extend to a greater or less distance beyond the chromosphere, when the narrow slit was removed somewhat from the sun's limb. In order to observe the form of the prominence, the slit was widened to the full height of this line. When this height exceeded, the Respighi's observations of the prominences round the entire limb of the sun. Observation was made in parts from the sun's limb outwards, since by a wider opening of the slit, the light became too brilliant. By this method, Respighi sketched in detail the whole circumference of the chromosphere point by point. And it will be seen from figure 156, which is an exact copy on a reduced scale of one of his original maps, how the aspects of the prominences, their distribution on the sun's limb, and their forms and heights during the space of a month may be viewed at a glance. The prominences are represented in the drawing twice the size they really appear. In the line's day is marked with an asterisk. The observations are not trustworthy, owing to the prevalence of fog. By a comparison of the maps already constructed, Respighi has arrived at the following results. 1. In the polar regions, prominences occur only exceptionally. The district from which they are absent lies between north and northeast on the one side, and south and southwest on the other. The portion which is almost entirely without prominences has a semi-diameter of 22.22. The district where the prominences most frequently occur lies between north and northwest, and at about 450 north latitude, in a region where solar spots are rarely seen. 3. The prominences are therefore phenomena quite distinct from the spots. They are probably more intimately connected with the formation of facles, P270, an hypothesis supported by the observations of both Gilman and Lockyer. 4. The various forms of the prominences show that they are not of the nature of clouds, which float in an atmosphere in which they are produced by local condensations. They are much more like eruptions out of the chromosphere. which often spread out of the higher regions and take the form of bouquets of flowers, some being bent over on one side and some on the other, and which fall again onto the surface of the chromosphere as rapidly as they rose from it. 5. It appears that eruptions of hydrogen take place from the interior of the sun. Their form and the extreme rapidity of their motion necessitates the hypothesis of a repulsive power at work, either at the surface or in the mass of the sun, which Respelai attributes to electricity, but Fay simply to the action of the intense heat of the photosphere. On the 28th of September, 1870, Professor Young succeeded for the first time in photographing the prominences on the sun's limb in bright sunshine. This he effected by bringing the blue hydrogen line HY near G into the middle of the field of the spectroscope, and placing a small photographic camera in connection with the eyepiece of the telescope. As the chemicals employed were those ordinarily used in taking portraits, the requisite time of exposure was 2 minutes, during which time the image of the prominence suffered a slight displacement on the prepared plate, owing to a want of accuracy in the perfect adjustment of the polar axis. Still, however, the various forms of the prominences could be clearly discerned in the photograph, which was 1/2 inch in diameter, so that the possibility of photographing the prominences has been proved by Young's experiment. Chapter 58. Measurement of the direction and speed of the gas streams in the sun and of the gas streams in the sun. One of the most glorious triumphs of spectrum analysis, surpassing perhaps in splendor all its other wonderful achievements, is the discovery that by means of accurate measurements, undertaken with the best instruments, of the position, or rather of the small displacement in the position of the spectrum lines of a star or other source of light, a prominence, for instance, it is possible to ascertain whether this luminous body be approaching us or receding from us, and at what speed it is traveling. The principle on which investigations of this kind are founded was suggested by Doppler in 1842, who sought to explain the periodic change of color in variable stars by assuming their motion to bear some comparison with that of light, and therefore that the number of ether waves striking the eye in a second would be greater if the star were approaching us, and smaller if it were receding from us than if it were at rest. Now, as violet light produces the greatest number of vibrations in a second, and red light the fewest vibrations, it follows that if the star be approaching, its light will be displaced in the direction of the violet, and in the direction of the red if the star be receding from us. The pitch of a musical tone depends, as is well known, upon the number of impulses which the ear receives from the air at a given time. P59. Now, as a tone rises in pitch, the greater the number of air vibrations which strike the tympan in a second, so must the sound ascend in tone if we rapidly approach it, and fall in pitch if we recede from it. The truth of this supposition may be fully proved by the whistle of a railway engine in rapid motion. To an observer standing still, the pitch of the tone rises on the rapid approach of the locomotive, although the same note is sounded, and falls again as the engine travels away. As the various tones of sound depend on the rapidity of the air vibrations, so the varieties of place of waves which had been raised or lowered in refrangibility by the star's motion. No change of color in the star could take place until the whole of those invisible waves of force had been expended, which would only be the case when the relative motion of the star and the observer was several times greater than that of light color, are regulated by the number of ether vibrations, P63. If therefore a luminous object, as for instance the glowing hydrogen of a prominence, be receding rapidly from us, fewer waves of ether will strike the optic nerve in a second than if it were stationary. If the difference in the number of ether waves be sufficiently great to be perceived by the eye, then each color of the glowing gas must sink in the scale of the spectrum, that is to say, incline more towards the red. The individual colored rays will not then, in the prismatic decomposition of the light, occur in the same place of the spectrum in which they would have appeared had the light been stationary. They will all be displaced somewhat towards the red. The converse takes place when the luminous body is rapidly approaching us. The number of ether vibrations received by the eye is then increased beyond what it would be if the source of light were stationary. In the prismatic analysis of the light, The colored rays will be found likewise to have changed their place in the scale of the spectrum and taken a position in accordance with their increased refrangibility, suffering a general displacement towards the violet when it is remembered that the number of ether red light is at least 480 billion and in violet 800 billion in a second, and that, moreover, the wavelength of the greenish-blue light, HSS, situated at the spot marked F in the solar spectrum, is only millionth, more precisely OH 48,505 of a millimeter, 44 to 6, and that instruments of sufficient delicacy to measure these minute quantities are required for this purpose. There will be little danger of underestimating the extreme difficulty connected with observations of this displacement in the colors of the spectrum. Indeed, these observations would scarcely be possible were it not that in the dark lines crossing the spectra of the sun and fixed stars, the places of some of which may be accurately ascertained. We have fixed positions in the spectrum, the degree of refrangibility or wavelength of which may be determined beforehand both for the sun and terrestrial substances, and also for the stars or others supposed to be at rest. We shall presently see how Secchi and Huggins have availed themselves of this principle to determine the rate at which a fixed star is approaching or receding from the earth. Lockyer made use of the same plan for measuring the speed at which the glowing hydrogen gas composing the prominences streams forth from the sun's nucleus, or sinks again when the eruptive force is exhausted. The principle of this method rests on the following considerations. The refrangibility of the greenish-blue light, HASS, which with the red Ha and the blue light, Ha is emitted by glowing hydrogen gas, frontispiece number 7, is determined by the position of the line F in the solar spectrum. If any displacement be observed in the line F, that is to say, a change in the refrangibility or wavelength of the greenish-blue light, without the neighboring dark line suffering any displacement at the same time, it is evident that the cause of this movement cannot be attributed either to the motion of the earth or to that of the sun, but is rather to be ascribed exclusively to the motion of the luminous hydrogen gas. If the hydrogen gas in the sun were rapidly approaching us, the number of its ether waves in a second must increase. The length of each wave will become shorter, and the light be inclined towards the violet. Because that color is composed of the shortest wavelengths, Daphne suffers then a displacement from its usual position in the solar spectrum towards the violet end. If the shortening of the ether waves of the greenish-blue hydrogen line, HSS, be only of a millimeter, the due-earth direction and speed of the gas streams in the sun, consequent displacement of the F line can be perceived, and by this means the motion of the hydrogen gas on the sun be demonstrated. If, on the contrary, this gas be moving in the opposite direction and be receding sheaf from us, the number of its ether waves in a second will decrease, the wavelengths will be augmented, the greenish-blue rays will approach the red, and a displacement of the Y line will be produced then towards the red end of the spectrum. With regard to the approach or recession of the hydrogen gas in reference to an observer on the Earth, there are two different circumstances to be taken into account. If the direction of the arrow A in figure 157 be supposed to denote a luminous stream of gas rising from the sun and approaching the earth, that of the arrow N, on the contrary, to represent a stream of gas sinking again into the sun and receding from the earth, the stream will cause a displacement of the F line towards the violet, and the stream N towards the red, providing the velocity be sufficiently great to alter the wavelength at least of a millimeter. Tangential or side streams, however, indicated by the arrows R and, will have no influence in displacing the F line. They neither approach nor recede from the eye, their direction being perpendicular to the line of sight L. The telespectroscope be directed to the center of the sun in the direction of the line L. We shall, in the event of the displacement of the F line, receive only the rising and falling gas streams, A and N, the velocity of which can be measured, but neither of the lateral streams flowing at a tangent to the sun's surface. But if the instrument be directed to the sun's limb at R, the case is reversed, and the rising and falling gas streams acts in T, inasmuch as they neither approach the eye nor recede from it, and therefore produce by their motion No displacement in the F-line cannot be perceived. If, on the contrary, the lateral or tangential streams, Rx, LT be traveling at this spot with sufficient rapidity, the stream Rx will approach the eye of the observer and cause a displacement of the F-line towards the violet, while the stream LT receding from the Earth will produce a displacement of the same line towards the red. It is evident, therefore, that the rising and falling streams of hydrogen gas are best observed in the geomelansocian sec. From the eye, 1 to red, UL10 towards the I1, the 0I E3 violet 35, Dewey displacement of the F-line velocity of the gas streams in the sun. Central part of the sun, while the lateral streams compared by Lockyer to circular storms, whirlpools or cyclones, the best observed on the sun's limb are horizon. If it should happen that the hydrogen lines suffer a simultaneous displacement at both sides, or a uniform increase in width, it is obvious that the inference of motion in the luminous body must be received with caution. The cause of such a widening of either the bright or the dark lines must rather be sought for in an increase of density or temperature in the luminous gas, section 32. When, however, the expansion of the lines occurs sometimes on one side only, then only on the other, and again unequally on both sides. This cannot, according to the investigations of Lockyer and Franklin, be ascribed to a change in density, since by an increase of pressure, the F-line of hydrogen gas always expands equally or nearly equally on both sides. Shows clearly what remarkable changes take place in the dark line F when the spectroscope is directed to a solar spot in the middle of the sun. The dark band passing through the length of the spectrum is occasioned by the general absorption and weakening of the light produced by the substance of the spot. The F-line, which as a rule is sharply defined at the edges, appears in some places not merely as a bright line, but as a bright and dark line twisted together, in which parts it suffers the greatest displacement towards the red. When this occurs, there is frequently also a bright line to be seen on the violet side. In small solar spots, this line sometimes breaks off suddenly, or spreads out immediately before its termination in a globular form. Over the bright faculae of a spot, the bridges, the line is often altogether waning, or else it is reversed, and appears as a bright line, compare figure 108, also 45 T red C line. Though as the greenish-blue F-line, HSS, is by an equal increase of pressure much more sensitive with regard to expansion than the red line is, and exhibits with greater distinctness the changes that have been already described. It is better adapted to observations of this kind. All these expansions, twistings, and displacements of the F-line result, as we have already learnt in section 56, from a change in the wavelength of the greenish-blue light emitted by the moving masses of incandescent hydrogen gas in the sun. The middle of this line, when it is well defined, corresponds to a wavelength of 485 millionth of a millimeter, yet it is possible by means of Angstrom's maps of the solar spectrum, plates 4. Sixth, to measure a displacement of this line, when the wavelength has only changed as much as of a millimeter, and inversely, it is also possible to read off at once by the measured displacement of the F-line the corresponding amount which the wavelength of the greenish-blue hydrogen light has lengthened or shortened to 10 millionth of a millimeter. Were the F-line to be displaced from its normal place in the solar spectrum to the spot marked 1, figure 158, the wavelengths of the greenish-blue hydrogen light would be shortened 1 of a millimeter. The light would therefore be approaching the eye of the observer, and an eruption of gas be ascending at the spot, figure 157, observed in the middle of the sun. It is easy to calculate that such a displacement of the F-line from its normal center to the spot marked I denotes a rate of motion in the glowing gas of 36 miles in a second. If the F-line were to suffer an equal displacement to the left, that is to say towards the red, the wavelength of the greenish-blue hydrogen light would then be lengthened. The gas would therefore be moving away from the Earth at the same rate of miles in a second, and the stream of gas be sinking down to the surface of the sun, as indicated by the arrow in figure 157. A displacement of the F-line from its normal center to the places marked 2 and 3 in figure 158, either towards the violet or the red, would justify the conclusion that the hydrogen gas was rising from the sun or sinking back to it again at a speed of 72 and 144 miles respectively in a second, from the changes actually observed in the wavelength of the greenish-blue hydrogen light, or from the measured displacements of the F-line, whether bright or dark. It appears that the speed of the gas streams is usually about 18 miles in a second. The observation of the lateral movements must be made on the bright lines of the chromosphere at the sun's lit, either at R or R. The speed of the hydrogen gas is in this case much greater, whether it be approaching the Earth, as at RT near R, or at near R, figure 157, or whether it be receding from the Earth, as at NX next near R, and at 4 near R. The changes in the wavelengths of the greenish-blue hydrogen light occurring at these places are not caused by the rising and falling of the streams of gas, all 9NS 909NI. 3, but by the lateral motion of the streams are all 9 and 24, and they are evident indications that the glowing hydrogen is in a state of rotatory or cyclonic movement. It must again be remarked that even with the narrowest setting of the slit, when the opening is not wider than of an inch, a considerable portion of the sun's surface is still visible. In Lockyer's telescope, the field of view, even with this exceedingly narrow slit, embraces a portion of the sun's surface about 1/800 miles in extent. And in Secchi's telescope, the slit, when fully open, covers a space of from 20 to 24 miles. If, therefore, a vortex of glowing hydrogen gas extending over a space of 900 or 10 miles be in rapid revolution in the neighborhood of the sun's limb, the whole of it may be observed with even the narrowest opening of the slit. In the telespectroscope, the ether waves which are approaching the Earth may be distinguished at once from those which are receding from it, and the motion detected by a corresponding displacement of the F-line. Such a gas cyclone, figure 157, 1, 2, 3, 4, has been observed by Lockyer. When the slit was directed to the middle of the storm, there was an equal expansion of the F-line both towards the red and the violet, which indicated the velocity of the stream of gas to be rather more than 36 miles in a second. When the slit was moved first to one end of the vortex, and then to the other, figure 157-24, it was evident that the ether waves were at one place approaching and at the other receding from the Earth. For in each case, the displacement of the F-line occurred only on one side. Where the displacement was towards the red, a lengthening of the ether waves had taken place, and consequently the stream of gas, figure 157-4, was receding from the Earth, the displacement or expansion of the F-line towards violet only proved, on the contrary, a shortening of the ether waves and the approach of the stream of gas towards the Earth. Observed by Lockyer on the sun's limb on the 14th of March, 1869. With the first setting of the slit, the image of the bright F-line, HSS in the chromosphere, appeared in the spectroscope as in number 1. A slight alteration of the slit gave in succession the pictures 2 and 3. There occurred also a simultaneous displacement of the bright F-line towards both the red and violet, a sign that at that place on the sun a portion of the hydrogen gas was moving towards the Earth, while another portion was going in an opposite direction away from the Earth towards the sun, and thus the whole action of the gas in motion resembled that of a whirlwind. In figure 160 are given 3 different pictures of the same greenish-blue F-line of a prominence which Lockyer observed near the middle of the sun on the 2nd of May, 1869, together with the dark F-line of the faint solar spectrum. In all these drawings, the pointed bright line coinciding in unequal displacement of the greenish-blue hydrogen line, HSS. Direction with the dark F-line indicates that portion of the prominence or chromosphere which was at rest. These lines showed unequivocally that the greenish-blue light of the glowing hydrogen had undergone no change in its wavelength, and therefore that the gas was not in motion either towards or away from the Earth. The bright lines diverging from these normal lines to the right or towards the violet indicate those portions of the prominences that were in motion toward the Earth, with very varying velocities. The greenish-blue line of the hydrogen gas, for instance, manifestly underwent a very unequal displacement in the spectroscope. The lower portions lying close to the dark F line showed a smaller displacement, and therefore a smaller change, shortening, of the wavelength than did the upper portions, an indication that the incandescent hydrogen gas was moving from the sun towards the eye of the observer with a velocity greater in the higher and less dense regions of the solar atmosphere than in the lower strata. By means of the distances from the normal dark F line, which are taken from Angstrom's maps and marked by dots, it is easy to recognize the individual displacements to which the greenish-blue hydrogen line is subject in consequence of motion, and to estimate from them the velocity of the movements of the gas. Lockyer found that the furthest displacement of the bright F line corresponded to a shortening of the wavelength that indicated a velocity in the stream of gas of at least 147 miles in a second in the direction from the sun towards the Earth. These spectroscopic observations receive an additional interest when taken in connection with those made with the telescope. On the 21st of April, 1869, Lockyer observed a spot in the neighborhood of the sun's limb at 7H33. A prominence showing great activity appeared in the field of view. The lines of hydrogen were remarkably brilliant, and as the spectrum of the spot was visible in the same field, it could be seen that the prominence was the spot's. The violence of the eruption was so great as to carry up a quantity of metallic vapors out of the photosphere in a manner not previously observed. High up in the flame of hydrogen floated a cloud of magnesium vapor at 8:30. The eruption was over, but an hour later another eruption began, and the new prominence displayed a motion of extreme rapidity. Whilst this was taking place, the hydrogen lines at the side of the spot nearest to the Earth were suddenly changed into bright lines, and expanded so remarkably as to give undoubted evidence of the occurrence of a cyclonic storm. The sun was photographed at Q on the same day at IOL 55M. The picture showed clearly that great disturbances had taken place in the photosphere in the neighborhood of the spot observed by Lockyer. In a second photograph, taken at 4 ORI, in E, the sun's limb appeared as if torn away just at the place where the spectroscope had revealed a rotary storm. It occurred to both Secchi and Zollner that from the unequal displacement of the C line when observed at the two opposite points of the sun's equator, the speed of the sun's rotation might be ascertained. As a point on the surface of the sun turned towards the Earth moves in the direction from east to west, so a point on the sun's eastern limb must be approaching an observer stationed on the Earth, while a point on the western limb must be receding from him. The points upon the sun's equator would have the greatest velocity, amounting to as much as 192 km in a second. If a spectrum line, as for instance the C line, as for instance, be observed on the eastern limb of the sun which is approaching the observer, it will, in comparison with its position when viewed at the pole of the sun's axis, or even in the center of the sun, appear to be displaced towards the violet. On the contrary, the same line observed on the western limb of the sun, where it is receding from the Earth, would be seen to suffer a displacement towards the red. Secchi thinks he has observed similar displacements in the red HA line of the chromosphere when compared with the constant dark C line in the spectrum of the atmosphere visible at the same time. This bright line, when viewed on the advancing limb in the sun's equator, was seen pushed towards the violet, leaving behind it a narrow strip of the dark C line visible on the side nearest the red. When examined on the receding limb, the line was pushed towards the red, leaving behind it a narrow strip of the C line visible on the side nearest the violet. Although, owing to improvements introduced by Fizeau, instruments are constructed of sufficient delicacy to measure such a displacement, even when it does not exceed 75 of the interval between the 2D lines. And a very ingenious contrivance, a reversion spectroscope, has been specially devised by Zollner, by which this small amount may be reduced 1/2. Yet observations and measure merits of this kind must be received with great caution. The observations of Secchi, as far as they relate to the displacement of the line, are doubtless correct, but it is premature to ascribe this displacement to the rotation of the sun. Not merely because displacements of the bright lines are seen at all times and at all points on the sun's surface, wherever prominences exist, sometimes to one side of the spectrum and sometimes to the other, and that often on the eastern limb of the sun's equator, the red sea line is seen to be displaced towards the red instead of the violet, and the reverse observed on the western limb of the sun, but also because the dark lines of the spectrum ought to suffer an equal displacement, if the cause lay in the revolution of the sun upon its axis. It must therefore be concluded that, at least in the instances adduced by Secchi, the observed displacement of the red line in the spectrum of the prominence was in no way due to the rotation of the sun. Chapter 59. Spectrum Analysis of the Heavenly Bodies, Stellar Spectroscopes, Stellar Spectroscopes. The investigation of the spectra of the planets and fixed stars, commenced by Fraunhofer, has since been carried on at various times by Lamont, Donati, Brewster, Stokes, Gladstone, and others, but their labors were restricted to observing the position of the dark lines present in these spectra, as well as their relation to the Fraunhofer lines of the solar spectrum, without any suspicion of their real nature or connection with the material constitution of the heavenly bodies. It was not till Kirchhoff's discovery of the theory of the Fraunhofer lines that the sun, the planets, the fixed stars, the nebulae, clusters, comets, and even meteors were subjected to analysis by means of their spectra. When it is remembered that the light of the stars, and especially that of nebulae and comets, is very faint, and that in a northern climate there are but few nights favorable for the observation of these delicate objects, in which their light is neither overpowered by the moon nor obscured by mist or cloud. And when it is further borne in mind that since the instruments participate in the daily revolution of the earth, a complicated driving clock is requisite for giving them a contrary motion by which the image of a star may be kept stationary for some time in the field of view, some idea may be formed of the difficulties inseparable from the investigations of the heavenly bodies by spectrum analysis, and some proper estimate made of the services of such men as Angelo Secchi, director of the observatory at the Collegio Romano at Rome, William Huggins, of Upper Tulse Hill, and William, who have won for themselves well-merited honor by their untiring zeal and energy in overcoming so many obstacles. It is obvious that the spectroscopes constructed in the manner most suitable for the analysis of terrestrial substances are not adapted for the investigation of stellar light. Whenever the distances of the lines in the stellar spectra have to be measured, or their position compared with the spectrum lines of any terrestrial substance, the instrument must be attached to an equatorially mounted telescope. That is to say, a telescope made to turn at the same speed as the Earth, but in a contrary direction, so as to follow any star from its rising to its setting, upon which the instrument may be directed, and thus to keep the star stationary in the center of the field of view. The motion of such an instrument is generally accomplished by clockwork, according to the method already described. In connection with figure note, the image of a fixed star in a telescope is, as is well known, a point. Now the spectrum of a point is a line without any sensible breadth, and therefore not suitable for observation. In order to obtain a spectrum of sufficient breadth from a luminous point, the point may either first be converted into a short line of light, which is easily accomplished by the use of a cylindrical lens, and its light, when projected onto the slit analyzed by a prism or a linear spectrum, may first be formed, and then a cylindrical lens employed for increasing its breadth. It is evident that suitable optical contrivances are requisite, a large object glass or concentrating lens, for instance, to collect the greatest possible amount of the faint light of a star and condense it into a short line of light. And further, that on account of the faintness of the object, the dispersive power of the spectroscope must under ordinary circumstances be limited, and the instrument contain only a few prisms. A suitable contrivance is also necessary, whereby, in immediate connection with the spectroscope, all kinds of terrestrial substances may be converted into luminous vapor, either by means of a Bunsen burner, or, which is preferable, a Ruhmkorff's induction coil, and the light thus emitted sent into the spectroscope through the prism of comparison, figure 57, which covers one half of the slit so as to enable the observer to compare the spectra thus formed with the spectrum of a star. From these general remarks, it will be easy to understand the construction of a stellar spectroscope and become familiar with the details of its practical management. The first stellar spectroscope was made by Fraunhofer in 1823. In order to observe the spectra of the fixed stars and at the same time to determine the refrangibility of their light, he constructed a large instrument with a telescope of 4 inches aperture, and placed in connection with it a flint glass prism possessing an angle of 370/40 of the same diameter as the object glass. The angle formed by the incident with the emergent ray was about 26 degrees. Fraunhofer placed the prism in front of the object glass of the telescope, so that the latter served only as the observing telescope to the spectrum already formed. This plan was abandoned by later observers who, after the example of Lamont, allowed the light of the star to pass unchanged through the object glass of the telescope and analyzed the image from the position of the eyepiece, either by a prism alone or else by the use of a small telescope. The Roman observers Respighi and Secchi have lately reverted to Fraunhofer's method and have furnished their large refractors with an object-glass spectroscope constructed by the celebrated optician Merz of Munich. In figure 16.1, the apparatus is represented complete, ready for attachment to the object glass of a refractor. Figure 162 shows the mounting for the prism, and figure 163 the prism when removed from its bed. The prism P is mounted in a ring turning on a horizontal axis, which by means of the lateral pins AX being inserted between the screws H, BX, may be fitted into a second ring. This outer ring is made to travel around the case, by which the whole apparatus is placed in connection with the mounting of the object glass, so as to allow of the prism being placed in any position or inclined in any direction. Merz object glass spectroscope, mounting of the prism. With respect to the object glass or the axis of the telescope, since the rays falling on the object glass are diverted by the prism, the axis of the telescope cannot be pointed direct to the star that is to be observed, in order therefore to facilitate the finding of a star. The case carrying the prism is constructed with an opening at R through which the star may be viewed direct. On the side of the case opposite this aperture is attached an achromatic system of prisms P of equal refracting power with the prism P, by means of which the difficulty of finding a star is much reduced. The prism has a refracting angle of 120. It is composed of the purest colorless flint glass, so that the loss of light it occasions is inappreciable. Its aperture measures 6 Paris inches, and the mounting is provided, as shown in the drawings, with every necessary contrivance for adjustment. Although this prism reduces the effective aperture of the 9-inch refractor of the Collegio Romano to less than 1/2, the amount of light obtained far exceeds that of the refractor with a direct vision spectroscope applied in the place of the eyepiece. The dispersion is, according to Secchi, at least 6 times as great as the most powerful apparatus applied at the eyepiece tube. Zero Merz has also adapted the object glass prism for direct vision observation by constructing it of a combination of crown and flint glass prisms corrected for refraction. The slight loss of light occasioned by such a combination is unavoidable. In an instrument of this kind made for the observatory of Privy Councillor L. Kamphausen at Ringsdorf, the refracting angle of the crown glass prism is 36 degrees, and that of the flint glass prism 250. The mean index of refraction for the crown glass is 1 to 5,283. For the flint glass, 1 to 7,1610 Dye. When an eyepiece spectroscope is employed, which analyzes the optical image of a heavenly body, a point of light, in the case of a fixed star, by means of a system of prisms occupying the place of the eyepiece. Either of the methods above described for spreading out the point of light by the use of a cylindrical lens may be adopted, and it is in most cases a matter of indifference whether this lens be placed in front or behind the slit and prisms. The stellar spectroscope with which Huygens made his first observations, and which was constructed for him by Browning, is represented in figures 164, 165, and 166 diagonally. The outer tube TT of the eyepiece is the only portion of the equatorial telescope given in the drawings. All the other parts are omitted. The spectroscope is attached to the eye and TT of the telescope, a refractor of 8 inches aperture and 10 feet focal length, the whole being carried forward by clockwork. Within the tube TT of the equatorial there slides a second tube B, which carries a plano-convex power to 2 prisms of dense glass of 60 degrees, and is used in the observation of nebulae and faint stars. The spectroscope represented at D contains 2 compound prisms and is filled with Grubb's automatic arrangement. The collimator, which is common to all the spectroscopes, cylindrical lens A of 1-inch aperture and 14 inches focal length. This lens is so placed in the path of the converging rays as they emerge from the object glass that the axis of the cylindrical surface is perpendicular to the slit D of the spectroscope, and by its means a sufficiently broad spectrum of the line of light is formed, the slit D being placed exactly in the focus of the object glass of the telescope, behind Huygens' stellar spectroscope. Partial vertical section. The slit is placed as usual, the collimating lens G, by which the rays are rendered parallel before entering the prism. The lens is achromatic and has a focus of 47 inches and an aperture of inch. By this arrangement, the lens G receives all the light which diverges from the linear image of the star, when this has been brought precisely between the 2 edges, is provided with a perforated mirror and adjustable hole for spectra of comparison, and with a cylindrical lens. It is not represented in the figures of the slit. The parallel rays emerging from the lens G pass through 2 dense flint glass prisms H9, possessing a refracting angle of 60 degrees, by which they are decomposed, and a spectrum formed, which is examined by means of the small achromatic telescope P. In order to measure the distances between the lines of the spectrum, the telescope can be turned upon a pivot by means of a fine micrometer screw Q. The object glass of this observing telescope has an aperture of 0.8 inch and a focal length of inches. The eyepiece usually employed has a magnifying power of 57 times. The micrometer screw is so contrived that it is possible to measure with accuracy an interval of the distance between the H1800 lines A and H of the solar spectrum. The light of the terrestrial elements, the spectra of which are required for comparison with the spectrum of a star, is brought into the spectroscope in the following manner. 1/2 of the slit D is covered with a small prism, an end opposite to which is a mirror S, figure 166, so fastened to the spectroscope by the arm as to be easily adjusted. This mirror receives the light emitted by the substance which, held in the right position by metal forceps fixed into ebonite, is converted into glowing vapor by the induction spark, and reflects it through a side opening in the tube TT into the telescope and onto the little prism E, while at the same time, therefore, the light of the star passes through 1/2 of the slit. The light from the glowing terrestrial substance passes through the other half, and in this way there are formed in the telescope, at the same time, 2 spectra, ranged close one over the other, so that the coincidence or non-coincidence of the dark lines of the star with the bright lines of the terrestrial substance may be observed with accuracy in his researches on stellar spectra. Secchi employs by preference a simple direct vision spectroscope, as a more complicated apparatus, when attached to an equatorial, is liable to destroy the equilibrium of the instrument and interfere with the regularity of the clock motion. The spectroscope employed by Secchi is represented apart from the equatorial in figure 167. MN is the principal tube, which is adapted at M to screw into the eyepiece tube G of the equatorial. To this tube is attached the arc QBC along the divided circle CB, of which the telescope OO is made to travel round the pivot D by means of a fine micrometer screw. For the purpose of measuring the lines of the spectrum, E is an achromatic cylindrical lens, the axis of which can be placed either at right angles to the slit or parallel with it. E is the slit, and 5 a small glass mirror inclined to the slit at a less angle than 450. the upper half of which, being unsilvered, allows the light of the star to pass through unobstructed, while the lower half, acting as a mirror, reflects from its silvered surface into the spectroscope the light of the substance made incandescent in the electric apparatus at LM. The two achromatic lenses, KKK, as their combined foci meet at the slit, act as collimators and render the rays parallel before throwing them on to the system of prisms. The 5 Janssen-Hoffmann direct vision prisms PQPX, QLPL, P figure 47 throw the prismatic rays into the observing telescope OO in the direction G, so that the axis of the equatorial can be directed straight upon the star. In the lateral tube RI is the collimating lens R, in the focus of which is a small metal plate T, containing an exceedingly narrow slit and movable backwards and forwards by means of a fine micrometer screw valve. Through this slit passes the light of an enclosed lamp at I, and forms a very narrow line of light in the inside of the tube RI, which reflected into the telescope QI by the front surface of the prism, serves as a mark to the observer in the examination of the relative positions of the spectrum lines, in order to see the finer dark lines of the spectra, and to compare them with the lines of terrestrial substances. Instruments composed of single and compound prisms have recently been constructed both by Secchi and Huggins, suitable for application to powerful telescopes which admit of a great dispersion of the light. A sketch of Secchi's compound spectroscope without the equatorial is given in figure 168. It is more particularly adapted to celestial objects of considerable diameters. By means of the screw O1, the instrument is attached to the eyepiece tube of the refractor. At K, as in the foregoing arrangement, is a cylindrical lens by which the image of a star appearing as a point is extended into a fine line of light, and brought precisely within the opening of the slit. F is the slit, half of which is covered with the prism for comparison. D, the collimating lens for bringing the rays onto the first prism C in a parallel direction. Both prisms C and D are of dense flint glass, possessing a refracting angle of 60 degrees, and are fastened onto the plate XYZ. They throw the spectrum of the star into the axis of the direct vision spectroscope, EFO, which contains the compound prism EF consisting of 5 prisms, the observing telescope H0, and, as in the instrument previously described, the lateral tube K with a graduated scale. This scale is moved by the micrometer screw M, and when the instrument is in use is illuminated in the usual manner by the flame of a lamp. The image of the scale is thrown by reflection from the front surface of the last prism into the telescope O, where the eye sees at the same moment the divisions of the scale in the spectrum of the star. N is a holder for receiving Geissler's tubes. Huggins' large compound telespectroscope is shown in figure 169. It consists of 2 direct vision systems of prisms, each system composed of 5 prisms, with a train of 3 excellent single prisms, 2 of which possess a refracting angle of 60 degrees and one of 450, making 13 prisms in all. The spectroscope is screwed in the usual manner into the eye tube TT of an equatorial, driven by clockwork. A is the slit provided with a prism for comparison, and the contrivance is already described for the simultaneous observation of the spectrum of a star and that of a terrestrial substance produced by the induction coil. B is the achromatic collimating lens of 45 inches focus, which renders parallel to rays entering the slit. The light is decomposed first by the set of prisms D, then further dispersed, and the individual colored rays still more separated by the following train of 3 prisms F, G degrees, and H for 450. After which it again passes through a second direct vision system of prisms to reach the object glass of the telescope C. The last set of prisms E is placed in a tube attached to the telescope C. By means of a micrometer screw, the telescope can be directed to any part of the spectrum, which is a necessary contrivance in the observation of nebulae. As these objects frequently emit light consist e.g. only of 2 or 3 different kinds of colored rays, the compound prism E can be employed or dispensed with at pleasure so that the dispersive power of the instrument may be made to vary within the limits of from 4e to 6 prisms of 6/0 degrees. The advantage of being thus able to reduce the dispersive power of the instrument is found to be very great when observing faint objects, or when the atmospheric conditions are unfavorable. The excellence of the prisms and the whole instrument is proved by the great purity and sharpness with which, even with high powers, the finest lines in the spectrum can be separated when metals are volatilized in the electric spark. For most purposes, however, and for application to smaller refractors, the dispersion of the stellar light must be accomplished in much less compass than is the case with the instruments just described. The direct vision spectroscope constructed by Merz of Munich for the observation of the solar prominences described at p. 390 is a very efficient instrument for this purpose, and from the simplicity of its construction is easily managed. When attached to the telescope, it is screwed into the sliding tube of the eyepiece, which has been previously removed, and the cylindrical lens L, figure 170, not required for the observation of the prominences, is inserted in such a manner as to project the line of light into which the image of the star has been converted exactly upon the slit 5 to 5, as there is no means of altering the distance between L and 5. The exact adjustment of the line of light onto the slit is accomplished by screwing the whole instrument in or out, which increases or diminishes the distance between the lens L and the image of the star. In observing the spectra of the stars when the light is sufficient to allow of it, the dispersive power may be doubled by the introduction of a second system of prisms without losing the advantage of a direct vision spectroscope. A simple stellar spectroscope is also constructed by Merz, adapted specially to telescopes of small power. A drawing of this instrument is given in adjustable cylindrical lens L and a direct vision system of 5 prisms, the dispersive power of which amounts to 8 degrees from D to H. It is so contrived that the prisms, when separated from the lens L and the eyepiece O, may be easily introduced between the collimator C and the system of prisms of the larger spectroscope, figure 170, which is furnished with a slit. The two instruments, figures 170 and 171, thus form a universal eyepiece spectroscope admirably suited to the observation of the heavenly bodies. Even Browning's miniature spectroscope, represented in figure 49 and described in p. 119, which, including the tube containing the prisms, measures only 3 inches, yields a really fine spectrum when directed on to a bright star, and shows very distinctly the prominent dark lines. The construction of this little instrument is shown in figure 172. The outer tube carries the slit, which can be removed at pleasure, and is easily adjusted by turning round a ring. In this tube slides a second tube carrying the small achromatic collimating lens C, behind which is placed the system of 7 prisms P, and an opening O for the eyepiece without any lens. To employ it in stellar observations, the tube containing the slit is removed, and the collimator tubo screwed into the place of the eyepiece of the telescope. The spectroscope is easily so adjusted that the image of the star is brought into the focus of the lens C, from whence the rays are thrown in a parallel direction onto the system of prisms P, and present to the observer at a sharply defined linear spectrum of the star. By the introduction of a suitable cylindrical lens between the eye hole O and the eye, a sufficient breadth is given to the spectrum for the dark lines to be visible when the instrument is properly adjusted. We must not omit here to mention the simple spectroscopes employed both by Secchi and Huggins in those circumstances when the light is insufficient or the large instruments too cumbrous for use. Huggins has long made use of a hand spectroscope for observing the spectra of meteors and other phenomena in rapid motion in the heavens. Similar instruments were also employed in the various expeditions for observing the solar eclipse of the 1/8 of August, 1868, on which occasion they rendered valuable service. These instruments, as constructed by Browning, consist principally, as shown in figure 173, of a direct vision system of prism C and an observing telescope, a B. The achromatic object glass has an aperture of 12 inch and a focus of about 10 inches. the eyepiece consists of two planoconvex lenses, as a large field of view is very important. Especially when the instrument is employed as a meteor spectroscope, the lens turned towards the object glass equals it in diameter and is fixed in a movable tube, so that the distance between the two lenses of the eyepiece may be controlled, and thus the power of the instrument increased or diminished within certain limits. The system of prisms consists of one prism of dense flint glass and two prisms of crown glass. The field of view of this hand spectroscope embraces a space in the heavens of about 70 in diameter. The spectrum of a bright star has an apparent length of 30. And even the spectrum of the great nebula of Orion appears as two bright lines with a faint, continuous spectrum. For the purpose of testing the instrument as a meteor spectroscope, Huygens observed the spectra of some fireworks at a distance of about 3 miles. The bright lines of the incandescent metals in the fireworks were seen with great distinctness, and showed with certainty the presence of sodium, magnesium, strontium, copper, and some other metals. The same little instrument suffices to show some of the Fraunhofer lines in the spectrum of the extreme points of the moon's cusp, as well as the dark lines in the stellar spectra. In order to give some breadth to the spectrum of a star, which in this instrument appears only as a bright line, a small cylindrical lens is placed over the eyepiece immediately in front of the eye. As the instrument is not furnished with a slit, it can only be used on bright objects of small magnitude, or on objects at such a distance that they have only a small apparent size. Chapter 60. Spectra of the moon and planets, since the planets and their satellites do not emit any light of their own, but shine only by the reflected light of the sun. Their spectra are the same as the solar spectrum. And any differences that may be perceived can arise only from the changes the sunlight may undergo by reflection from the surfaces of these bodies, or by its passage through their atmospheres. The observations of Fraunhofer, Brewster, and Gladstone, Heinrich, Huygens, and Miller, as well as Janssen, agree in establishing the complete accordance of the lunar spectrum with that of the sun. In all the various portions of the moon's disk brought under observation, no difference could be perceived in the dark lines of the spectrum, either in respect of their number or relative intensity. From this entire absence of any special absorption lines, it must be concluded that there is no atmosphere in the moon, a conclusion previously arrived at from the circumstance that during an occultation, no refraction is perceived on the moon's limb when a star disappears behind the disk. Moreover, a small telescope of only a few inches aperture suffices to show the spectrum of the moon very distinctly. The spectra of the planets, Venus, Mars, Jupiter, and Saturn are also characterized by the Fraunhofer lines peculiar to the solar light, but contain in addition the absorption lines, which are known to be telluric lines, section 47, and are evidence of the presence of an atmosphere containing aqueous vapor. The spectrum of Jupiter, which has been recently examined by Browning with a spectroscope attached to his I2-inch reflector, is not of sufficient brilliancy to allow of its being observed or measured with extreme accuracy. Notwithstanding the great brilliancy with which this planet shines in the heavens, its spectrum is not so bright as that of a star of the second magnitude. This is owing to the brightness being more apparent than real, and arises from the large size of the disk compared with a star, and from the light being reflected and not original. As early as 1864, Huygens discovered some dark lines in the red portion of Jupiter's spectrum, which were not coincident with any of the Fraunhofer lines of the solar spectrum, and among them is one that does not occur among the telluric lines. Browning distinctly recognized these lines early in 1870, and thinks that in the green part of the spectrum, near the yellow, several fine dark lines occur which are coincident with those occasioned by the vapors of the Earth's atmosphere, and which are generally visible in the corresponding portion of the solar spectrum when the sun is near the horizon. If it be supposed that Jupiter is in any way self-luminous, these lines may be occasioned by such elements in the planet as are not to be found in the sun, or at present in the sun have not been revealed to us by any effect of absorption. The comparatively faint spectrum of Saturn has been examined by Huygens, who observed in it some of the lines characteristic of Jupiter's spectrum. These lines are less clearly seen in the light of the ring than in that of the ball, whence it may be concluded that the light from the ring suffers less absorption than does the light from the planet itself. The observations of Janssen, which have been supported by Secchi, have since shown that aqueous vapor is probably present both in Jupiter and Saturn. Secchi has further discovered some lines in the spectrum of Saturn, which are not coincident with any of the telluric lines, nor with any of the lines of the solar spectrum produced by the aqueous vapor of the Earth's atmosphere. It is not improbable, therefore, that the atmosphere of Saturn may contain gases or vapors which do not exist in that of our Earth. The great Melbourne telescope and saw the absorption lines as they are described by Huggins. The spectrum of Uranus, which has been investigated by Secchi, appears to be of a very remarkable character. It consists mainly of two broad black bands, 1M figure 174 in the greenish blue, but not coincident with the F line, and the other N in the green near the line E. A little beyond the band 11, the spectrum disappears altogether and shows a blank space, QP, extending entirely over the yellow to the red, where there is again a faint reappearance of light. The spectrum is therefore such a one as would be produced were all the yellow rays extinguished from the light of the sun. The dark sodium line occurs, as is well known, in the part of the spectrum occupied by this broad non-luminous space. Is this extraordinary phenomenon, therefore, to be ascribed to the influence of this metal, or is the planet Uranus, which has a spectrum differing so greatly from that of the sun, self-luminous? Has the planet not yet attained that degree of consistency possessed by the nearer planets, which shine only by the sun's light, and as the photometric observations of Zollner led us to suppose is possible, is still in that process of condensation and subsequent development through which the Earth has already passed? These are questions to which, at present, we can furnish no reply, and the problem can only be solved by additional observations of the strange characteristics exhibited by this spectrum. The spectrum of Neptune, which has also been examined by Secchi, bears a great resemblance to the spectrum of Uranus, is continuous without any part being wanting as far as the feebleness of its light permits it to be traced, which is from about C to about G. On account of the small amount of light from the planet, I was not able to use a slit sufficiently narrow to bring out the Fraunhofer lines. The remarkable absorption taking place at Uranus shows itself in the 6 strong lines drawn that of Uranus. It is characterized by 3 principal bands. The first, which is the faintest, is situated between the green and the yellow, nearly in the center between D and B. It is of considerable breadth, but very ill-defined at the edges. Between this and the red there is a tolerably bright band, with which the spectrum seems suddenly to terminate, and the red is entirely wanting. Secchi is of opinion that the absence of the red is not occasioned by the faintness of this planet for other stars in the diagram. The position of the least refrangible of these lines could only be estimated as it occurs in a very faint part of the spectrum. On this account, it is represented by a dotted line. The measures taken of the most refrangible band showed that it was probably at the position of the solar F. By direct comparison, it appeared to be coincident with the bright line of hydrogen. 3 of the lines were shown by the micrometer not to differ greatly in position from some of the bright lines of air. A direct comparison was made when the principal bright lines of the spectrum of air were found to have the positions relatively to the bands of planetary absorption, which are shown in the diagram. The band, which has a wavelength of about 572 millionths of a millimeter, was found to be less refrangible than the double line of nitrogen, which occurs near it. The 2 planetary bands less refrangible appeared nearly coincident with bright lines, but I suspected that the lines of air were in a small degree more refrangible. There was no strong line in the spectrum of Uranus at the position of the strongest of the air lilies, namely the double line of nitrogen at 500 of the scale. Measures taken with the same spectroscope of the principal bright bands of carbonic acid gas showed the bands in the spectrum of Uranus are not produced by the absorption of this gas. There is no absorption band in the spectrum of Uranus at the place of double line of sodium. An inspection of the diagram will show that there are no bands in the spectrum of Uranus similar to these produced by the absorption of the Earth's atmosphere. No brighter than Neptune show the red clearly in the spectrum. The absence of this color in the spectrum of Neptune must therefore be ascribed to absorption. The second absorption band occurs at the line 6. It is tolerably well defined at the edges, but much fainter and more difficult of observation than the first band. The third band is in the blue and is even fainter than the second. This spectrum is in agreement with the color of the planet, which resembles the beautiful tint of the sea. A peculiar interest attaches to this spectrum from the coincidence of the dark bands with the bright bands of certain comets, and with the dark bands of stars of the fourth type. These bands may possibly be due to carbon, but accurate measurements are exceedingly difficult and can only be attempted on the finest evenings, and with the use of the most powerful instruments, while Jupiter and his satellites, with a power of 350, give a sharply defined image, the disk of Neptune, with the same power ceases to be well defined, and appears with a nebulous edge. From this it may be inferred that the planet is surrounded by a dense mist of considerable extent, the chemical nature of which has yet to be discovered, or else that, like Jupiter, Saturn, and Uranus, it has not yet attained that degree of density which must necessarily precede the formation of a solid surface. Chapter 61. Spectra of the fixed stars. The fixed stars, though immensely more remote and less conspicuous in brightness than the moon and planets, yet from the fact of their being original sources of light, furnish us with fuller indications of their nature. In all ages, and among every people, the stars have been the object of admiring wonder, and not unfrequently of superstitious adoration. The greatest investigators and the deepest thinkers who have devoted themselves to the study of the stars have felt a longing to know more of these sparkling mysteries, and with the child have experienced the sentiment expressed in the well-known lines, "Twinkle, twinkle, little star, how I wonder what you are." The telescope has been appealed to, but in vain, for in the largest instruments the stars remain diskless, never appearing more than as brilliant points. The stars have indeed been represented as suns, each surrounded by a dependent group of planets. But this opinion rested only upon a possible analogy, for of the peculiar nature of these points of light, and of what substances they are composed, the telescope yields us no information. Spectrum analysis alone can disclose to us this much coveted knowledge, as it gives us the means of reading in the light emitted by these heavenly bodies the indications of their true nature and physical constitution. In this light, we possess a telegraphic communication between the stars and our Earth. The spectroscope is the telegraph. The spectrum lines are individually the letters of the alphabet. Their united assemblage as a spectrum forms the telegram. It is not, however, easy to comprehend this language of the stars. But through the indefatigable labors of Secchi, Huggins, and Miller, most of the bright stars, the nebulae, and some of the comets have been investigated by spectrum analysis, and valuable evidence obtained as to their physical constitution, as the spectra of the stars bear in general a marked resemblance to the spectrum of the sun, being continuous and crossed by dark lines. There is every reason for applying Kirchhoff's theory also to the fixed stars, and for accepting the same explanation of these similar phenomena that we have already accepted for the sun. By the supposition that the vaporous incandescent photosphere of a star contains or is surrounded by heated vapors which absorb the same rays of light which they would emit when self-luminous, we may discover from the dark lines in the stellar spectra the substances which are contained in the photosphere or atmosphere of each star. In order to ascertain this with certainty, the dark lines must be compared with the bright lines of terrestrial substances volatilized in the electric spark, and the complete coincidence of the characteristic bright lines of a terrestrial substance with the same number of dark lines in the stellar spectrum would justify the conclusion that this substance is present in the atmosphere of the star, a conclusion that gains all the more in certainty the greater the number of lines coincident in the two spectra, for the purpose of exhibiting the results of his observations before a large audience. Huggins, in conjunction with Miller, prepared accurate drawings of the most remarkable stellar spectra and had them photographed on glass of the size of about 2 inches. By means of these transparent photographs, colored in correspondence with the tints of the spectrum, it is possible by the use of Dubosc's lantern and the electric or Drummond's limelight to magnify these stellar spectra and project them onto a screen, that even at a great distance the dark lines may be easily distinguished. The brilliant spectra of two stars of the first magnitude, Aldebaran, Atari, and Betelgeuse Orionis, taken from these photographs, are represented in figure 175. The poations of all these dark lines, about 80 in each spectrum, which cross that portion of the continuous spectrum of Aldebaran, T. Auricanipare, JWTF solar spectrum, and spectra of terrestrial elements. Spectrum of Betelgeuse Aeonanis, JR between the Fraunhofer lines C and F, were carefully determined by Huggins and Miller through repeated and very accurate measurements. These measured lines, however, are but few compared with the innumerable fine lines which are visible in the spectra of these stars. Beneath the spectrum of each star, the bright lines of the metals with which it was compared are represented. These spectra of terrestrial elements appear in the spectroscope as bright lines upon a dark background in the position shown in figure 175, that is to say, exactly in juxtaposition with the spectrum of the star, so that it can be determined with the greatest accuracy whether these bright lines are coincident or not with the dark lines of the star. The double D line characteristic of sodium, for example, coincides line for line with a dark line also double in both the stars. Sodium vapor is therefore contained in the atmosphere of these stars, and the metal sodium forms one of the constituent elements of these brilliant and remote heavenly bodies. The three bright lines, Mg in the green, are so far as is yet known exclusively produced by the luminous vapor of magnesium. They agree in position exactly, line for line, with the three dark stellar lines B. The conclusion, therefore, would appear to be well-founded that magnesium forms another of the constituents of these stars. In the same way, the two intensely bright lines marked H characteristic of hydrogen gas, one of which is in the red and the other in the blue limit of the green, coincide precisely with the dark lines C and F in the spectrum of Aldebaran, but not, according to Huggins, in that of Betelgeuse. Therefore, hydrogen gas exists in the photosphere or atmosphere of Aldebaran, but is not present in that of Orionis. In a similar manner, other elements, among them bismuth, antimony, tellurium, and mercury, are known to form constituents of these stars. It is necessary to remark here in reference to all these elements that the certainty of their presence in the stars does not rest upon the coincidence of only one line, which would furnish but feeble evidence, but upon the coincidence of a group of 2, 3, or more lines occurring in different parts of the spectrum. The coincidence of many other bright and dark lines of the same substance might doubtless be seen, as in the case of the solar spectrum, were the light of the star more intense, but the faintness of the stellar light limits the comparison to the stronger lines of each terrestrial substance. The question might be asked what elements are represented by the other innumerable dark lines and bands in the stars. Some of them are probably due to the vapors of such terrestrial elements as have not yet been compared with the spectra of the stars. The fact that certain stars possess an atmosphere of aqueous vapor has been observed both by Janssen and Secchi. They belong, for the most part, to the class of red and yellow stars, and in their spectra, as might be supposed, the lines of luminous hydrogen are wanting. As early as 1864, Janssen had remarked the existence of an atmosphere of aqueous vapor in the star Antares, and after a more complete investigation of the spectrum of steam in 1866, section 47, and further observations of stellar spectra made after the total solar eclipse of 1868, in the remarkably dry air of the heights of Sikkim, Himalaya, he could no longer doubt that there are many stars surrounded by a similar atmosphere. Notwithstanding the dry condition of the air, the lines of aqueous vapor were more strongly marked in the spectra of these stars as seen from the heights of the Himalaya than had been observed previously, a phenomenon which cannot be ascribed to the absorption of the Earth's atmosphere, and must therefore be due to that CF. The stars are results of the comparison of the two stellar spectra given above, figure 175, with the spectra of terrestrial elements. are given in the following: hydrogen with the line C and F, nitrogen 3 lines compared, 2 sodium with the double D line 3, magnesium with the triple line B 4 to 5, calcium with 4 lines, iron with 4 lines and with E6, bismuth with 4 lines, 7, tellurium with 4 lines, 8, antimony with 3 lines, 9, mercury with 4 lines, cobalt, tin, lead, cadmium, barium, lithium, line 1, sodium with a double D line 2, calcium with 4 lines, 4, iron with 4 lines, and with E5, bismuth with 4 lines, 6, thallium, nitrogen, 3, tin, 5, gold, cadmium, 3, silver, 2, mercury, 2, barium, 2, lithium, 1 line. Chapter 62. Secchi's types of the fixed stars. While Huggins and Miller had thus been investigating about 100 of the brightest stars, Secchi, favored above his English fellow laborers by the purity of an Italian sky, had already extended his observations over more than 500 fixed stars, and gave the results to the world in 1867, in his work entitled Catalogo delle stelle di cui si determinate lo spettro luminoso, al Osservatorio del Collegio Romano. Since then, above 100 more stars have been added to this catalog by this industrious astronomer, so that there exists at present a rich mass of spectrum observations of the fixed stars, which Secchi has so far provisionally arranged as to be able to group them into 4 principal types, into which all stars, with only a few very remarkable exceptions, may be classified. The first type is represented by the star Lyraea, frontispiece number 12, and also by the well-known brilliant star Sirius, figure 176. Most of the stars shining with a white light are included in this class, such as Sirius, Vega, Altair, Regulus, Rigel, the stars of the Great Bear with the exception of her Ursa, etc., all these stars, although they really shine with a slight tinge of blue. Give a spectrum like that, represented in figure 176, number 1. It is composed of rays of all the 7 colors, and is sometimes crossed by very numerous and mostly very fine lines, but always by 4 broad and very dark lines. Of these 4 lines, 1 is in the red, another in the greenish blue, and the remaining 2 in the violet. All the 4 lines are due to hydrogen and are in exact coincidence with the 4 brightest lines, H, A, J3, Y, T, composing the spectrum of terrestrial hydrogen as produced by means of a Geissler's tube. Micrometric measures of the principal stellar lines to which Secchi's work was mainly restricted. 3 ice types of the fixed stars, in figure 176, no. The dark line C coincides with the line HGS, the F line with H3, the line V with HY, and W with HG besides these 4 broad lines characteristic of hydrogen. The spectra of the brightest stars of this class show also a faint dark line in the yellow, apparently coincident with the sodium line D, and also a number of still fainter lines in the green belonging to iron and magnesium. The most remarkable peculiarity of this type is the great breadth of some of the lines, which seems to indicate that the absorptive stratum must be very thick and under considerable pressure, as well as at a very high temperature. In the smaller stars, the line C in the red is difficult of observation, on account of the faintness of the light, while the line occurring in the blue is often very broad. A slight tinge of blue pervades the color of all these stars. As before stated, consequently, their spectra contain but little red and yellow. While the blue and violet predominate, a complete spectrum of the first type is given in Huggins' drawing of the spectrum of Sirius, figure 177. Nearly half the stars in the heavens are included in this type, and their spectra may be examined even with a telescope of small power. The second type of fixed stars, represented by the spectrum of Arcturus, of Boötes, is that to which our Sun belongs. In this class, most of the yellow stars are included, as for instance Capella, Pollux, Arcturus, Aldebaran in the Great Bear. Procyon, etc. The dark Fraunhofer lines are very strongly marked in the red and in the blue portions of their spectra, but are almost entirely absent in the yellow. The Fraunhofer lines in the solar spectrum, figure 176, number 2, give an example of this. The space between the lines A and D is occupied as is well known, by red and orange. Yellow extends from D to E, while green and blue lie beyond, while strong absorption lines cross the spaces between A and D and between E and G. They are almost entirely wanting in the yellow space between D and E. It is therefore to be expected that this color should predominate in the light of these stars. The dark lines, moreover, are generally sharply defined and only occasionally, as in the case of a Tauri, seem somewhat expanded. The stars belonging to this class are difficult to observe. The dark lines in the spectra of Capella TF lines in the spectrum of Aldebaran appear to the editor as narrow and defined as those of the solar spectrum, and more easily recognized. Aldebaran may be regarded as holding an intermediate position between the second and the third type, while Procyon forms the connecting link between the stars of the first and second type. The dark lines in the spectrum of the second type coincide so exactly with the strongest of the Fraunhofer lines that stars of this type may be used, as suggested by Secchi, as a standard of comparison in the investigation of other spectra. And as a correction for the instrument, this close conformity to the solar spectrum undoubtedly leads to the conclusion that these stars are composed of similar elements and possess a physical constitution in other respects analogous to that of our Sun. Many of them appear to yield a continuous spectrum, but this arises only from the fineness of the lines, which does not allow of their being always visible. They are, however, generally easily seen in a good instrument when the air is clear and free from tremor. To the first type belong about 1/2 of all the stars hitherto observed. Of the remaining half, perhaps 2/3 may be reckoned as yellow stars, to be classed accordingly under the second type. Of the third type, which includes specially the stars shining with a red light, Secchi has given as an example the spectra of the stars Orionis and de Hercules, figure 176, and frontispiece Nos in 14. The spectra of such stars appear like a row of columns illuminated from the side, producing a stereoscopic effect. And when the bright bands are narrower than the dark ones, the spectrum has the appearance of a series of grooves. Red stars of even the 8th magnitude have been examined spectroscopically with Secchi's admirable instrument and show a similar constitution, while no spectrum could be obtained from white stars of the same magnitude. In red stars, the absorption lines are more bands than lines, and resemble the bands produced in the solar spectrum by our atmosphere. The sodium line D is not sharply defined, as in Nozine 2, as a single or a double line, but is very much expanded and shaded at the edges, as shown in the frontispiece, Nos 13 and 14. This seems to indicate that these stars are surrounded by a power TSA statement is not in accordance with the observation of the editor. In some of these stars, as a Hercules, the sodium line falls within a group of lines. In others, as SS Pegasi and Orionis, fine lines are present very near to D under unfavorable circumstances of observation. Therefore, the line D may have the appearance of being expanded and shaded at the edges, fully absorptive atmosphere, the nature of which can only be accurately ascertained when a more perfect knowledge of the influence which the temperature and density of a gas exerts upon its spectrum has been acquired. Only about 30 bright stars belong to this type, among which are Orionis, Hercules, SS Pegasi, Mira, Ceti, Antares, etc. If stars of the second magnitude be included, their number will amount to about 100. Secchi remarks as a peculiar characteristic of these stars that the darker lines of the spectrum separating the grooves occur in the same place in all the stars. The most prominent are those of magnesium, Bn, in the solar spectrum, are often ill-defined. The hydrogen lines are also present, but they do not predominate as in the foregoing types. Hydrogen gas is therefore likewise present in these stars. When its characteristic dark lines, C and F, are not visible in their spectra, an instance of which, according to Huggins, is to be found in Orionis, figure 175, number 2. This anomaly is to be explained by these lines being sometimes reversed, and appearing as bright lines, a phenomenon occasionally to be noticed in the spectrum of a solar spot. Most of the prominent lines belong to metals, which are found also in the Sun. As a rule, the spectra of these stars resemble closely the spectrum of a solar spot. which has led Secchi to the conclusion that stars of the third type differ only from those of the second by the thickness of the envelope of vapor or atmosphere by which they are surrounded, as well as by the want of continuity in their photosphere. It seems therefore that these stars must have spots like our Sun, but of proportionally much larger dimensions. The fourth type, consisting of stars not exceeding the sixth magnitude, is principally characterized by a spectrum of three bright bands separated by dark spaces. The most brilliant band lies in the green, and is in general well marked and broad. The second, much fainter and often scarcely visible, is in the blue, while the third, in the yellow, extends as far as the red, where it separates into several divisions. All these bright bands have this peculiarity that they are brightest on the side towards the violet, where the light terminates abruptly, while towards the red they fade gradually away into black. The spectra of this class are therefore in direct contrast to those of the third type, in which the columnar bands are not only double in number in the same space, but the maximum of their light is turned towards the red, while the darker side is towards the violet. The spectra of the third and fourth types can therefore in no way be regarded merely as modifications of one and the same original spectrum, but must be considered as emanating from substances completely and entirely differing one from the other. The extreme faintness of these stars forbids the use of the slit, and thus the substances emitting their light cannot be ascertained with certainty. Their spectra, however, bear a very close resemblance to the spectrum of carbon. A spectrum of this fourth type is given in figure 176, for number 152 of Kellerup's Tatellite. Secchi has observed about 30 of this class, the most beautiful of which are no speed, 41, 78, 132, 152, and 273 of Schellerup's catalog. Great variety is noticeable in their spectra. Some of them, such as the red star and the Great Bear, in two of which occur in the green and two in the greenish blue in the spectrum of this star, besides these four principal types. There are other groups of stars deserving particular notice. The spectrum of the star using a narrow slit with the brightliness of sodium and carbon. The line marked D he found to be coincident with that of sodium. The less refrangible boundary of the first of the three principal bright bands in the spectrum of carbon is nearly coincident with the beginning of the first group of dark lines. The second of the carbon bands is less refrangible than the second group in the star. The third band of the carbon to these belong, for instance, the stars composing the constellation of Orion, which from the fineness of their spectrum lines ought to be classed under the second type, but which are also remarkable for the almost entire absence of the red and the yellow. All the stars in this portion of the heavens are marked by a twofold character. They have all a very decided green color, and the lines of their spectra are so fine as to be often difficult to distinguish. The region of Cetus and Eridanus, on the contrary, is remarkable for the great number of yellow stars. It cannot be conceived that such a distribution and grouping of stars is merely the effect of chance. It is more reasonable to suppose that it depends upon the nature and condition of the substance with which the various parts of the universe are filled. A remarkable exception to the four types above mentioned is formed by a few stars, which present a direct spectrum of hydrogen, and may be classed, after Secchi's example, under a fifth type. The most remarkable star of this class is Y Cassiopeiae, in the spectrum of which, according to Huggins' measurements, the bright lines Hya, red, and HSS spectrum falls on the bright space between the second and third group of dark lines in the spectrum of the star. The absorption bands are therefore not due to carbon. There is a strong line about the position of C, but this part of the spectrum is too faint to permit of comparison or micrometric measurement. The comparative relative freedom of the red part of the spectrum from dark lines is in accordance with the predominance of this color in the star's light, greenish-blue, are visible in the places of the dark lines, C and F. Besides a bright line in the yellow, apparently coincident with D3, figure 140. Similar spectra have been observed in the variable star SS Lyrae in V Argo, in the spectrum of which Lesueur with the great Melbourne telescope saw the line CBF, a yellow line near to D3, and the most intense of the nitrogen lines as bright lines. The same phenomena were also observed in two temporary stars, of which more will be said in section 65. From all these observations, it may be concluded that at least the brightest stars have a physical constitution similar to that of our sun. Their light radiates, like that of the sun, from matter in a state of intense incandescence and passes in like manner through an atmosphere of absorptive vapors. Notwithstanding this general conformity of structure, there is yet a great difference in the constitution of individual stars. The grouping of the various elements is peculiar and characteristic for each star, and we must suppose that even these individual peculiarities are in necessary accordance with the special object of the star's existence, and its adaptation to the animal life of the planetary worlds by which it is surrounded. Chapter 63. Color of the stars, double stars, and their spectra. In a transparent atmosphere, especially in a southern clime, the stars do not all appear with the white brilliancy of the diamond. Here and there, the eye discovers richly colored gems sparkling on the somber robe of night in every shade of red, green, blue, and violet. And the astronomer, enabled by his powerful telescope to investigate the faintest objects, is lost in wonder over the variety of these colors and their remarkable distribution in the starry heavens. This play of color is most conspicuous in the double stars, so called from their consisting of two or more suns kept together by the bond of mutual attraction, and revolving in orbits according to their mass, either one around the other or both round a common center of gravity. To the naked eye, their appearance is that of a single star, on account of their close proximity, but on the application of sufficient magnifying power, they are found to be constituted of 3, 4, or more suns in intimate connection. Such a system is to be found in the beautiful constellation of Orion in the Sword, consisting of 16 stars, where to the unassisted eye there seems but one. In several of these double stars, the number of which already exceeds 6, it has been possible to calculate the time of revolution of the small star. The period of one in the Great Bear has been found to be 60 years, of another in Virgo 513 years, and of 7 Leones 200 years. A peculiar interest attaches to double stars from their great diversity of color, which occasioned Sir John Herschel to remark in describing a cluster in the Southern Cross that it resembled a splendid ornament composed of the richest jewel. While the majority of single stars shine with a white light, but sometimes with a yellow and even occasionally with a red hue, in double stars the companion is almost always blue, green, or red, thus contrasting with the white light of the larger or central star. It has long been a subject of inquiry whence these colors arise. It has been supposed that they were complementary colors, and therefore that they were not inherent in the stars, but dependent on an optical illusion similar to that produced by looking upon a white wall immediately after gazing at the sun, when the wall appears covered with violet spots. But the simple expedient of covering the central star in the telescope suffices to show the incorrectness of this supposition, for the color of the small star remains unaffected by its separation from the light of the larger one. Zollner, to whom we are indebted for a masterly work on light and the physical constitution of the heavenly bodies, was the first to express the idea that, as all known substances in their transition from a state of incandescence to that of a lower temperature pass through the stage of red heat, so the fixed stars in their process of development from the condition of glowing gas through the period of an incandescent liquid state, and the subsequent development of floating scoriae, or gradual formation of a cold non-luminous surface, must, together with the gradual diminution of their light, be also subject to a change of color. For many colored stars, especially for the so-called new stars, in which the color has been known to sink in the scale from white to yellow and to red. This conjecture of Zollner's has a high degree of probability, but that other circumstances must exercise an influence also on the color of stars is proved by a change of color having been observed to take place in the opposite direction, that is, from red to white, of which, among other stars. We have an example in Sirius, regarded by the ancients as a red star, and which is now considered as a type of the white stars, as well as in Capella, which formerly was red, and now shines with a pale blue light. Huggins and Miller have discovered by means of the spectroscope that the color of a star not only depends upon the degree of incandescence of the intensely hot liquid or solid nucleus, but also upon the kind of absorptive power its atmosphere may exert upon the light emitted by the glowing nucleus. As the source of stellar light, remarks Huggins, is incandescent, solid or liquid matter, Kirchhoff, it appears very probable that at the time of its emission, the light of all stars is alike white. The colors in which we see them must, therefore, be produced by certain changes which the light has undergone since its emission. It is further obvious that if the dark absorption lines are more numerous or more strongly marked in some parts of the spectrum than in others, then the peculiar colors of those places will be subdued in tone, and in any case will appear relatively weaker than in those parts of the spectrum where the absorption lines are much less numerous. While in this way certain colors would be partially extinguished from the spectrum, the remaining colors, being unaffected, would predominate and give their own tints to the originally white light of the star. The spectrum of Sirius, universally known as one of the most beautiful white stars, is given in figure 177. As might be expected, the spectra of these stars are remarkable for the absence of any groups of intense absorption bands. The dark lines which traverse the colored spectrum, though very numerous, and with a single exception equally distributed over all the colors, are exceedingly fine and delicate, and therefore too faint to affect the original whiteness of the light. The one exception consists of 4 strong single dark lines, one of which corresponds with the Fraunhofer C line, another with the F line, while the third lies very near to G, which, as we have already seen, indicate with certainty the presence of hydrogen. If this spectrum be compared with that of an orange-colored star, the largest of the 2 stars composing the group, a Hercules, of which a drawing by Huggins is given in figure 178, the difference between this spectrum and that of Sirius will appear at a glance, for the green, blue, and even the red colors in this spectrum are subdued by groups of intensely dark bands, while the orange and yellow rays preserve nearly their original intensity, and therefore predominate in the light of this star. After conquering many difficulties, Huggins and Miller obtained the same results from the observation of a faint telescopic double star. Figure shows the 2 spectra of the well-known double star SS Cygni. In a large telescope, the colors of these 2 stars contrast very beautifully. The lower spectrum is that of the orange star, the upper that of its faint but beautiful blue companion. In the orange star, the dark lines are observed to be most intense and most closely grouped in the blue and violet parts of the spectrum. The orange, therefore, which is comparatively free from these bands, gives the predominant color to the light. In the delicate blue companion, the strongest groups of lines are to be found in the yellow, orange, and part of the red, so that it is to be expected that blue should predominate in the light of this star, and that we should see it of the hue produced by the mingling of those colors which are left after the absorption of the above-mentioned rays from the white light. The colors of the stars are, therefore, without doubt produced by the vapors of certain substances contained in their atmosphere, and as the chemical constitution of the atmosphere of a star depends upon the elements of which the star itself is composed, and upon its temperature, it would be possible to ascertain the chief constituents of these small telescopic worlds if the position of the dark absorption lines could be determined with accuracy, or if these lines could be compared with the spectrum lines of terrestrial elements. Chapter 64. Variable stars among the fixed stars. There are several which vary from time to time in brightness as compared with neighboring stars. Their light increases or diminishes, and alternates in some cases from the brilliancy even of a star of the first magnitude to complete invisibility. In some, this change of brightness takes place as a constant, very slow and regular diminution of light. In others, there appears an almost sudden increase and decrease of brilliancy, while with others, again, the change takes place within regularly recurring periods. The period of variability is therefore the time elapsing between the 2 successive seasons of greatest brilliancy. The following table shows the varieties exhibited by variable stars of this latter order star. Variation of brightness. Period of variability from 2.7. Argus 1 magnitude, 4 magnitude 46 years Bisafi 6 255 US 73 under 14 428 to 9 days. 0 SETI mirror 1 or 2. 95S Cancri 9 to 485 SSS per se 2 to 867. Of all variable stars, Mira Ceti is perhaps the most interesting, since at its maximum brightness it equals a star of the first or second magnitude. Scarcely less interesting is SS per se, which for 2 days, 13 hours and a half shines with the brightness of a star of the second magnitude. Then suddenly decreases in light and sinks down in 3 hours and a half to a star of the fourth magnitude. Its light then again increases and in a similar period of 3 hours and a half regains its original brilliancy. All these changes recur regularly in the space of less than 3 days, during which the star always remains visible to the naked eye. Whence comes this variation in the light of a star? Zollner, with great acuteness, and supported by numerous observations of these changes of brightness, offers a simple and unconstrained explanation in supposing the cause to lie in the configuration and distribution of dark masses of scoria, which form on the red-hot liquid body of the star in the process of cooling, and which, in consequence of the star's rotation on its axis and the centrifugal force thus arising, would take certain definite courses on the surface of the star in a manner analogous to that which may be observed with floating icebergs on our Earth. As a consequence of this peculiar relative motion, the dark masses of scoriae would arrange themselves in a fixed order and would produce on the surface of the star an unequal distribution of red-hot luminous matter, and accumulations of non-luminous scoria. Were this distribution to assume the form depicted by Zollner in Figure 180, and the variability on a star, according to Zollner, bright liquid mass flowing in the direction of the arrows A and B, or against that of the star's axial rotation, after the manner of the polar streams of our Earth, to become stopped in its course by the bank of scoria. Then the change in the brilliancy of the light coming to us from this star, and the periodic recurrence with every revolution on its axis, would in most cases be easily accounted for. Others think on the contrary, with Stewart and Klinkerfues, that the variable stars are very close, double stars, and that the one in revolution, whether it be a dark body or a yet incandescent gaseous or red-hot fluid mass, would occasion in passing before the larger star either a partial eclipse or an atmospheric absorption of the light, such as not unfrequently happens in our own planetary system. It is instructive to consider how these different theories have been affected by spectrum analysis. If the periodic change in the brightness of a star be occasioned by a change in its physical constitution, or by the interposition of a dark and opaque body, or should the interposing body, whether dark or luminous, be surrounded by an absorptive atmosphere, this would be made apparent by an alteration in the spectrum, consisting of an accession of absorption lines principally noticeable at the time of minimum brightness. Secchi and Huggins and Miller have given much time to investigations of this nature, and the last two observers noticed that in the spectrum of Betelgeuse Aureus, Figure 175, in February 1866, when the star was at its maximum brightness, a group of dark bands was missing, the precise place of which had been determined with great care 2 years before in Figure 175 at number 10,000. 695 degrees of the scale, bordered by a dark line. Secchi has also noticed changes in a dark line in the spectrum of the same star during a diminution of brightness. But these observations are yet too few and isolated for any conclusion to be deduced from them as to the correctness of either of the foregoing hypotheses. It has recently been remarked by Secchi that the spectrum of the nucleus of a solar spot, Figure 108, bears a close resemblance to that given by several red stars, such as Orionis, Antares, Aldebaran, Ceti. A series of dark bands and stripes is represented in the spectrum of Orionis, given in the lower part of Figure 175. Number 2 are present equally in the spectrum of a solar spot as in the spectra of the above-named red stars, which leads to the supposition that the red color of these stars arises from the same cause that produces the absorption bands in the spectrum of the solar spot. As nearly all these stars are variable, it is not improbable that they are also subject to spots, which occur with a certain degree of regularity, as the solar spots have been proved to do. The period of variability in the light would then depend upon the period of the formation of the spots, in the same way as our sun appears as a variable star, of which the period of variation in the light coincides with the regular recurrence of the spots. Chapter 65. New or temporary stars among the variable stars must also be reckoned, those which from time to time, but only at exceedingly long intervals, have suddenly flamed forth in the sky and disappeared again after a longer or shorter interval, and which always excite the greatest wonder and interest, not only from the rarity of their appearance, but also from the mighty revolutions in space which they announce. According to Humboldt, only 21 such stars have been recorded in the space of 20 years, from 134 BC to 1848 AD. The most remarkable of which was that observed by Tycho Brahe in Cassiopeia, which surpassed both Sirius and Jupiter, and even rivaled Venus in brilliancy, but disappeared after 17 months, without leaving a trace visible to the naked eye, and that seen by Kepler in the right foot of Ophiuchus, which excelled Jupiter, but did not quite equal Venus in brightness, and at the end of 15 months was visible only by means of the telescope. Two similar stars which have appeared in recent times, one observed by Hind in 1848, and another seen in the Northern Crown in 1866, though they soon lost their ephemeral glory, still continue visible as stars of the 10th and 9th magnitude. A characteristic peculiarity of these temporary stars is that they nearly all flash out at once with a degree of brilliancy exceeding, in some cases, even stars of the first magnitude, and that they have not been observed, at least with the naked eye, to increase gradually in brightness. Are we to suppose that these so-called new stars are really new creations, as Tycho Brahe believed, and that those that have disappeared are really annihilated or burned out? Can we suppose with Riccioli that these heavenly bodies are luminous only on one side, which by a sudden semi-revolution the Creator at the appointed time has turned towards us? The first supposition has been set aside by later observations, which have shown by the help of maps that a small star had already existed precisely in the place where the new star burst forth. The other view is too absurd to deserve in these days any further consideration. The star observed by Tycho, as well as that one seen by Kepler, are still visible. According to Argelander, the position of the first in 1865 was RA 4-19 near 577th in ND 63 degrees 23, 55. And that of the second, according to Schoenfeld, was in 1855 RA 17-2 IM 57th, with a yearly variation of plus 35,865. SD 210-21-2 with a yearly variation of 5 fives. If, therefore, the sudden bursting forth of a star in the heavens does not denote the creation of a new star, nor its gradual disappearance indicate its complete annihilation, we may well suppose that both phenomena are the successive effects of a violent outbreak of fire taking place in the star, either in the form of an eruption of the internal red-hot liquid matter and its suffusion over the surface, or of the ignition of gigantic streams of gas forcing their way from the interior. While such an occurrence would raise the star to a state of extreme incandescence and cause it to emit an intense light for some time, the cooling subsequent to this combustion would ensue more or less rapidly, and the brightness consequently diminish in quick progression until in certain conditions the star would cease to be visible. Fortunately for science, such an occurrence has taken place since spectrum analysis has been so successfully applied to the examination of the heavenly bodies. On the night of the 12th of May, 1866, a new star, brighter than one of the second magnitude, was observed at Tuam by Mr. John Birmingham in the constellation Corona Borealis. On the following night, it was seen by the French engineer Corvibaz at Rochefort, and was observed a few hours earlier at Athens by the astronomer Julius Schmidt. who expressly declares that the new star could not have been visible before 11 o'clock on the night of the 12th of May, as he had been observing with his comet seeker the star R Coronae, and while sweeping for some time in its neighborhood for meteors, could not have failed to notice the new star if it had been then visible. On the same night, 13th of May, the light of the star sensibly decreased, and by the 16th of May it had become only of the 4th magnitude. Its brightness then waned somewhat rapidly. It decreased from 49 on the 17th to 53 on the 18th, and from 57 on the 19th to 62 on the 20th, till by the end of the month it had become a star of the 9th magnitude. That the star was not a new one was pointed out by Schmidt, who found it marked in Argelander's Durchmusterung des nördlichen Himmels as number 2765 in plus 250 declination. Argelander had observed the star on the 18th of May, 1855, and on the 31st of March, 1856, and on both occasions had classed the star as between the 9th and 10th magnitudes. Huggins was informed by Birmingham of his discovery on the 14th of May, and was thus enabled on the 15th inst., in conjunction with Miller, to examine the spectrum of this star when it had not fallen much below the 3rd magnitude. The result of this investigation is as follows. The spectrum of the star was very remarkable, and showed clearly that there were two distinct sources of light, each producing a separate spectrum. The compound spectrum, figure 181, is seen evidently to be composed of two independent spectra superposed. The one is a continuous spectrum crossed by dark lines similar to that given by the Sun and other stars, while the other consists of four bright lines which from their great brilliancy stand in bold relief upon the dark background of the first spectrum. The principal spectrum traversed by dark lines shows the presence of a photosphere of Incan plus and Mr. Stone. Now Her Majesty's astronomer at the Cape of Good Hope stated as the result of a careful investigation of Mr. Barker's announcement. I have not the slightest hesitation in stating that, in my opinion, Mr. Barker's observations previous to those made on May 14 are not entitled to the slightest credit. Monthly notices, Royal Astronomical Society, Vault 27. 60. Descent matter probably solid or liquid, which is surrounded by an atmosphere of cooler vapors, giving rise by absorption to the dark lines. This absorption spectrum contains two strong dark bands of less refrangibility than the D line of the solar spectrum. A group of fine lines stretches from them close up to D, while one fine line is quite coincident with D. Up to this point, the constitution of this object is analogous to that of the Sun and the stars, but the star has also a spectrum consisting of bright lines, which denotes the presence of a second source of light, which from the nature of the spectrum, P105, is undoubtedly an intensely luminous gas. Spectrum of the temporary star T Coronae Borealis, 15th May. 1866. Huggins compared the spectrum of the star on the 17th of May with the spectrum of hydrogen gas produced by means of the induction spark through a gaseless tube, and found that the strongest of the stellar lines, too, was coincident with the greenish-blue line, HSS frontispiece number 7 of hydrogen gas. Apparently also, the line 1 in the red coincided with the HA line of hydrogen, but owing to the want of brilliancy of the line, the coincidence could not be ascertained with the same degree of certainty. The great brilliancy of these lines, compared with the 5.222 parts of the continuous spectrum where they occur, proves that the luminous gas was at a higher temperature than the photosphere of the star. These facts, taken in connection with the suddenness of the outburst of light in the star and the immediate very rapid decline in its brightness from the 2nd down to the 8th magnitude, have led to the hypothesis already alluded to, that in consequence of some internal convulsion, enormous quantities of hydrogen and other gases were evolved, which in combining with some other elements ignited on the surface of the star, and thus enveloped the whole body suddenly in a sheet of flame. The ignited hydrogen gas, in its combination with some other element, produced the light characterized by the two bright bands in the red and green. The remaining bright lines, among which those of oxygen might have been expected, were not coincident with any of the lines of this gas, the burning hydrogen gas must also have greatly increased the heat of the solid matter of the photosphere, and brought it into a state of more intense incandescence and luminosity, which may explain how the formerly faint star could so suddenly assume such remarkable brilliancy. As the liberated hydrogen gas became exhausted, the flame gradually abated, and with the consequent cooling, the photosphere became less vivid, and the star returned to its original condition. Against this hypothesis, it has been justly advanced that a sudden development of hydrogen in quantities sufficient to occasion the phenomenon of the outburst of a star is a very unlikely occurrence. To which it may be added that the spectrum given by the star was not that of burning, but of luminous hydrogen. Robert Meyer and H.J. Klein have, therefore, expressed the opinion that the sudden blazing out of a star might be occasioned by the violent precipitation of some great mass, perhaps of a planet, upon a fixed star, by which the momentum of the falling mass would be changed into molecular motion, or in other words, into heat and light. It might even be supposed that the star and corona, through its motion in space, may have come in contact with one of the nebulae, section 67, which traverse in great numbers the realms of space in every direction, and which from their gaseous condition must possess a high temperature. Such a collision would necessarily set the star on a blaze, and occasion the most vehement ignition of its hydrogen. Rea and Wolf, who examined the star with a large telespectroscope on the 20th of May, when between the 5th and 6th magnitude, confirmed Huygens' observations, and in their report to Leverrier expressed their independent opinion that the new star owed its brilliancy mainly to burning gases. This brilliancy, as was to be expected, decreased faster than the light of the burning gas, when there was scarcely any trace remaining in the spectroscope of the continuous spectrum given by the photosphere. The 4 bright lines were still quite brilliant. It must not be forgotten that light, though an extremely quick messenger, yet occupies a certain time in coming to us from a star. The speed of light is 185 miles in a second. The distance of the nearest fixed star, a Centauri, is about 16 billion miles, so that light takes about 3 years to travel from this star to us. The great physical convulsion, which was observed in the star and corona in the year 1866, was therefore an event which had really taken place long before that period, at a time, no doubt, when spectrum analysis, to which we are indebted for the information we obtained on the subject, was yet quite unknown. Secchi has recently discovered, while examining spectroscopically the variable star R Geminorum, that its spectrum showed bright hydrogen lines, just as they appeared in the spectrum of the new star T Corax. The star gave besides other bright bands, the most important of which coincide with the dark bands in the spectrum of Orionis. One group lies in the green, and is probably due to magnesium, while another is in the yellow, and appears to be either the sodium D line or else the new bright line D3 of the solar prominences, P396. The observations were made when the star had reached its maximum brightness, somewhat above the 7th magnitude. The great interest which attaches to this phenomenon, especially to the appearance of the same bright lines that characterize the solar prominences, leads us to hope that these observations may be prosecuted during a period of variability, so long as the strength of the light will permit. Vide P. 506. Chapter 66. Influence of the proper motion of the stars in space upon their spectra. In section 58, the principle was unfolded, which, in its application to spectrum analysis, enables us under certain circumstances to determine by the displacement of the spectrum lines of a star whether it be approaching us or receding from us, and at what speed it is moving in space. It was shown that the displacement of one of the spectrum lines towards a violet indicated that the wavelength had been shortened in its passage to the Earth, and therefore that the star was approaching us. A displacement towards the red showed, on the contrary, that the ether waves had been lengthened, and that the star was therefore receding from the Earth. Secchi, who was the first to enter on this kind of investigation, directed his telescope to Sirius, and placed the prism of the spectroscope so that the dark F line was exactly coincident with the direct image of the star. He then turned his instrument to another fixed star of the same type in which the F line was also visible, and observed it narrowly to ascertain whether this line were also coincident or showed some displacement. His instrument did not, however, prove adequate to such delicate observations, and the results obtained were not decisive. By the aid of more delicate instruments and an apparatus better adapted for such measurements, Huggins instituted some very complete investigations on this subject. By a series of preliminary observations, he first established that a strongly marked dark line in the spectrum of Sirius, figure 177, was the hydrogen line. He assessed that for this purpose, he thought that the line in Sirius belongs to hydrogen, was shown by the observation that it is one of three strong lines, which in a spectroscope of moderate power appear to be exactly coincident with the principal lines of hydrogen. It was only when a much more powerful spectroscope was brought to bear upon the star that the slight displacement described in the text was detected. Compared the dark line of Sirius in the usual way with the HSS line of the hydrogen spectrum, formed from a Geissler's tube, which is coincident with the Fraunhofer F line of the solar spectrum, and also with the 50 SS line of hydrogen when under atmospheric pressure. Figure 182 shows the position of these three lines in relation to each other, and to the line in Sirius. While the comparison lines coincide exactly, the line in Sirius is displaced a little towards the red. As this line in Sirius appears broader than the bright hydrogen line HSS, which is always the red-violet Lurs tubes. F line in the Sun, displacement of the F line in the spectrum of Sirius. Case with this line when the gas is subjected to some pressure, it became of importance to determine whether the expansion of the hydrogen line, HSS under pressure, takes place unsymmetrically or on both sides equally. In the first case, it is obvious that the position of the Sirius line could not be regarded as a displacement due to motion, but merely as an expansion occurring on one side only. In the latter case, the bright line HSS ought to fall exactly in the middle of the broad Sirius line, if merely when it is remembered that by employing the requisite number of prisms for producing a sufficiently long stellar spectrum, the light is so much weakened that an exact comparison of the dark lines of the stellar spectrum with the bright lines of a terrestrial element is rendered extremely difficult, and when it is further borne in mind that many dark lines in the stellar spectrum are ill-defined at the edges, and often, like the F line in the spectrum of Sirius, somewhat weak and of varying breadth, we must certainly not place more than a conditional reliance upon the results of such observations, which are admitted even by Huggins to be attended with some uncertainty. With a just appreciation of the great difficulties connected with the measurement of such exceedingly small lineal displacements as might possibly occur in the stellar spectra, Zollner has endeavored to construct a spectroscope with such an arrangement as shall double the amount of this displacement without diminishing at the same time the brightness of the spectrum. The construction of this new instrument, called by Zollner the reversion spectroscope, is as follows. The line of light formed by a slit or a cylindrical lens is brought into the focus of a lens which, as in the continuance of these observations with the larger telescope now at his command, all spectroscopes at once renders the diverging rays parallel. The rays then pass through two of Amici's direct vision compound prisms, which are fastened near to one another in such a manner that their horizontal reflecting angles are placed at opposite sides, so that each one transmits half of the pencil of rays issuing from the collimating lens, thus decomposing the whole of the rays into two spectra which are sent in opposite directions. The object glass of the telescope, which unites the rays again into one image, is divided in a direction perpendicular to the horizontal position of the reflecting angles of the prisms, and each half is capable of micrometrical movement, both in a parallel and perpendicular direction to the line of separate. In this way, it is possible to bring the lines of the one spectrum successively into coincidence with the lines of the other, as well as to place the two spectra at will either in exact juxtaposition, so that one can be moved up and down the other in the manner of a vernier, or else brought partially one over the other. By this construction, not only is the delicate and very sensitive method of a double image made use of for estimating any change of wavelength in the spectrum lines, but every such change is doubled from its influence being exerted in an opposite direction in each spectrum. Zollner was able to determine with the reversion spectroscope the distance between the D lines in the solar spectrum with a probable error of only e of that distance. Were the distance between the source CF light and the observer to change at the rate of 16 miles in a second, the mean velocity of our Earth, it would occasion in Zollner's instrument a displacement of the spectrum lines amounting to 1/5 of the distance between the D lines, a quantity nearly 40 times greater than the supposed error of the instrument. The reversion spectroscope promises not only to remove any remaining doubts as to the displacement of the dark lines being the indication of motion in the heavenly bodies, but also, as Zollner has pointed out, to procure for us more certain results concerning the speed of rotation of the sun, and to separate the lines of the solar spectrum produced by the absorption of the Earth's atmosphere from those originating in the sun itself, since it is evident that such a displacement can occur only in the latter. Chapter 67. Spectra of nebula and clusters. We now come to treat of the remotest realms of the universe, those regions of stellar clusters and nebulae which can only be reached by means of those powerful telescopes. When the starry heavens are viewed through a telescope of moderate power, a great number of stellar clusters and faint nebulous forms are revealed against the dark background of the sky, which might be taken at first sight for passing clouds, but which, by their unchanging forms and persistent appearance, are proved to belong to the heavenly bodies, though possessing a character widely differing from the point-like images of ordinary stars. Sir William Herschel was able, with his gigantic 40-foot telescope, to resolve many of these nebulae into clusters of stars, and found them to consist of vast groups of individual suns, in which thousands of fixed stars may be clearly separated and counted, but which are so far removed from us that we are unable to perceive their distance one from the other, though that may really amount to many millions of miles, and their light with a low magnifying power seems to come from a large, faintly luminous mass. But all nebulae were not resolvable with this telescope, and in proportion as such nebulae were resolved into clusters of stars, new nebulae appeared, which resisted a power of 6-0, and suggested to this astute investigator the theory that, besides the many thousand apparent nebulae which reveal themselves to us as a complete and separate system of worlds, there are also thousands of real nebulae in the universe composed of primeval cosmical matter, out of which future worlds were to be fashioned. Lord Rosse, by means of a telescope of 52 feet, focus of his own construction, was able to resolve into clusters of stars many of the nebulae not resolved by Herschel, but they were still revealed to the eye, thus carried further into space, new nebulae beyond the power even of this gigantic telescope to resolve. Telescopes failed, therefore, to solve the question whether the unresolved nebulae are portions of the primeval matter out of which the existing star is 77.7 Pi, the great nebula in Orion, have been formed. They leave us in uncertainty as to whether these nebulae are masses of luminous gas, which in the lapse of ages would pass through the various stages of incandescent liquid, the sun and fixed stars, of scoriae or gradual formation of a cold and non-luminous surface, the Earth and planets, and finally of complete gelation and torpidity, the moon, or whether they exist as a complete and separate system of worlds. Telescopes have only widened the problem, and have neither simplified nor solved its difficulties. That which was beyond the power of the most gigantic telescopes has been accomplished by that apparently insignificant, but really delicate, and almost infinitely sensitive instrument, the spectroscope. We are indebted to it for being able to say north. Central and most brilliant portion of the great nebula in the sword handle of Orion, as observed by Sir John Herschel in his 20-foot reflector at Feldhausen, Cape of Good Hope, 1834 to 1837. With certainty that luminous nebulae actually exist as isolated bodies in space, and that these bodies are luminous masses of gas. The splendid edifice already planned by Kant in his Allgemeine Naturgeschichte und Theorie des Himmels, I 755, and erected by Laplace 41 years later, has received its topmost stone through the discoveries of the spectroscope in combination with the telescope, affords means for ascertaining even now. Some of the phases through which the sun and planets have passed in their process of development or transition from masses of luminous nebulae to their present condition. Great variety is observed in the forms of the nebulae. While some are chaotic and irregular, and sometimes highly fantastic, others exhibit the pure and beautiful forms of a curve, a crescent, a globe, or a circle. A number of the most characteristic of these forms have been photographed on glass. At the suggestion of Mr. Huggins, to these have been added a few others taken from accurate drawings by Lord Rosse, and they may all be projected onto a screen by means of the electric or limelight lantern and made visible to a large audience. The largest and most irregular of all the nebulae is that in the constellation of Orion, figures 183, 184, nebula of the form of a sickle, 3,239. It is situated rather below the three stars of second magnitude, composing the central part of that magnificent constellation, and is visible to the naked eye. It is extremely difficult to execute even a tolerably correct drawing of this nebula, but it appears, from the various drawings made at different times, that a change is taking place in the form and position of the brightest portions. Figure 184 represents the central and brightest part of the nebula. 4 bright stars forming a trapezium are situated in it, one of which only is visible to the naked eye, the spiral nebula, H-bar. 1173. Nebula surrounding these stars has a flaky appearance and is of a greenish-white color. Single portions form long curved streaks, stretching out in a radiating manner from the middle and bright parts. Mans Monascheften 12182. The glass photographs can be procured from W. Schellen, Cavalier, Rhenish Prussia, and of Mr. Ladbeek Street, Regent Street, London. Much less irregularity is apparent in the Great Magellanic or Cape Clouds, figure 185, which are 2 nebulae in the southern hemisphere, one of them exceeding by 5 times the apparent size of the moon. They are distinctly visible to the naked eye and are so bright that they serve as marks for reconnoitering the heavens and for reckoning the hour of the night. Spiral nebula in Canes Venatici, H. 1622. The interest aroused by these irregular and chaotic nebulous forms is still further increased by the phenomena of the spiral or convoluted nebulae, with which the giant telescopes of Lord Rosse and Mr. Bond have made us further acquainted. As a rule, there streams out from one or more centers of luminous matter innumerable curved nebulous streaks, which recede from the center in a spiral form, and finally lose themselves in space. Or Comet Tail Herschel, number 3239, figure 187, a complete spiral, HE 1173, and figure 188, the most remarkable of all the spiral nebulae situated in the constellation Canes Venatici. It is hardly conceivable that a system of such a nebulous form could exist without internal motion. The bright nucleus, as well as the streaks curving round it in the same direction, seem to indicate an accumulation of matter towards the center, with a gradual increase of density and a rotatory movement. But if we combine with this motion the supposition of an opposing medium, it is difficult to harmonize such a system with the known laws of statics. Accurate measures are, therefore, of the highest interest for the purpose of showing whether actual rotation or other changes are taking place in these nebulae. But, unfortunately, they are Wren nebula with several rings, H. 854, rendered extremely difficult and uncertain by the want of outline, and by the remarkable faintness of these nebulous objects. The transition state from the spiral to the annular form is shown in such nebulae as the one represented in figure 189, H. 604, and they then pass into the simple or compound annular nebula, of which a type is given in figure 190. The space within most of these elliptic rings is not perfectly dark, but is occupied either by a diffuse faint nebulous light, as in figure 190, or, as in most cases, by a bright nucleus, round which sometimes one ring, sometimes several, Incentation is given of a compound annular nebula H854 with very elliptic rings and bright nucleus. According as the ring has its surface or its edge turned towards us, or according as our line of sight is perpendicular or more or less obliquely inclined to the surface of the ring. Elliptical annular nebula, H 1909. Its form approaches that of a circle, a ring, an ellipse, or even a straight line. Nebulae of this latter kind are represented in figure 192, H 1909, and in when an elliptical ring is extremely elongated and the minor axis is much smaller than elongated nebula, H 2601. The major one, the density and brightness of the ring diminishes as its distance from the central nucleus increases, and this takes place to such a degree sometimes that at the furthest points of the ring, the ends of the major axis, it ceases to be visible, and the continuity seems to be broken. The nebula has then the appearance of a double nebula with a central spot as represented in figure those nebulae, which appear with tolerably sharply defined edges in the form of a circle or slight HER-D double nebula. 3501. Ellipse seem to belong to a much higher stage of development. From their resemblance to those planets, which shine with a pale or bluish light, they have been called planetary nebulae. In form, however, they vary considerably, some of them being spiral and some annular. Some of these planetary nebulae are represented in figures 196, H838, H464, and 198, H2241. The first has two central stars or nuclei, each surrounded by a dark space beyond which the spiral streaks are disposed. The second has also two nuclei, but without clearly separable dark spaces. The third is without any nucleus, but shows a well-defined ring of light. The highest type of nebulae are certainly the planetary nebula with two stars, HE 838, stellar nebulae, in which a tolerably well-defined bright star is surrounded by a completely round disk or faint atmosphere of light, which sometimes two stars, H464. Planetary nebula, H4 2241, fades away gradually into space, at other times terminates abruptly with a sharp edge, figures H2098, and 200 H450 exhibit the most striking of these very remarkable stellar nebulae. The first is surrounded by a system of rings like Saturn, with the thin edge turned towards us. The second is a veritable star of the 8th magnitude, and is not nebulous, but is surrounded by a bright luminous atmosphere, perfectly concentric. To the right of the star is a small dark space, such as often occurs in these nebulae, indicating perhaps an opening in the surrounding atmosphere. We have now passed in review all that is at present known of the nebulae, so far as their appearance and form have been revealed by the largest planetary nebula, H2098, stellar nebula, H450, telescopes. The information as yet furnished by the spectroscope on this subject is certainly much less extensive, but is nevertheless of the greatest importance, since the spectroscope has power to reveal the nature and constitution of these remote heavenly bodies. It must here again be remembered that the character of the spectrum not only indicates what the substance is that emits the light, but also its physical condition. If the spectrum be a continuous one, consisting of rays of every color or degree of refrangibility, then the source of light is either a solid or a liquid incandescent body. If, on the contrary, the spectrum be composed of bright lines only, then it is certain that the light comes from luminous gas. Finally, if the spectrum be continuous, but crossed by dark lines interrupting the colors, it is an indication that the source of light is a solid or liquid incandescent body, but that the light has passed through an atmosphere of vapors at a lower temperature, which by their selective absorptive power have abstracted those colored rays, which they would have emitted had they been self-luminous. Spectrum of nebula. 4374, when Huygens first directed his telespectroscope in August 1864 to one of these objects, a small but very bright nebula, H 4374, he found to his great surprise that the spectrum, figure 201, instead of being a continuous colored band, such as that given by a star, consisted only of 3 bright lines. This one observation was sufficient to solve the long-vexed question, at least for this particular nebula, and to prove that it is not a cluster of individual separable stars, but is actually a gaseous nebula, a body of luminous gas. In fact, such a spectrum could only be produced by a substance in a state of gas. The light of this nebula, therefore, was emitted neither by solid nor liquid incandescent matter, nor by gases in a state of extreme density, as may be the case in the sun and stars, but by luminous gas in a highly rarefied condition. In order to discover the chemical nature of this gas, Huygens followed the usual methods of comparison and tested the spectrum with the Fraunhofer lines of the solar spectrum and the bright lines of terrestrial elements. A glance at figure 202 will show at once the result of this investigation. The brightest spectrum of nebula compared with the sun and some terrestrial elements. Line of the nebula coincides exactly with the brightest line end of the spectrum of nitrogen, which is a double line. The faintest of the nebular lines also coincides with the bluish-green hydrogen line, HSS, or which is the same thing, with the Fraunhofer line F in the solar spectrum. The middle line of the nebula was not found to coincide with any of the bright lines of the 30 terrestrial elements with which it has been compared. It lies not far from the barium line BGO, but is not coincident with it. The question why the characteristic bright lines, besides the spectrum containing these 3 bright lines, the nebula gave also a very faint continuous spectrum, figure 201, of scarcely perceptible width, which from its nature could proceed only from the diffused light of a faintly glowing nucleus, either solid or liquid, or from faintly luminous matter in the form of a cloud of solid or liquid particles. All planetary nebulae yield the same spectrum. The bright lines appear with considerable intensity in the spectroscope and are of sufficient brilliancy to compare with the bright lines in the spectrum of a candle. Although the nebulae may not be brighter in the heavens than stars of the 9th magnitude. The reason of this is that the light of the candle is spread out into a continuous spectrum, while that of the nebula remains concentrated into a few lines. The principle is identical with that by which the spectra of the solar prominences have been, since of one line only, of the gases composing them. In a few nebulae, a second line of hydrogen near G is seen, is due to the diminution of their light by the imperfect transparency of interstellar space through which the light has passed, or to their original feeble luminosity. By direct comparison with the light of a candle, Huygens found the intrinsic brilliancy of nebula number 4628 to be equal to JT degrees of the annular nebula and Lyra 2 and of the dumbbell nebula, 2 of the intensity of the flame of a sperm candle burning 160 grains per hour. These results would be affected by any interstellar absorption, should such exist, observed in sunlight simultaneously with the greatly subdued spectrum of daylight, section 57. During the years 1865 and 1866, more than 60 nebulae were examined by Huygens with the spectroscope, mainly with the intention of ascertaining whether those which were clearly resolvable by the telescope into a cluster of bright points gave a continuous spectrum, or one composed of bright lines. The extreme faintness of these objects, and the circumstance that investigations of this kind can only be carried on during the absence of the moon in very clear nights, render spectroscopic observations of these heavenly bodies exceedingly difficult, and the results uncertain. It is only by observations and measures many times repeated, especially when undertaken by different astronomers at various places, that the disturbing influences may in course of time be eliminated, and trustworthy results obtained. As a result of his observations, Huygens divides the nebulae into 2 groups. 1. The nebulae giving a spectrum of 1 or more bright lines. 2. The nebulae giving a spectrum apparently continuous. About a third of the 60 nebulae observed belong to the first group. Their spectrum consists of 1, 2, or 3 bright lines, a few showing at the same time a very narrow, faint, continuous spectrum. They are as follows. The numbers refer to Sir John Herschel's general catalog. Number 4373, Nova HR4D 6245 38 38. Annular nebula in Lyra 33, Dumbbell nebula in Orion clusters, and nebulae showing a continuous spectrum without lines, number 4294 Nobel in Andromeda. Hours 2081H to glass photographs, which Huggins has had prepared from drawings of some of the most interesting gaseous nebulae, include also their spectra planetary annular nebula in Aquarius with spectrum of lines, so that both can be exhibited upon the screen at the same time. Stellar nebula H450, Urias from a drawing made by Lord Ross, figure 199. The nebula, the ring of which is turned edgeways towards us, gives a spectrum of 3 bright lines, as in figure 201, one of which is due to nitrogen and another to hydrogen. Same nebula that has been already given from one of Lord Ross's drawings in figure 200. Its structure is essentially the same as that of the former one. A luminous gaseous mass with a central nucleus of light, and surrounded by a luminous ring, the whole surface of which being turned towards us causes spiral nebula H41964, with spectrum, the nebula, to assume a very different form. The spectrum also consists of 3 bright lines. The nebula, H41964 represented in figure 205, will be seen at a glance to be of a spiral character. It is remarkable because its spectrum contains 4 bright lines, 2 of which indicate hydrogen and 1 nitrogen. The spectrum of the annular nebula in Lyra, H4447, figure 206, consists, on the contrary, of only 1 bright line, that of nitrogen. When the spectroscope is so directed to the nebula that the slit cuts straight through it, the bright line appears to be composed of 2 brilliant lines corresponding to the upper and lower segments of the ring. These 2 lines are united by a small band, which shows that the faint inner portion of the nebula is of the same substance as that of the surrounding rings. The Great Nebula of Orion, figures 183 and 184. Annular nebula in Lyra, WS spectrum, has been the subject of spectroscopic investigations. Its spectrum consists of 3 very conspicuous bright lines, one of which again indicates nitrogen and another hydrogen. Huggins has lately repeated his former observations with instruments of much greater power, and compared especially these 2 lines with those of the terrestrial gases under circumstances which gave him a spectrum 4 times the length of the one he obtained in his earlier investigations. The result of these observations, continued for several nights, was to show the complete coincidence, even in this greatly extended spectrum of the nebular lines, with those of both gases, so that there can be no remaining doubt as to the identity of the lines. Recently, a 4th line has been seen in this nebula by Captain Herschel in India, by Lord Rosse, and also by Professor Winlott of Harvard Observatory, the same line which Huggins had before observed in the nebula H 4964, figure 205, and which belongs apparently to hydrogen. It has been suggested by the last named observer that very probably other faint lines exist in this spectrum, which can only be revealed by more powerful instruments. All actual clusters of stars, separable by the telescope into individual bright points, give a continuous spectrum without either gaps or bright lines. There are, however, some instances where resolvable nebulae, the cluster in Hercules, for example, give different and peculiar spectra consisting of bands and dark lines. It would therefore be interesting to inquire how far and in what manner the classification of nebulae, as given by the spectroscope, is in accordance with the classification made by the telescope. This information is given in the following table. Drawn up by Lord Oxmantown, by whom a Reviati at the present, Earl of Rosse, whose successful researches on Sion has been undertaken of all the observations made with his father's great telescope of such of the nebulae and clusters as had been examined by Huggins. Spectrum, lines, clusters, IO resolved, or apparently resolved, 10O resolvable, or apparently resolvable 5 blue or green. No resolvability apparent 6, not observed through Lord Ross's telescope 10 total, 41 half of the nebulae giving a continuous spectrum, have been resolved into stars, and about a third more are probably resolvable. While of those yielding a spectrum of lines, not one has been certainly resolved by Lord Rosse. Considering the extreme difficulty attending investigations of this kind, there is scarcely any doubt that there is a complete accordance between the results of the telescope and spectroscope, and therefore those nebulae giving a continuous spectrum are clusters of actual stars, while those giving a spectrum of bright lines must be regarded as masses of luminous gas, of which nitrogen and hydrogen form the chief constituents.